We have, let me see in the schedule program. We have, 4 presenters today. Each presenter should finish their presentation, his presentation, within 17 minutes. And then we leave for 3 minutes for discussion. And the first presenter will be presented by Hiroshi Eto. Are you here, Hiroshi Eto?
I'm Yuma Tamura, and I'm presenter of this talk, but I cannot share my screen.
Okay. So you will present instead of, maybe you are okay. Okay, please. Time is yours now. Yeah. Organizing committee, let him allow to share the share screen. Yeah.
I cannot show my screen yet.
So does the computer allow you to share screen, or you have a problem with your laptop? Sure. Hiroshi Ito is the first author of the this topic entitled "Happy Set Problem on Subclasses of O Comparability Graphs." But the co-authors, namely Yuma Tamura, will present instead of him. But now he has a problem with the computer, his computer to share his presentation. Do you have any suggestion that can we allow the second presenter to present first? What do you think? And then Yuma Tamura maybe prepare for the the second presentation sessions. What do you think, Professor Saidun? He has a problem with his computer now.
Actually, we wish to fix the slot because many audience will plan to talk, listen some talk, and they may join at that time.
Okay, so should we wait?
Yes, we should wait, I think.
Okay. No problem then.
I entered Zoom again, but
Okay, I think for testing the system, some other person, would you please test whether you can share it or not? The second author, just test if you are available
Okay,
there.
okay. Okay, the second authors is Dibayan Karaborty and Kisitich Kajar. So, are you in this meeting? The second author. The title of his talk, Finding Geometrics Representation of Apex Graph as a non-polynomial problem.
Okay, now Dr. Tamura has been successful.
Okay, Dr. Tamura. So please, your times now. Yeah.
Can you see my screen?
I saw your screen, but now it's disappear again.
Is it okay?
So please try to share your screen again. Just now I have seen your screen, but it doesn't again appear. Yeah, that's okay. That's fine now.
Okay.
Okay, that's good.
Okay, sorry. I'm sorry, very sorry. Let's start. I'm Wim Tamura, and today I talk about happy set problem on subclasses of co-compatibility graphs. This is joint work with Hiroshi Eto, Takehiro Ito, Akira Suzuki, Tofuku Medeshi, and Eiji Miyano at Kyushu Institute of Technology. Let me start with the notion of happy vertices. For graph G equal V and subset vertex subset S, a vertex V in S is happy if all its neighbors in G are contained in S. In other words, a vertex V is happy if its closed neighborhood is a subset of S. Let's see an example. Given this graph G, suppose that we choose these three blue vertices as subset S. Then this apparent vertex is in S, and all its neighbors are also in S. So this vertex is happy. On the other hand, the other blue vertices are not happy because they have an adjacent vertex that is not contained in S. These black vertices are not happy too because they are not in S. For this subset S, only this vertex is happy. So our question is that, can we make more vertices happy? The answer is yes. If we choose these three blue vertices as a subset S, then the right two vertices are happy. Our task in this study is to maximize the number of happy vertices. Of course, if we choose all vertices in G, then all vertices are happy. So we suppose that the size of S is bounded by an integer k. This is the happy set problem. Here I formally define the happy set problem. Given graph G equal V and non-negative integer k, our task is to find subset S such that the size of S equals k and the number of happy vertices in S is maximized. This problem is motivated by homophily of social networks. Homophily is the principle that we are likely to associate with people who are similar in characteristics such as their age, their occupations, and their interest. And if we belong to the same group with them, we are probably happy. Next, I'd like to show the known result for the happy set problem. This problem has been studied based on graph classes and graph parameters. This problem is solvable in polynomial time for graphs of bounded click widths. Moreover, an order of k times n to the power 8 time algorithm is provided for interval graphs. On the other hand, this problem remains NP-hard for bipartite graphs and split graphs. The complexity on planar graphs is still open. In this study, we further investigate the problem on co-comparability graphs. So let's get closer to these graph classes. The class of perfect graphs has subclasses, caudal graphs, comparability graphs, and co-comparability graphs. Every interval graph is caudal and co-comparability graph. And every permutation graph is comparability and co-comparability. Our first motivation is to analyze the complexity of the problem on co-comparability graphs. Many classical NP-hard problems are tractable for co-comparability graphs. For example, the dominating set problem, Hamiltonian cycle problem, and the feedback particle set problem. So we expected that the happy set problem is also solvable on this graph class. Another motivation is to improve the existing algorithm on interval graphs. For interval graphs, polynomial time algorithm is already known, but can we give a fast algorithm? Here are our results. First, we show NP hardness on co-bipartite graphs. This implies that the problem remains NP hard on co-comparability graphs in contrast to many classical problems. We then give a fast algorithm on interval graphs, which runs in order k squared times n squared time. Furthermore, applying the same method as the algorithm for interval graphs, we design polynomial time algorithm on permutation graphs. In this talk, we will explain the brief sketch of the algorithm for interval graphs. I first introduce some definition of interval graphs. An interval graph is the intersection graph of intervals on the real line. That is, intervals corresponding to vertices and intersection of two intervals corresponds to an edge of the interval graph. In this example, I1 intersects I2, so V1 is adjacent to V2 in G. On the other hand, I1 has no intersection with I3, so there is no edge between V1 and V3. We call this set of intervals an interval representation of G. Given interval graph, a corresponding interval representation can be obtained in linear time. So, in the remainder of this talk, we consider the problem on an interval representation rather than on interval graph. For a subset R of intervals, an interval I in R is happy if every interval that intersects with I is in R. For example, suppose that R equals I2, I3, I4. Then I3 is happy in this interval representation. Moreover, for the vertex set of G corresponding to R, V3 is also happy in G. Before explaining our algorithm, we thought intervals in increasing order of their right endpoints, shown as in the upper figure. Then for integer I, we let Ri equals the set of intervals from I1 to II, and Ri bar equals a set of the other intervals. When I equals 3, I3 equals I1, I2, I3, and I3 bar equals I4, I5, I6, and I7. We compute partial solutions for Ri by means of dynamic programming. That is, by using partial solutions for Ri minus 1, we compute partial solutions for Ri for every I. An optimal solution for Rn corresponds to an optimal solution for the original graph G. So our task is to correctly compute partial solutions for Ri. However, I remark that an optimal solution for Ri may not be extendable to an optimal solution for Rn. In this interval representation, when k equals 3, our optimal solution for R3 is I1, I2, and I3. Then all intervals are happy on R3. But in fact, an optimal solution for whole intervals is I1, I2, and I6, and only I1 is happy. So it is not enough to find an optimal solution for Ri. To correctly compute partial solutions, we focus on intervals that are not contained in optimal solution for Rn instead of the optimal solution. In this case, I3, I4, I5, and I7 is not contained in the optimal solution. If we can successfully guess such intervals, then the problem is solved. But of course, this takes exponential time in general. Our key idea is that not all such intervals are necessary, and it is enough to guess the leftmost interval of Ri bar and the rightmost interval of Ri among all intervals that are not contained in the optimal solution for Rn. In the case of this slide, if an interval of R3 intersects with I4 or I7, it also intersects with I5, which is the leftmost intervals of R3 bar. Conversely, if an interval of R3 has no intersection with I5, then it intersects none of I4, I5, and I7. So roughly speaking, only I5 is necessary to confirm whether the interval of R3 is happy or not. And then I4 and I7 can be ignored. Similarly, if an interval of R3 bar intersects with some interval of R3, then it must intersect I3, which is the rightmost interval of R3 that are not contained in an optimal solution. That is, by two intervals, we can characterize the interval that are not contained in an optimal solution. This is the main idea of our algorithm. More formally, we compute the function Fri, Iu, Id, k prime that return an optimal solution Ri star for Ri cap Id under the assumption that Iu is the rightmost interval of Ri set minus Ri star. Id is the leftmost interval of Ri bar that is not contained in the optimal solution for Rn. And k prime equals the size of Ri star. Each of 4 arguments of this function have possible order n or order k patterns. So the running time of our algorithm is order of k squared times n squared. I omit the details of our algorithm in this talk. I summarize my talk. We studied the happy set problem on subclasses of co-convoluted graphs, and we showed that the problem is NP-hard even for co-bipartite graphs. We then give polynomial time algorithm for interval graphs and permutation graphs. In particular, our algorithm for interval graphs improves the running time of the existing algorithm. Finally, we discuss future work. I believe that our method can be applied to other graph classes, such as trapezoid graphs or circular graphs, which have good representation models. I want to also probe the complexity of the problem for planar graphs. I think the problem on planar graphs is NP-hard, but we cannot probe it yet. That's all. Thank you for your attention.
Thank you, Yuma. It's very nice presentation. Okay, participants, audience, do you have any question for Yuma Tamura? We have 3 minutes for discussion. Yes.
May I ask the question?
Please.
Okay.
Yes.
So for planar graph, do you have any intuition that which problem can be reduced for proving the complex hardness of planar graph?
Sorry, you mean that why the problem on planar graph is hard?
That is you are guessing that it is hard, or the problem is hard. So do you have an intuition that this problem can be maybe reduced to this problem for planar graphs?
I think we create a gadget, some gadget, and we reduced from planar 3-sat to a happy set problem, but I cannot such a gadget yet. I cannot create yet.
Is it clear, Professor Shaidur? Do you have any other response?
It is fine from me.
It's fine. Yeah. Yeah, I just curious, Human. Could I ask about what is the the story of happy set? Then you call this set is happy or something like that. What is the story? It is quite new for me. Can you tell us about the story of this set, and then it is called happy, something like this?
Sorry, yes, story?
Yeah, yeah. So in the definition you have is a happy, yeah. First, second slide, yeah.
Okay.
Yeah.
So
why do you call is happy? Happy vertices.
This problem is motivated by homophily of social networks.
Okay.
So we are likely to associate with friends with similar characteristics, their ages or their occupation, and so on. So if we belongs to the same group with them, similar characteristics with similar characteristics, so we are happy, I think.
Okay, yeah, okay, that's very good. Thank you very much. So that's it for the first presenters. And then I do appreciate about your presentation is very nice, quite clear, and give a new contribution for our study in algorithm and computation as well. So let's stop now. Then we should continue to the second presenter. Please be prepared. The second presenters will be presented by Dibayan or Gajars. They will present a talk entitled Finding Geometric Representations of APEC Graphs is NP-Hart's problem. So are you here? Are you in these meetings already?
Yeah, I'm here.
Okay. So please,
So,
time is yours.
yeah.
Yes.
Let me just share my screen.
Yes, please.
Okay, now it should share.
If you don't mind, could you please turn on your camera, please?
Yeah, 1 second. Yeah,
Yes,
hi, good morning.
And then I can.
Okay, can you see my screen now?
Yes, definitely. Okay.
Okay. Yeah. So I'll start. Yeah. So my name is Kshitij, and this is joint work with Dibyayan. So yeah, all this work was done during the pandemic, so we have never actually met in person with each other. And this research started at the Graph Masters workshop in 2020. Okay, so let me. Yeah. Okay, so what's a geometric representation of a graph in the plane? So you're given a graph that is a set of vertices and edges, and you're given some geometric objects, okay, denoted by the subscript, denoted by M. Okay, so right now think of M as line segments. So the geometric objects you are given as line segments, okay, and you want to represent a graph using line segments. What does this mean? For every vertex of the graph, there will be a line segment dedicated to it. So if the graph has, say, 10 vertices, then there will be 10 line segments, okay? And 2 line segments intersect each other if and only if those 2 vertices have an edge between them, okay? So for example, this is a graph on 5 vertices, okay? And these are 5 intervals on the line. And here notice that 2 intervals intersect if and only if those 2 vertices have an edge between them, okay? Now, there are some graphs which have such representation and some graphs which do not. Okay, so for example, this graph over here, it does not, you cannot represent it using intervals on the linear line. In fact, if you just take this cycle C4, okay, it is impossible to represent C4 using just intervals on the real line. However, what you can do is you can represent it using rectangles in the plane. So here again, notice that there are 5 vertices, so there are 5 rectangles, and 2 rectangles intersect or 2 rectangles overlap if and only if those 2 vertices have an edge between them. Okay, so here are some examples of the geometric objects that we are talking about. So the first one is interval graphs, as we have seen. The second one is something known as pure 2DIR. What this means is that there are line segments, but of only 2 directions. So you can either see that there are either vertical segments or there are horizontal segments. And they are called pure 2DIR because 2 horizontal segments have to lie in, have to have different y coordinates. And similarly, 2 vertical segments have to have different x coordinates. Okay, this is 2DIR. This is not pure 2DIR. Notice that there are 2 vertical segments here with the same x coordinate, and there are 2 horizontal segments here with the same y coordinate. Okay, these are segment graphs. These are just line segment graphs. These are L shapes. So each vertex is represented by an L shape. These are one string. So a string is simply a simple curve in the plane. Okay, and they are called one string because 2 curves can intersect in at most 1 point. So for example, here the blue curve and the pink curve, they intersect in 1 point, whereas the green curve does not intersect either of those. Okay, these are rectangle intersection graphs and these are string graphs. String graphs are a generalization of one string. And here you can see that 2 strings can intersect in more than 1 point. For example, the green string and the purple string. Okay. Yeah, and amongst these, there are obviously containments, and string graphs is the most general. String graph contains all these graph classes that we have seen. Okay. So now, people wanted to represent planar graphs in these forms, like given a planar graph as input, can you represent it using these objects? And the earliest known result is by Kobe from 1936, and it was reproved later also, that suppose you're given a planar graph, then you can represent it using circles. Okay, so, and in fact, it's the theorem is even stronger. It says that not only can you represent it using intersection graphs of circles, the circles that intersect don't intersect in their interiors, they intersect just tangentially. Okay, so you can think of this as coins lying on a table, and two coins touch each other if and only if those two vertices intersect. Okay. Then came Schienermann's famous conjecture that all planar graphs can be represented by line segments in the plane. And this remained unresolved for quite some time. Then was Hartmann et al. They solved a simpler problem that if your graph is planar as well as bipartite, then you can represent it using a specific set of line segments, which is pure 2D-IR, which I mentioned earlier, that all your line segments are horizontal or vertical. Okay. And around the same time, people were unable to prove Schienermann's conjecture. So West stated an even stronger conjecture that, okay, all planar graphs can be represented as line segments having only 4 different slopes. Okay, so you can't have line segments having all arbitrary slopes. There'll be 4 fixed slopes, and those are the type of line segments you are allowed. Okay, and note that if West's conjecture was true, then it would be an alternate proof of the 4-color theorem, because lines of a particular slope, you can assign all of them the same color. Okay. Soon thereafter, it was shown that triangle-free planar graphs, a subclass of planar graphs, do have segment representations. Okay, and finally, Schienermann's conjecture was resolved 25 years later, from when it was conjectured. And subsequently, it has also been shown that planar graphs can be represented using homothetic triangles. That is, triangles that have the same shape. You can't rotate the triangles around. You can translate them. Okay, and they can also be represented using L shapes, which were described. And the most recent result is that West's conjecture is false. So you can represent planar graphs using line segments, but not with 4 different slopes. There are planar graphs which require at least 5 slopes. Okay, so this is a brief history of where these results stand. So now what we were interested in, all these results are for planar graphs. Okay. Yeah. Sorry. So what we were interested in was what happens when the graphs are slightly non-planar. So by the way, if your graphs are non-planar, then such representations need not exist. In fact, there are easy counterexamples to show that they do not exist. Okay. Now, what is an apex graph? Apex graph is simply a planar graph with one extra vertex. Okay, so an apex graph on say 100 vertices, it means that there is one vertex from this graph that you can remove, such that the graph on the remaining 99 vertices is planar. Okay, so it turns out that these theorems do not generalize to apex graphs. So this is a simple counter example. So this is the graph K33, and each edge has been subdivided. That is, one vertex is placed on each edge. Okay, and you can show that this is not even a string graph. Like the most general graph does a string. So this is an apex graph because you remove any one of the blue vertices, it becomes planar. So it is an apex graph, but this is not even a string graph. Okay, so we wanted to ask the following question. So what is the computational complexity of representing apex graphs? So all those results that we just saw about planar graphs being represented as L shapes or homothetic triangles or segments, they are all constructive. Those constructions can be carried out in polynomial time. That is, if you're given the planar graph, okay, you can in polynomial time construct it using those objects. So we asked, what is the computational complexity of constructing apex graphs? And the reason this question is interesting is because if you have non-planar graphs, then those constructions are NP-hard. That is, it is NP-hard to even check whether a representation exists. Forget about finding the representation. Just the decision problem is NP-hard. Okay, so apex graphs are very close to planar graphs. In fact, they are just one extra vertex from planar graph, and we want to know what is the computational complexity. And we show that it is actually NP-hard. And this was a bit surprising to us because for planar graphs, all these can be done in polynomial time. And it turns out you just put one extra vertex and it suddenly becomes NP. So in particular, what we show is that if you have a graph class, for any graph class that is bigger than pure 2dir or equal to it, and smaller than one string or equal to it, okay? Any graph class that that is sandwiched between these two, it is NP hard to even decide whether an input graph belongs to it. Okay, if the input, even if the input graph is apex, and even if it is bipartite. Okay, so let me just see. Yeah, so as you can expect, because you can substitute different values in this subscript G here, okay, in this calligraphic G, sorry, we have some corollaries. So, recognizing intersection graphs is NP hard, okay, and this strengthens the results of Kratochvil and Matuszek. The next one is for L shapes also, it is NP hard because L shape is also sandwiched between those two. This strengthens the result of Schmel, and rectangle intersection graphs strengthens the result of Kratochvil. Okay. And some of these also simplify the proofs because some of these proofs were a bit complicated and our gadgets are a bit simpler, as I'll explain shortly. Okay, so what's our technique? So it's an NP hardness proof. So it is a reduction from a known NP hard problem, which is the planar Hamiltonian path completion problem proposed by Auer and Kleibner around 11 years ago. So the problem is just this. So you're given a planar graph, okay? Find out whether it is a subgraph of a planar graph with a Hamiltonian path, okay? So the graph itself need not have an Hamiltonian path, but can you add more edges to it such that the graph remains planar and it has a Hamiltonian path? Okay, and this is NP hard. This problem to check whether it is PHPC is NP hard. Okay, PHPC stands for planar Hamiltonian path completion. Okay, so this is how we show our main theorem. So suppose you give us a planar graph, okay, then and your graph class is calligraphic G, where G is between one string and pure 2dir. Okay, so we'll prove both these A and B. So the A part is that if the graph is in one string, that is, if it has a one string representation, then it is a then it is a yes instance, or which means then it is a subgraph of a planar graph with the Hamiltonian path. And if and the B part is the other direction, if it is a subgraph of a planar graph with Hamiltonian path, then it is in pure 2dir. So notice that if the graph has a pure 2dir representation, then obviously it is in G because pure 2dir is a subset of that. And if the graph is sorry, which direction was it? Yeah, if because one string, if it has a one string representation, then obviously it has a representation using those objects. Okay, so now yeah, okay, so this is the basic technique. So you're given a planar graph, okay, and you want to construct an apex graph out of it. This is a reduction. So it's a two-step reduction. So here I've given a planar graph and I have not drawn the Hamiltonian path. So notice that the path V1, V2, V3, V4, I have drawn it in dotted because it needs to be a subgraph of a graph with a Hamiltonian path. Okay, so these are all represented by dotted edges. Okay, so the Hamiltonian path is not yet drawn. What I do, the first step is I do a 3 subdivision of each of its edges. Okay, so each edge is subdivided by 3 vertices, or rather each edge is replaced by a path on 4 edges. Okay, so obviously this can be done in polynomial time. And the next step is that I add an apex vertex. So I add an extra vertex, which is connected to all the blue vertices. So the blue vertices are the original vertices that are coming. The red vertices are the new vertices that we are inserting. Okay, and this big red vertex is the apex vertex. So note that if you remove the apex vertex, clearly the graph that you are left with is planar. Okay, so it is an apex graph. Okay, so first we'll prove part A. So suppose you are given a one string representation. Okay, so the apex is also obviously represented by a string. So let this be the string, that is CA. Okay, and obviously these since the apex is connected to only these 5 blue vertices, okay, each of those 5 blue vertices are represented by strings. Now look at the order on these. So you start from one end of the apex vertex and you travel along it all the way towards the upper end. The first one that arises, we call it V1. The second one V2, the third one V3, and so on. Okay. Now, because this is we have subdivided 3 times, there are 3 vertices between each. So for example, consider V2 and V4. So there is this one string here, another string here, and another string here. Okay. What you can do is you can concatenate these strings to form a single edge. And that's why it is a planar representation. So this is a graph drawn on a plane where these are just bit of strings. But if you think of them, you can think of the strings as edges itself. Okay. So the 5 blue strings here represent the 5 vertices. The part between the blue string represents the Hamiltonian path. Okay. So this is one part of one edge of the Hamiltonian. Sorry. This is the second edge, this is the third edge, and so on. So eventually you get something like this. So this is the super graph of this graph, which has a Hamiltonian. Okay. In the other direction, we'll show that if G is a yes-instant, that is, if G has a Hamiltonian path, then it is in pure 2D IR. Okay, so this is the graph. Again, we do the same thing. We subdivide it 3 times. We have the apex vertex, and this is the representation. Okay, so for the apex, you have, so notice that in pure 2D, you're only allowed to use vertical and horizontal segments. So for the apex, we'll always use a big vertical segment like this. All the blue vertices or the original vertices, they will be horizontal segments. So they'll be like this. And in this order, the order that we are given in V1, V2, V3, okay, and so on. Now, notice that some of them are extended to the left, some of them to the right, and some of them in both directions. So V1 has 2 edges going, emanating from it towards the right-hand side. So V1 is extended to the left, sorry, to the left-hand side. Similarly, V2 has a couple of edges to the left, something to the right. V3 only has edges to the left, so it's only to the left, and so on. Okay. V7, for example, has only edges to its right, so it's extended to the right. And now you can just complete it. You can draw all the remaining subdivision vertices using these horizontal and vertical segments. In most cases, you could have done it using only one subdivision. Like you could have connected these using one segment, but the ones that are going across, all the way across, so V7 and V5, it's going all the way across here. For that, you need 3 segments. Okay. And this is it. That's it. That completes the proof. And before ending, I'll just mention a few open problems. So what we consider is almost planar graphs or apex graphs, where you can remove one vertex and you can make it planar. Okay, this is one definition of almost planar. Okay, what is another definition is you could also have something like one planar graph. That is, they are not planar, but each edge crosses only once. Okay, then you have graphs with crossing number 1. This is an even more restricted case in which there is only one pair of edges which are crossing. Then there's K5 minor phi graphs. So notice that apex graphs are K6 minor phi. So why not consider K5 minor phi? Then you have graphs embedded on the torus, graphs embedded on the projected plane, and so on. Okay. And we also want to know what is the complexity of recognizing an even more general class, that is of classes of non-piercing regions. Okay, these are just objects, like they could have any weird sort of shapes, but they cannot pierce each other. Okay, so yeah, so that's it for my talk, and yeah, I would like to stop here. Thank you.
Okay, thank you very much, Gaja. It's very nice presentation.
Thank you.
Okay, let me having a discussion time now. Participant, audience, do you have any discussion or some questions given
I have
to
one question.
Gaja? Yes, please, yeah.
So it's very nice talk, and so it's very interesting that apex graph is quite different from planar graphs. So
Yeah.
it seems that because apex graph has a very complicated forbidden minor structure. So I wonder whether there is some relation of this kind of geometric graph theory and also the graph minor theory. So are there any characterization of that kind of geometric graph by using graph minor or so?
I think so. I don't remember. So apex graphs can be characterized using
yeah, but forbidden minor structure is it's closed, so minor closed, but
yeah.
forbidden minor is very complicated. So
so your question is, did we consider like other minor closed families?
Yeah. So from the viewpoint of the graph minor theory, so.
Yeah, we didn't. Like one thing we do want to consider, as I mentioned, is this one, K5 minor phi graphs. But we haven't considered more. Yeah, so I mean, even these toroidal graphs, they can be represented by a I mean, characterized by a finite set of forbidden minors. But yeah, this is interesting. Like you give a set of forbidden minors and can be represented like that. It should be NP hard, but yeah, should it be? I don't know. We don't know.
Okay, thank you very much. Yeah.
Okay, thank you. Very nice.
Thank you.
Okay.
Thank you.
Other audience, do you still have a question to give to Gajar presentation today? Okay, if not, that's it for the second presenter.
Thank you.
Then you can close the share screen, Gajar. Thank you very much, Gajar. It's very nice talk.
Bye.
Okay, for the second presenters, the title will be the complexity of LPQH labeling. Yeah, it is a graph labeling study. Then this title will be presented by Gaitam Bertha, Barnaby Martin, Daniel Paulusma, and Siani Smith. But unfortunately, I have news from the organizing committee that those authors cannot join this session, but instead they have a video to give it to us. Yeah. So is it right? Yeah. Yuhara, it is right. If yes, then we can see and hear the video of this presentation. Okay. Who will share the video of this? Okay, yeah, okay then.
So welcome to my WALCOM presentation. I will now share my screen.
Oh, okay, yes. You are now, yeah, okay.
So my plan is not to give any proofs of the results I will show, but instead place the results in a historical context, in particular the context in which I came to study these sorts of problems. Given that it's a relatively short talk, I think this is probably the most appropriate thing to do. So I am Barnaby Martin. You can see my co-authors around me. So let's start with the coloring problem. A K coloring of a graph C is a mapping from the vertices to a set of colors 1 up to K, such that whenever U and V are adjacent, they have different colors. Sometimes this is called, of course, a proper K coloring. And from this, we have two problems, coloring and K coloring. And in coloring, the integer that is the positive integer that is the number of colors is a part of the input, whereas K coloring gives a whole family of problems for which it is fixed. Now, my interest in this broad area is mostly these days in H-freeness. So you study an algorithm that would be of high complexity in general, maybe an algorithm that's exponential in general, for a problem that's NP hard, and you ask whether, if you restrict the instances to some instances that omit some small set of graphs, maybe one graph, in this case it's just one graph, and ask, does the problem become easy? So a graph G is said to be H-free for some graph H if G has no induced subgraph isomorphic to H. So for example, this graph is not K3 free. It does in fact have an induced copy of K3 in it. So coloring, K coloring problems have been extensively studied for H-free graphs. And for coloring, this is where K is part of the input. A complete complexity dichotomy has been known for a while. So coloring is polynomial time solvable for H-free graphs if H is induced in P4 or induced in P3 plus P1. This plus is disjoint union here, and it's NP complete otherwise. So for H-free graphs where H is just a single graph, we have a complete dichotomy here between the NP complete cases and the polynomial cases. Now, when K is part of the input, things get a little bit more complicated. K coloring is known to be NP complete for H-free graphs where H contains a cycle or a claw. And in fact, K coloring is NP complete for graphs of arbitrary girth. This is the result that we just mentioned. Actually, this is the result that K coloring is NP complete for claw-free graphs. But unfortunately, this is not dealing with all situations because there are still some linear forests that show themselves. So combining these results, the remaining open cases are those where H is a forest of maximal degree 2, known as a linear forest. Although much progress has been made on these cases, infinitely many remain open. For example, 3 coloring remains open for PT-free graphs with T greater than or equal to 8, and K coloring for K greater than or equal to 3 is open for SP4 free graphs. So that's the disjoint union of S copies of P4. So here is the situation for coloring. We do have a complete dichotomy when K is part of the input, but we have these open cases for fixed K. Now, I became interested with my co-authors in various other versions of coloring. One, which is an acyclic coloring problem. And an acyclic K coloring is a K coloring such that the graph induced by any 2 color classes is a forest. It doesn't contain any cycles. And then a more restrictive version, a star K coloring of a graph is a proper K coloring, such that the union of any 2 color classes induces a star forest. In other words, any cycle, any path on 4 vertices is assigned at least 3 different colors. And finally, an injective K coloring of a graph G is a proper K coloring such that the union of any 2 color classes induces a disjoint union of edges and vertices. So in other words, any path on 3 vertices is assigned 3 different colors. So acyclic coloring is the least restrictive. Star coloring is more restrictive than acyclic coloring, and injective coloring is more restrictive than star. Some definitions of injective coloring don't actually require that the original coloring be a proper coloring, but for us it must be. Now, this is actually the topic of the paper at WALCOM. So instead of coloring, we call it a labeling problem, but this is just a historical thing. The labeling and the coloring is the same. The difference is that labels are numeric values, whereas the coloring problem could in principle be any colors. Although in the definition we gave in this talk, we actually gave them to be positive integers. So an LPQK labeling of a graph G is a K coloring such that adjacent vertices are colored with values at least P apart, and vertices between which there is a path of length 2 are colored with values at least Q apart. So L11 labeling is precisely injective coloring, and these LPQ labeling problems generalize injective coloring. Now, some authors actually phrase 2 in a different way, as vertices at distance 2 are colored, rather than vertices for which there is a path of length 2, because vertices at distance 2 could actually have a path, vertices at distance, when there is a path of length 2 between 2 vertices, they could still actually be at distance 1. That's why the 2 definitions are not the same, but the 2 definitions are the same so long as P is greater than or equal to Q. So I spent with my co-authors quite a long time studying this problem. And when K is in the input, so when K is part of the input, we got to the point where we have this full classification, except one open case for acyclic, one open case for star, one open case for injective. And actually the open case for star and injective is the same. So we're doing quite well here. Actually for fixed K, for acyclic coloring, star coloring and injective coloring, we have a complete classification. Whereas for K coloring, we discussed that in the linear forests, there are cases that are where there are infinitely many open cases still remain. Now, one of the big cases that you have to do when you study algorithms for H-freeness is the claw-free case. So there are various cases that one often considers. Cycle-free cases, so bipartite graphs, for example. Well, bipartite graphs only emit odd cycles, but in general, cycle-free cases are good. How would we prove cycle-free cases? Often we do it by proving that something holds for arbitrarily high girth. Claw-free is an important case that we have to deal with. And in fact, for all of these coloring problems where K is fixed, the claw-free case is already NP complete for a large enough K. Actually, the K at which it becomes NP complete is different from injective coloring to star and acyclic coloring, because injective 3 coloring is always polynomial. How do we deal with the claw-free case? Well, often we do it through the method of line graphs. And how do we make line graphs? Line graphs are always claw-free. And how do we prove the result for line graphs? We'll take the vertex version of the problem and turn it into the edge version of the problem. So for each of our 3 problems, these are the 3 problems on the previous slide. We follow the same approach used for K coloring to prove NP completeness for claw-free graphs. So we look at the edge coloring version and it's NP complete. And then a graph G has an acyclic or star injective K edge coloring, if and only if it's a line graph. If its line graph has an acyclic star injective K coloring. So if you can prove NP completeness for line graphs, you've dealt with the claw-free case. And in order to do the line graph case, you just study the edge version of the original problem. So as it happens, the basic edge versions of these problems were studied already some time ago, certainly for acyclic edge coloring, where acyclic 3 edge coloring was known 20 years ago to be NP complete. Now in work, in recent work, but not at WALCOM, we generalized this K to numbers greater than or equal to 4. In the star coloring case, we again have that star 3 edge coloring is NP complete, and we've generalized that to star K edge coloring is NP complete for K greater than or equal to 4. Now, what about injective coloring, which of course is L11 labeling? So Mardian proved actually that for any girth greater than or equal to 3 and any K greater than or equal to 4, something called strong K edge coloring is NP complete for bipartite graphs of girth at least G. And actually this strong edge K coloring is equivalent to injective K coloring, or injective K edge coloring. The strong edge K coloring is equivalent to injective K edge coloring. So therefore, injective K edge coloring is NP complete for line graphs and hence claw-free graphs. And so here is sort of a starting point for the present paper, that for any girth, large girth, and any K greater than or equal to 4, L11 edge K labeling is NP complete, even on bipartite graphs of girth at least G. So that's sort of setting the scene for the work in the present paper, but the result that we really build on in the paper is this one by Knopp and Mazurek, where they prove they were dealing with the not L11 labeling, but L21 labeling. Now in the literature, L11 labeling and L21 labeling, the most common instances of the labeling problem. And since the L11 labeling problem actually has many, many other names, somehow the most important instance of the LPQ labeling problem is the case P, Q equals 2, 1. So L21 is the really important case. And what they proved, they were already natively studying the edge labeling problem. For me, I usually was involved in the edge labeling problem because I'm interested in the vertex problem, but for H-free graphs, for claw-free graphs, let's say. But they, in their paper, they study specifically the 2-1 case, and they prove that it's in polynomial time for K less than 6 and is NP complete for K greater than or equals to 6. And this is truly the starting point for the research that generated this paper at WALCOM. So Jarek communicated to me that the authors of this paper actually wanted to settle the complexity, not just for 2,1 labeling, but for many more cases. But actually it became quickly quite complicated, and the 2,1 case was already quite sophisticated. And they left it at that, and they just published it at that. By the way, in the literature, the case where P is larger, greater than or equal to Q is much more prevalent. I mentioned already that when P is greater than or equal to Q, you have this this alternative definition, which you sometimes see in the literature. When Q is greater than P, things get a bit strange, and the two definitions don't necessarily coincide. Now, the Knop and Majarek proof, in fact, doesn't just work for P, Q equals 2,1. It actually works in this whole range where Q over P is greater than 0 and less than or equal to a half. So now I want to give our results basically in one line. So for all PQ greater than 0, except the trivial case where P equals Q equals 0, there exists an integer K such that LPQ edge K labeling is NP complete. So what's interesting about this is one can't just provide a single proof that deals with all cases. I said already that the Knop and Majarek case, it's down here. It works not just for Q over P equals 1 over 2, but it works for Q over P between 0 and 1 over 2. But then when we started working on this problem, we quickly found that we had to find different arguments for different ranges. And these are the ranges we have here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 ranges. And of those 9 ranges, 2 of them were basically settled before. The P, Q equals 1,1 case we've already mentioned, and Knop and Majarek dealt with this case that Q over P is less than or equal to 1 over 2. But for the others, we had to come up with tailored algorithms or tailored reductions for each of the regimes. And indeed, although there is some commonality in the gadgets we build, the properties of the gadgets are different. And that's why the reduction isn't always from the same problem. Some reductions are from coloring, 3 coloring, some reductions are from not all equal 3 sat, and some reductions are from more complicated versions of sat, monotone, 1 in 3 sat, monotone, 2 in 4 sat. And finally, an interesting thing about our proof is that for the particular case, Q over P equals 2 over 3, the properties of our gadgets were discovered and verified by a computer. So it got to the point where we had an idea what sort of gadgets we wanted to build, but to prove that the gadgets have the right properties, when you're actually modifying these gadgets on the fly, we found that it was much easier to do this with a computer. And so we were working all the time with a computer. It's interesting that a number of these regimes here on the left-hand side are particular points as opposed to ranges. Some of them are points and some of them are ranges. So what are the 2 principal directions for future work? Well, the first is determining the boundary for K between P and NP complete. And this is by and large known. In fact, it's by and large not known. In fact, it's only known at P, Q equals 1,1 and P, Q equals 2,1. So if we look here for Knop and Majarek, the boundary is 6, and they know that. But for our results, we only show that eventually for K, it becomes NP complete. We're not quite sure at exactly the boundary where it becomes NP complete. And finally, for me, the very interesting thing is to take this research and purpose it for what it was originally intended, which is the edge-free case. So the present paper is dealing with edge labeling, but it would also apply to the vertex labeling problem in the case of line graphs. And hopefully we can make progress there and finish that project. Thank you.
Okay, so that's the video presentation from the 3rd paper entitled The Complexity of LPQH Labeling. Since the authors are not joining this session. So I believe there is no discussion session for this presentation. So let's move on to the fourth presenters. The fourth presenters will present the talk entitled Trains, Games, and Complexity, and so on. It will be presented by Joshua Ani et al. One of your authors is already here.
Yes, I'm here.
Yeah, Deminder, or who will present this paper?
I'm Dylan.
Yes, I didn't hear your voice.
Sorry, I'm here. Can you hear me?
Okay. Please, now yours time now. Yes.
Sure, thank you. Yeah, so as you just said, I'm here to tell you about our paper on trains, games, and complexity. With my co-authors are listed here. So let me start by telling you about the arrival problem, which has had a decent amount of attention recently. So in the arrival problem, you're given a network of these switches, and there's a signal often described as a train, which will move deterministically through this network. It starts at this arrow here and follows the lines. Whenever it comes to one of these gadgets, the gadget will send it either up or down based on the current state, and that's indicated by which of these is the solid arrow. So the first time it'll come here, it'll go up, and when it does this, it toggles the state of the gadget. So it'll go up and leave that in the opposite state, then it'll go up through the next one. The next time it visits here, it goes down, and so on. So each of these switches alternates the direction the train goes each time the train arrives at that switch. Then it goes up here, and so on. And the question we're interested in asking is, where does the train eventually go? So as a decision problem, we can ask, does the train eventually reach this blue star? And that problem is called arrival. The path length can be exponentially long, so it's not obviously in P, but it's shown to be in NP, and in fact also in co-NP in 2017, and then more recently it's been shown to be in some smaller, somewhat more niche complexity classes. So in this work, we mostly don't think about arrival. We think about generalizations of this problem, where we replace this particular switch gadget with other kinds of gadget that behave in different and perhaps more complicated ways. And ultimately, what we would like to know is the complexity of the resulting decision problem as a function of the gadget. So the gadgets here are we call them input-output gadgets, because they have separate inputs and outputs, and the train will always enter an input and exit an output. So for gadgets that have just one input, here's a summary of our results. We consider the fully deterministic game, but we also consider a one-player game where there are choices a player gets to make, and the question is it possible to reach the target location? And also a two-player game where two players are competing. So we adapt the certificates used to show that arrival is an NP to show that the one-player game is still an NP for arbitrary single input gadgets. And we show that the two-player game is in exp time, fairly straightforward. Then we also show hardness. These hardness results adapt hardness from an earlier paper, which essentially used arbitrary single input-output gadgets, but we show hardness using just this one gadget that's used in arrival. So we show that the original arrival problem is NL hard, and the one-player and two-player versions are NP complete and P space hard. We also consider input-output gadgets with multiple inputs, which I'd like to tell you more about. So to make this more tractable, we focus on a restricted type of gadgets that satisfy all of these adjectives. So I told you what input-output means. Deterministic means that the state of the gadget and the final location of the train are completely determined by the initial state of the gadget and where the train arrives. So there are no choices involved. output disjoint means that inputs don't share outputs. So that implies that the gadget can be sort of factored into separate components, one for each input, which only interact by sharing state. Next, we're going to focus on two-state gadgets, and we'll call the states up and down. That means that the components are limited to these 5. So there are 2 different kinds of tunnel or line, which just affect the state of the gadget, but don't redirect the train. So there's a set up line, and of course it's mirror the set down line, which sets the state to up. The toggle line, which toggles the state between up and down every time the train crosses it. And then there are switches, which send the state either up or down based on the current state of the gadget. And then the setup switch and the toggle switch also affect the state of the gadget in the same way the setup and set line, or the setup line and toggle line do. So the toggle switch alone is the gadget we saw earlier that's the basis of arrival. But we can combine these components to get a gadget that has multiple of these components that share state and interact in more interesting ways that way. In fact, so our main result here is that we're able to characterize the complexity of the decision problem. Does the train eventually reach this location for all gadgets satisfying these properties? The way we do that is first we split the gadgets into 3 types based on boundedness. So there are trivial gadgets, which never change state or never do anything using the state. And those are in L, fairly straightforwardly. Then there are bounded gadgets, which can change the state from down to up, but once the state is up, it never changes back to down. That implies that the length of the path is polynomial, which puts the decision problem in P. And in fact, it's always P complete for gadgets satisfying all of those adjectives. And finally, there are unbounded gadgets where the state can switch both ways between up and down. We can get exponentially long paths, and the decision problem becomes naturally P-space complete. And in fact, it's P-space complete for all unbounded gadgets satisfying all of those conditions. And that's what I want to focus on. So that's infinitely many gadgets that we want to prove P-space hardness for. The first step is reducing it to just 6 gadgets. So we can show that any unbounded gadget that satisfies all of those other adjectives must simulate one of these 6 gadgets. And that's just by some simple casework on it must have one of the 3 types of switches, and it must have ways to set the state both up and down, and it reduces to a small number of cases. So it suffices then to prove that all 6 of the gadgets are P-space complete. I'm going to prove that this first one, the set up line, switch, and set down line, is P-space complete. So as a reminder of what this does, when the train enters this set up line, it will set the state or the switch to the up state. When the train crosses the set down line, it sets the switch to the down state. And when it enters the switch, it goes either up or down based on the current state. So the way we prove P-space completeness is by building gadgets out of this gadget. So the first tool we have is an edge duplicator, which we'll use to make a version of this gadget that has an extra set down line. And the way that works is the line we want to make a copy of is going to go here from X to X prime. And this makes 2 copies of it. So if the train enters A, it will set this to up, come around here, go across X to X prime, and then take the up branch because we just crossed the set up line. If it enters B, it will set this switch to down, also go across X to X prime, and then exit at B prime. So both A to A prime and B to B prime are copies of X to X prime. With that in hand, we're ready to start reduction from quantified Boolean formulas. So the first component here is the universal quantifier, which works something like this. When the train enters in, it will set these switches. There was one of these for each instance of the variable this quantifier is quantifying over. For each instance of that variable in the formula, we have a copy of this switch. And it's going to set all of them to this left state. And then go to out, where it will then move to the next quantifier and essentially query that quantifier for, are you true with this setting of the variable? Eventually, that quantifier responds either true or false. If it responds false, then, well, then this quantifier should also respond false. So it does that after resetting some internal state. If the response is true, we need to check the other setting of the variable. So the train is going to come around here, set some internal state to remember that we had one true response, and then set the variable, try the other settings of the variable. So previously it set the variable to true. Now it sets all of these to the right state, which represents the variable being false. And it queries the next quantifier again. If the response is true a second time, this time it will take the top branch, reset that state, and then return true. So in summary, when this gets the signal to in, it will test the variable with true, test the variable false if needed, and if both responses are true, it will output true. If either response was false, it will output false. That's exactly what a universal quantifier should do. An existential quantifier is exactly the same, except we swap true and false, because that's how existential quantifiers work. The very last quantifier in sequence, instead of communicating with another quantifier, it will communicate with the formula evaluation. And the way that works is it's going to use these switches, which encode the current setting of all the variables, to evaluate our CNF formula. So the innermost part of the quantified formula is in CNF, meaning it's an and of clauses where each clause is an or of literals. And what we need to do is check if every clause has at least one true literal. And that's what this does. So each row here represents a clause. When the train enters in, it will go through these three switches, which represent the states of some literals. If any of them is set to true, it'll take the top branch and move to the next clause. Otherwise, it will go to the false outline. So in the end, if at least one literal is true in every clause, it will make its way all the way up and eventually exit true out. Otherwise, it will exit false out. So that that reports the truth of the CNF formula, the unquantified formula. The entire QBF formula is a series of quantifiers gadgets ending with this. And when the signal enters in on the very first quantifier, it will eventually exit true or false on the very first quantifier, telling us the truth value of the entire formula. So that's the piece-based hardness proof for that one gadget, the switch set up, set down. What about the other 5 that we need to prove that all infinitely many are piece-based complete? I'll show you one more, because this is interestingly different. We aren't going to do a fresh piece-based hardness reduction from QBF. Instead, we're going to simulate the switch setup, set down. And since we know that one's piece-based hard, this other gadget is piece-based hard. So I'll demonstrate how to simulate the switch setup, set down using this gadget, the toggle plus toggle switch. As a reminder, the toggle line just flips the state when it gets crossed. The toggle switch is the gadget in arrival, which sends the train to one of 2 exits and flips the state. So the first step will be to simulate this gadget, which has 2 toggle switches. And we do that with this image here. So the blue and the red each become 1 toggle switch. When the train comes through either path here, it goes through both of these gadgets. And so they're always kept in sync with each other. Once we have a toggle switch, we can make an edge duplicator, which works in a pretty similar way to the edge duplicator we saw earlier, where the train can enter either of these paths, and then it will exit the corresponding path here after traversing this edge once. So that lets us make copies of the toggle line on our gadget, which has a toggle line and a toggle switch. So we can build this gadget, which is just a whole bunch of copies of the toggle line plus the toggle switch. And by putting 3 of these sorts of things in series like this, we can make something with several toggles and several switches, or several toggle switches. So each red line here is just a toggle. Each blue line, which forks, is a toggle switch. So this gadget that we're simulating here has 3 toggle lines and 3 toggle switches. And once we have that, we can simulate the switch set up, set down like this. So each pair of a toggle line and a toggle switch becomes one of the 3 components. The idea for the set up line here is if the state is currently up, we will flip the state twice. If it's currently down, we'll flip it once. Either way, the state ends up up. Similarly for the set down line, and the switch just always toggles the state twice. So we've simulated the switch set up, set down using the toggle switch toggle. And that implies that the toggle switch toggle is also p-space complete. We can do this for the other 4 gadgets I showed earlier. And that proves that every unbounded gadget satisfying all of those adjectives is p-space complete. So that's sort of the main result. But one other place we can go with this is we can simulate more gadgets using the switch set up, set down. So in fact, this gadget simulates every deterministic input-output gadget, even dropping all of those other adjectives. And the way we do that, very briefly, is first we make it so it has more states and more set lines. So this is essentially a whole bunch of lines that can set to various states and one switch that just branches to all of the different paths depending on the state. So this is what that looks like with a 4-state version. Then we can combine several of those like this to make something with the same gadget, but with multiple copies of this switch. So this has one set line for each state. Though we also know how to duplicate set lines, of course, so we can have as many set lines as we'd like for each state, and as many switches as we want, which go to a separate location based on the state. And from there, it's pretty easy to simulate any particular deterministic input-output gadget just by hooking up these tunnels in the appropriate way, based on the gadget we want to simulate. So I'll end with a couple of applications of this. So we can use this work to fairly easily show other systems p-space complete. So in the video game Factorio, there's trained networks that behave basically deterministically. And in a game called The Sequence, this red thing will move around and follow some deterministic rules. And both of those we can build this setup line, switch, and set down line. So they're both p-space complete. Again, in Factorio, using the conveyor belt system, which just moves items around, we can show it's p-space complete to determine whether an item will eventually reach some location. And we do that by building this gadget. This is the 2 toggle switches, which we saw as an intermediate earlier. And because of some mechanics changes, you actually need a different construction in 2 different versions, but both of them, it is p-space complete. Yeah, that's it. So any questions?
Thank you very much, Dylan. It's very nice talk. Audience, do you have any question to Dylan? We have 3 minutes discussion. Again, we invite you to have some discussions. Do you have any question to Dylan? And if not, then we close this session. Again, I say thanks to Dylan for the nice presentation and to other co-authors, and also for the first presenters, second and the third presenters. And according to our schedule or program schedule, then we close the fourth session, and then we will have a tea break from your home. Yeah, of course. Yeah. Okay, so thank you, Dylan, and thank you for other presenters, and thank you for all audience. And we have 20 minutes breaks, tea break, and after that we will continue for the fifth session. Thank you very much for me, and that's it for all. And good a day for all. Yes, thank you very much.
Okay, now at 10 past 40 ETC plus 7. Now we're going to the next agenda. Yeah, the next agenda is about the contributed talk session 5, with the topic is online and property testing. And at this session will be led by Mr. Ming Yu Xiao. For Mr. Ming Yu Xiao, time is yours.
Yes, I'm here. Shall we start? Okay. Yeah. In this session, we will have 2 talks. The first one is given by Nado Bashati. The title is an optimal test for key linear. Please share your screen. Okay.
Oh, just a minute. Can you hear me?
Yes, we can hear you.
Okay. 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 So can I start?
Yes, please.
Okay. Okay, so this is an optimal testing for K-linear. And let me explain first what is the title. So what is K-linear? So we have a Boolean function from 0, 1 to the n to 0, 1. That is a function that depends on n Boolean variables. And K-linear is a class of Boolean function that is the XOR of exactly K variables. Exactly K variables. So XOR same like sum in the binary field. Okay. This is a class of K-linear, and we also define the class less equal K-linear, the sum of up to K variables. So here in this class, the number of variables is exactly K, where here in this class, it is the sum of up to K variables. So those are the classes we will study. And let me now explain what is tester. So a tester is an algorithm that has access to a Boolean function, any Boolean function. So f can be any Boolean function. The tester cannot see the function, but can ask the black box queries. So one query is black box query, where the tester can ask what is the value in some point, and the black box return the value of the function in this point. So the tester can only ask the value of the function, but cannot see the function. Now, with the function, there is also a distribution over the domain of the function. So the tester also has access to query for this distribution, which is called example query. And the black box return an example according to this distribution. So the tester can only access black box, cannot see the function, cannot see the distribution, can see only the value of the function and some example of an instance in this distribution. And now this is the class of K-linear. The tester needs to distinguish between functions that are K-linear and functions that are epsilon far from K-linear. Now, by epsilon far, we mean that we say that H is epsilon far from F if with the probability of F not equal to H is greater or equal epsilon with respect to this distribution. Now, F is epsilon far from the class if it is epsilon far from every function in the class. So the tester needs to distinguish between functions that are in the class, so accept functions that are in the class and reject functions that are epsilon far from the class. Now there's two type of tester, two-sided tester. So in two-sided tester, the tester accept with probability at least 2/3 if F is in the class and reject with probability at 2/3. Where in the one-sided tester, if F is the class, the tester need to accept with high probability. And we will also distinguish between adaptive and non-adaptive tester. So in adaptive tester, queries can depend on the answer of previous queries, where in non-adaptive tester, queries are independent. So we can ask all the queries in one step. Okay, so this is the model of testing, and what is optimal? Of course, we need an algorithm that runs in polynomial time, but optimal in the number of queries. So we want the query complexity to be optimal. So basically, after I define all this, what I'm doing is giving an optimal tester, optimal algorithm that distinguish between functions that are k-linear and functions that are epsilon far from k-linear. So this is the area of property testing. And now in property testing, almost all the results deal with uniform tester, which means that the distribution is uniform. In that case, we say that the tester, we just say tester, but when we say distribution-free tester, then the tester works under any distribution. So this probability, even if the tester doesn't know the distribution, it still can distinguish between F that is in the class and F that is epsilon far with respect to distribution D from the class. Okay, so some results. Saglam in Fox 2018 show a lower bound of omega k log k. So we cannot test this class with less than k log k queries. And my work with Goldreich this year shows that almost all classes cannot be tested with less than 1 over epsilon. So the lower bound is omega k log k plus 1 over epsilon. So it results from the literature. There's many papers on this, on testing this class. So what I will present here is non-adaptive tester, two-sided, distribution-free, and optimal. So it achieves the same number of queries. Previous results are either adaptive or only work under uniform distribution, or only and not optimal. So we get those three: non-adaptive, distribution-free, and optimal tester. Okay, so let me now explain the. I'll first give a one-sided tester for less equal k linear. Again, less equal k linear is sum of up to k variables. Okay, and one-sided means if f is a class, then the tester accepts with probability 1. So the algorithm goes like this. We first run the Blum-Rubinfeld algorithm, BLR algorithm, that distinguish between linear function and functions that are far from linear, and it's over the uniform distribution. So if f is linear function, then the algorithm, BLR algorithm accept, and if f is epsilon far from linear, then with probability at least 2/3 it reject. So this is the first algorithm we run, and the algorithm is very simple. It just chooses random uniform x, y, and test whether fx plus y equal fx plus fy for this many points. Okay? And our epsilon will be 1/theta k log k. I'll explain later why. We run this algorithm, and of course, the class I'm considering here is subset of linear. So linear is a XOR of any number of variables, and less equal k. Linear is a XOR of up to k variables. So it's a subclass. So if f is epsilon far from linear, it is also epsilon far from less k linear. So if this algorithm reject, then the algorithm, my algorithm will reject. After this test, we may assume that f is close to linear. Because if it is far, then it rejects. So now I consider the function that is linear, g, the closest function to f, okay? And there is a known technique in the literature called self-corrector. Using self-corrector, instead of querying f, we can query g instead, okay? So now I can assume that the function in the black box is a linear function and not f, which is the closest linear function to the function in the black box. And self-corrector is a very simple algorithm. It's just compute fx plus a plus f of a for a random a. Since f of x plus a is random, so f of x plus a is close to g, and f of a is close to g, and since g is linear, gx plus a plus g of a will be g of x. So g of x equal to this with high probability. Okay, so this is called self-corrector, and now I can query g and not f, which is a linear function. And now I want to distinguish between any linear function and linear functions that depends on at most k variables. Okay, so this explains what I said, and now I want to distinguish between linear function and functions that depend on at most k variables. So first, I distinguish between linear function and functions that depend on at most 8k variables, and later I'll restrict that more. Okay, so of course, if the less equal k linear is subset of less equal 8k linear. Okay, so if a function has less than equal 8k variables, and if it has less than k variables, then it has less equal 8k variables. So how do I distinguish between linear and less equal 8k linear? So what I do, I take the function g that I can query now, and I map uniformly at random the variables to 16k variables. Now what happens if the function is less equal k linear? When I map this function to 16k variables, then the functions that I get depend on less equal k variables. But when the function has 18k variables, because the function by this class has at least 8k variables, then with high probability, the number of variables that this function depends, it depends on more than k variables. So I find the number of variables. It's easy to find the number of variables when the function is XOR. And if the number of variables of the function is less equal k, then I accept. And if it is more than 8k, I reject. So this is also one-sided, because if the function has less equal k variables, then the projected function also has less equal k. So now I can assume that my function has less equal k variables, and I want to test if it has less equal k variables. So now I take another projection, and this time I project the variables to order k square variables, and then after I project it, I exactly learn the function. Okay, I use a learning algorithm, not very well known learning algorithm, that learns the function exactly. So now what happened? If the function contain at most k variables, when I project the variables to order k square variables with high probability, different variables mapped into different y variables. So when I learn this function, the projected function, I will find exactly the number of variables. So if the number of variables less equal k, then I accept. If it is more than k, I reject. So this is basically the algorithm. It is one-sided because when G contain less equal k variables, then when I project k variables here to order k square variables, then this function also depends on at most k variables. Okay, so this is the result. I showed, well, there's many detail in the algorithm, of course, that if f is less equal k linear, if it is XOR function that depend on less equal k variables, then the algorithm accepts with probability 1. And if f is epsilon far from this class, then it rejects with probability at least 2/3. So this is the result. The algorithm is one-sided, which means it accepts with probability 1 when we have this. It's non-adaptive, and it runs in a minimal number of queries. Okay, so this is not the class I want to test. I want to test the class k-linear. The same algorithm, exactly the same algorithm, is also non-adaptive, also optimal, but it is two-sided. And why it is two-sided and not one-sided? The reason is when I project the last stage of the algorithm, when I project the variables to order k square variables, if G depend on exactly k variables, I cannot guarantee that this projection with probability 1 is projected to exactly k variables. So the k variables that G depend on may not project with high probability only. It project to k different variables, but not with probability 1. This is why when the function has exactly k variables, the algorithm is two-sided and not one-sided. We cannot guarantee that the projection give the function with exactly k. When f is depend on less equal k variables, then the projection will give a function with less equal k variables. So it is two-sided. So I ask the question, what happened when it is one-sided? And I show a lower bound in the paper using coding theory, that if the function, if we're looking for algorithm that is one-sided, then the lower bound is omega k log n plus 1 over epsilon, not log k. And in property testing, we assume that n is huge, it's very large number. It's much larger than k, so we cannot find an efficient algorithm for this problem. And there is also an upper bound, so this is tight also. Okay, what about adaptive? Because finding algorithms that is adaptive is much easier than non-adaptive. Again, a non-adaptive, you have to ask all the question, get the answer, and then decide. Where in adaptive, you can ask the question, and then the next question can depend on the answer of the previous question. So also in this case, we prove a lower bound of square root of k log n, so it depends on n plus 1 over epsilon. The upper bound here is the same like this, so there is still a gap in the lower bound and the upper bound. So this is basically the result I have. You can read, of course, the result, the lower bound in the paper.
Thank you. Thank you, Ned, for the nice talk. Are there any questions? We can have a short question. There's not too many time left now.
Okay, how do I stop the sharing?
Any question? If no question, then we thank the speaker again. And then the next talk should be machine learning, advanced skin ratio problem with the discount. The speaker is Afia Bhattacharya. Afia?
Hello.
Yeah. Please.
Hello, everyone.
Screen. Please share your screen. Yeah. Yeah, we can see. Yeah.
Awesome. Thank you. Thanks for confirming. Hello, everyone. Welcome to WALCOM 2022. My name is Argho Bhattacharya. I am going to present our paper, ML Advised Ski Rental Problem with Discount. This is going to be our roadmap for this talk. I'm first going to talk about what is ML Augmented Online Algorithm. What is the augmentation? Why do we choose ML or machine learning? And how do we augment online algorithms? Then I will move on to the traditional ski rental problem, which is pretty popular in computer science. Then I will talk about the ski rental problem with a discount that this paper works on. And finally, I will talk about the algorithm design principles and their benefits. So let's first talk about the first topic, which is the ML augmented online algorithm. And before going there, I just briefly want to introduce what are the online decision-making problems. So the scenario is like the following. There's an adversary that decides the input sequence. The conventional online algorithm that makes some irrevocable decisions without any futuristic knowledge about the input sequence or the inputs. We compare the performance of the online algorithm relative to the optimal offline algorithm, which we also call OPT. By the way, the OPT or the offline algorithm that can see the future inputs, that is what we are comparing with. And we define competitive ratio, which is basically the relative performance of the online algorithm to the OPT or the offline optimum. Our objective of designing online algorithms is to design an algorithm with minimum competitive ratio. So in other words, less the competitive ratio, better the algorithm is. Now, I want to briefly talk about some of the disadvantages that online algorithms in general have. Firstly, I would say it's a pessimistic study. The reason being, we put too much focus on some bad inputs, and because of that, we may result in poor performance on supposedly easy inputs. What I mean is that we don't study those particular bad inputs, how rarely they appear or how likely they are to appear. And our design principle and strategies, they kind of revolve around those bad inputs. And that's why we miss out on opportunities where we could do better on easy inputs or average case inputs. And secondly, interestingly, we do not make any observations or assumptions on the input sequence or the inputs or the past inputs. Interestingly, machine learning it stands out because it just does two opposite things in these 2 points. Machine learning does not put too much focus on particularly some bad worst case inputs. And secondly, there's a very popular structure in the study where it tries to look into the past and find some pattern in the past inputs and tries to predict the future. Hence, what happens is that in a simulation with some fairly reasonable real-world data set, the conventional algorithm may perform worse on average case inputs than the ML algorithm, which, by the way, does not give you any performance guarantees for those worst case, particularly worst case inputs. Some researchers, that's why they thought fairly recently in the last 5 years that can we kind of take advantage of both the worlds? In other words, can we have some machine learning advice or some machine learning advisors or oracles available to the online algorithms, and these oracles will advise some values or patterns to the online algorithm. The online algorithm may take it or may not take it. The advantage that they observed by doing that is that firstly, there's a good average case performance that the online algorithms were missing out. And secondly, because we stick to the our basic structure of those online algorithms or our basic structure of the competitive analysis, we have a bounded performance for the bad inputs, which we required, by the way, and which is not easily available or popularly available in case of machine learning studies. So the machine learning augmented online algorithm, what it brings on table is that it kind of brings out the best from both the worlds. It has been applied to several online algorithms, such as competitive paging, job scheduling, membership query data structures, such as Bloom filters, index data structures, and so on. So now we want to talk about the second point in this presentation, which is the traditional ski rental problem. By the way, this is a very popular problem, which also comes under the online algorithm design problems. To briefly introduce the problem, here's a scenario where a skier makes an irrevocable decision at the start of every day. He only has 2 choices. He has to optimize between these 2 choices. One is he can rent the ski at a unit price every day. And the second choice is he can buy the ski with a higher price and ski for free from then onwards. Now, there is a source of uncertainty here. The skier does not know in advance the length of the ski session. In other words, when it does not snow anymore, then only the skier knows that the skiing session has come to an end. So this is the uncertainty in this problem. This is basically a canonical example of rent or buy types problems, where you have to decide either to rent or to buy, or when to buy. This sort of problems, this is an example of that. Now, let me introduce the ski rental problem with a discount that this paper proposes. And for that, let me first tell you the motivation of this problem. It is definitely an application of the ski rental problem to a larger set of rent or buy problems. Let me give you an example first. So let's say there is a return on investment for a market. And the return, interestingly, varies with respect to time, as is happening in this picture. Let's say the market of percentage of market return is 2% for the first 4 days, and from the 5th day onwards, it is 1%. It's a very easy function that's happening in the percentage of market return with respect to days. Now, the skier invests the rent that he has not spent yet, and hence gets a return on that investment. So the effective rent, if we plot that, which is the next plot, that is necessarily the rent that he actually pays, which is constant, by the way, minus the rent that the discount that he gets, or here the market return that he gets. And because this is a variable, the return, the effective rent, this function becomes a variable which is definitely decreasing with time, as is happening on this plot. The problem necessarily tries to simulate the net present value of the resource. Here the resource is the ski. More formally, the ski rental problem with a discount, it has, so X is the actual number of usage, which is there in the problem. B is the price of the ski. We assume a rent function, we define a rent function, which is basically, let's say, rent of I, that means rent of the ski for ith day. And another presentation is rent X through Y. That expression is basically a sum of rents from the day X to day Y. And this function is expressed as an arbitrary non-increasing function. In other words, rent of I plus 1th day is either equal to or less than rent on ith day. That is how the function is designed. Now, let us first understand what the optimal offline algorithm, or which we call OPT, that is going to do. By the way, OPT is visionary, so it can see in future. That means it is aware of the value of X, the value of B, and the rent function. We define a quantity, which is TB. The TB value denotes if you sum the rents from the first day, to the TBth day, it is going to be more than B. B is the price of the ski. And if you exclude the rent of the last day, TBth day, it is going to be, the sum is going to be less than B. Now, what OPT does, if your X, which is known to the OPT, it is more than TB, greater than TB, then it buys the ski on the first day. And if it's less than TB, it keeps on renting the ski. The cost that OPT incurs, it's a minimum of two quantities, which is the rent from 1 through X, and B. B is the price of the ski, and X is the actual number, how many days it snows. So what OPT performs, how OPT performs, that is the best, because it can see the future inputs, and that's why its decision is based on what is going to be happening in the future. Now, let us come to the final point, which is the algorithm design principles under this uncertain situation. First, we will try to see what happens in the break-even algorithm. This is the best deterministic strategy that we can use. The design is almost the same as the as what happens in the traditional problem. We just need to tweak a little bit. Basically, the strategy is like this: rent the ski until TB minus 1th day and buy the ski on the TBth day. The cost that we incur, this algorithm incurs, if we present that, express that as break even, is going to be less than 2 times OPT. That means the break even algorithm is too competitive. Now let us see what happens with ML augmentation. Necessarily what we do in ML augmentation, there is an ML oracle, just like in this picture, which has as input all the past X's, and it predicts a quantity Y. Now, in this method, firstly, what we do, we have a complete trust on the ML oracle. In other words, Y is kind of our proxy for X. We completely believe in the Y value that we have from the ML oracle. That means if Y is greater than B, TB, we buy on the first day, and if it is less than TB, we keep renting. Now, interestingly, if we have a really good prediction, that means we have a chance that we are doing exactly the same that the optimal offline algorithm is doing. In other words, we are one competitive, or we are necessarily as good as OPT. If we express the cost though, because the prediction may not be as good as we expect, the cost is going to be maximum of OPT times eta minus 1, where eta is the prediction error, and OPT plus R times eta, which is a function of eta. R is a constant, which is the rent on the first day. That means as the ML predictor fails to provide quality prediction, the performance degrades harshly. And not only that, we do not have a bound on how much it can degrade from the ideal value or what we want. That means we needed to have a better algorithm than this one. So what the next algorithm does, it's ML augmented algorithm with a trust parameter. So necessarily we introduce a trust parameter in this algorithm. So the trust parameter is nothing but a sort of knob or a tuner where you can choose that how much trust you have on the ML advice. The way it works, let's say the same prediction Y, if it's greater than TB, instead of buying on the first day, you buy on the lambda TBth day. What is lambda? Lambda is the trust parameter you set, which lies from 0 to 1. That means lambda TB is less than TB but greater than 1. Similarly, if Y is less than TB, you buy the ski on the TB over lambda day, which is greater than TB because lambda is less than 1. So you do not have a complete trust on the oracle, but you use the information you get from the oracle. Let's see how much cost we incur by doing that. If we denote that cost by the quantity trust, it's basically a minimum of OPT times 1 minus 1 over lambda. Lambda is the trust parameter itself, and OPT plus a function of eta and lambda. That means so even if the oracle fails to provide quality prediction, the performance does not degrade harshly, and see the cost that we pay, that is bounded for worst case. So let us still try to understand what this lambda is doing. Necessarily, when lambda tends to 1, what we express here is basically very less trust in the ML advice that we have. And when lambda tends to 0, you have a very high trust in the ML advice. For some value in between, let's say lambda is 0.5, the trust, the cost of this algorithm is less than 3 times OPT, which means, in other words, for 50% trust in the ML oracle, the algorithm is 3 competitive. Now, in the next scenario, it's another interesting thing. What if we have 2 advisors? Instead of 1 advice, if we have 2 advices, which is Y1 and Y2. Now, another layer of uncertainty is there, which advice to take or which advice to go for. I want to add an interesting situation here. Let's say one of the predictions is correct, and the skier does not know though which one is correct. So which one to trust? Do we go randomly trust one and see what happens? So instead of that, what we suggest that to tweak the algorithm in this way. Firstly, if Y1 and Y2 both are less than TB, it is obvious we will keep renting because one of them is correct. And if both of them are greater than TB, we buy on the first day again because one of them is correct. So the OPT will do the exact same action. What happens in this scenario, which is, Y1 is greater than TB and Y2 is less than TB. Here we define another quantity, which is T phi. What is T phi? Phi is firstly the golden ratio, which is very close to 1.6. So rent of 1 through T phi, the way we define T phi, the rent 1 through T phi, it's basically greater than phi minus 1 times B. B is the price of the ski. And if we exclude the cost of the T phith day, rent of the T phith day, that is going to be less than phi minus 1 times B. If Y2 is less than T phi, we rent for Y2 days and buy next day. If it is more than T phi, we rent on the we buy on the first day. Yes. The cost that we incur, and the last thing is if Y2 is even more than TB, we buy on the first day. The cost that we incur if we express that by this quantity multiple, that is going to be interestingly 5 times OPT. So there is nothing related to eta, which is the error of the other advisor, which is not correct, the incorrect advisor. Phi is a constant, which is the golden ratio. In other words, the augmented algorithm with 2 advisors performs better than even the break-even algorithm that we had. But what if we have 2 erroneous advisors? That means both the advisors are incorrect and the errors are non-zero. That means y1 and y2, none of that is correct or equals to x, in other words. Here, with an assumption that y1 is greater than y2, if y2 is less than t phi, we rent for y2 days and buy next day. And if y2 is greater than t phi, we buy on the first day. And if y2 is greater than tb, we buy on the first day the same way. Interestingly, there is nothing related to y1 in this strategy. We only consider ourselves with the prediction which is less than the other one. So y1 is greater than equal to y2 in this scenario. What is the cost that we incur here? This cost is also bounded. It is the max of OPT over phi minus 1 r eta over b. B is the price of the ski and r is the rent of on the first day. So in other words, the highest rent that the skier is paying. And the other quantity is phi plus 1 times OPT. That means necessarily the performance of the augmented algorithm with 2 erroneous advisors is bounded by either the error in prediction or the golden ratio. In other words, by eta or phi. Phi is a constant here. That means the prediction, even with both erroneous prediction, we have a bounded performance for the worst case inputs. So basically what we showed here in this paper, it's necessarily a new algorithm design recipe. There's a huge scope of empirical advantage for a large class of online algorithms, such as ski rental problem. There are like different classes of online algorithms where we can have a huge empirical advantage. Although by having or with having along with a bounded performance for the worst case inputs, while having the empirical advantage on the average case. We showed that this is there is a large class of rent or buy problems where this is applicable, and we can use single or multiple advice in order to get this advantage. Here I would like to conclude my talk. Thank you so much for being here. Please ask me questions either here or offline. I'll be happy to answer.
Thank you. Thank you to speak. Are there any questions? If not, then maybe you can ask the author late. This is the end of session 5. Next will be the time for lunch. Thank you. Thank you all for attending.
Thank you, Mingyu. Thank you, everyone.
Okay, thank you, Mr. Mingyu Xiao. And now we are at the end of the 5th session. Sorry. Based on the agenda, we are on the lunch break and Friday praying, and we will the meeting will start again at 12:30 UTC +7. Okay, thank you very much. Hello, Mr. Chen.
Yes.
Still,
Good. Thank you.
we are about waiting for 8 minutes again to start next session.
Yeah. This is fine. I just got up and got connected to chair the next session. So I'm making sure that you can hear me and I can hear you.
Okay. Okay, I think we can start it because it was near 12 past 30. So at this, based on the agenda, we are on the contributor talk session 6 with the topic is about parameterized complexity 1. At this section, at this session, it will be led by Mr. Jan Kratoxville. For Mr. Jan Kratoxville, time is yours.
Thank you. Thank you. Welcome, everybody. In this early morning time, for those who are in Europe like myself. As I understand, the first talk should be given by Ajinkya Gaikwad. Is it right? Now, Theo, we cannot hear you. You muted yourself.
Okay. I think the first speaker is Mr. Soman Meiti.
Soman Meiti, I don't see him among the present participants right now. Soman, are you here? Do we have the speaker for the first talk, for the talk on the harmless set problem parameterized by Trivets, co-authored by Ajinkya Gaikwad and Soman Meiti? Do we have one of the presenters, or do we have the presenter here?
Sorry, I think I can find Mr. Ajinkya and Soman. Sorry.
Ajinkya was connected, but disappeared from the list of participants. This may mean that there are some technical problems on the side of these two co-authors. And if they simply are not ready to present their talk, then we have a 20-minute waiting time for the next talk. I don't want to shift the talks because there might be people who are coming to watch at the specific time, if you agree with me. So once more, if they do not reconnect quickly, we will be waiting for the next talk, which should be given by Denis Agogo. Is a talk of Denis and Petr Hliněný. I see at least Petr Hliněný is here already. So the next talk will be at 12:50 of Indonesian time, 6:50 of European time. And it will be about isomorphism testing for T-graphs in FPT, but it will start in 18 minutes.
Jan, may I ask a question? Can I
Yes,
use
please.
this 18 minutes to try to how it works with sharing my screen? Just for a brief testing whether.
Certainly, Hans, if
Hi, this is
reappear, then we could still squeeze. We still have something like 17 minutes. So if they reconnect, they would have 15 minutes for the talk. So if
so this is Soumen Maiti speaking.
okay.
So is that our talk is now? So
Your talk was supposed to start 3 minutes ago.
okay, so somehow that's okay. So can I start now then?
You can start now,
Okay.
but you have to be a little bit briefer than the original.
Okay, sure. Yeah. Okay.
So sorry, Hans. Once the authors appeared, it is their time slot. So once more, it's a talk on the harmless set problem parameterized by trivets, co-authored by Ajinkya Gaikwad and Soumen Maiti, and Soumen Maiti is giving the talk. Please.
Okay, so I'm sharing my screen. So can you see my screen?
I can.
Yeah. Okay, thank you. Good morning. We'll talk about the harmless set problem. This is a joint work with Ajinkya, and I'm Soumen Maiti, and we are from Indian Institute of Science, Education and Research, Pune. So I'll start with the definition of target set, which is introduced by Chen in 2009. So input to this problem is a graph where every vertex V has a threshold value, TV, and an integer K. And the following propagation rule that a vertex becomes active if at least TV neighbors of V are active. Okay, so the question here is there a set of at most K vertices called a target set such that all vertices of the input graph becomes active. So I'll use an example to illustrate this definition of target set. So suppose this is my graph, and as I said that every vertex has a threshold value. So these are the threshold value you can see here. And we know the propagation rule. If for a vertex becomes active if at least TV neighbors of V are active. So we'll see in the first iteration, this vertex, which has threshold value 3, will become active because, so this is my target set in this graph because they're all active and it has 3 threshold value and 3 of its neighbor are active. So this will become active. In the second iteration, this vertex, which has threshold value 2, will become active because 2 of its neighbor are active. In the third iteration, this will become active. It has threshold value 2, and 2 of its neighbor are active now. And finally, in the fourth iteration, this will become active. Okay, so this is what the target set problem. And the application, this viral marketing, the task for a company would be to convince a few but influential individual such that by word of mouth process, a large fraction of customer is convinced about the usefulness of a product. So this set of influential individuals is basically the set, the target set.
if the individuals in the target set, they are influenced by something, then they will help to influence all other people. Okay, so this is what the target set is. And then in 2014, WALCOM and Chopin, they introduced opposite problem called harmless set problem. So here, for this problem also, the input to the problem is the same. You are given a graph and a threshold value t for each node. And here, the question, is there a set of at least k vertices with this is called a harmless set, such that every vertex V has less than TV neighbors in S. Okay, so the harmless set problem, that was a minimization problem, but here the target set problem was a minimization problem, but harmless set problem is a maximization problem. So we want to find bigger set such that still outside this set, no vertex will be activated. Okay, so the harmless set consists of set S of vertices with the property that no propagation occurs if any subset of set S gets activated. So here you can see that this is almost the same example, but one edge is missing. So this 2, 3 edge was there before, but it is now not there now. So you can see that this will not activate it because strictly less than 3 neighbors are activated only. So this will not activate it, and similarly, this will not be activated. This node will not be activated. So this is how no propagation occurred here in this network, and this is the largest set possible for this social network, you can say. Okay, so now what is known about this harmless set problem is that this harmless set problem is W2 complete on bipartite graph with respect to the solution size. And this problem is W1 hard even on bipartite graph with majority threshold. So I didn't say what is majority threshold. It's like, and the threshold value is half of its degree, and I mean the number of neighbors by 2. That's the majority threshold. Okay, so these two results are known in terms of the parameterized complexity. What we did here is that we proved that this problem is FPT when on planar graphs when parameterized by the solution size. And also we proved that this problem is FPT parameterized by neighborhood diversity on any graph. And also we proved that this problem is W1 hard parameterized by tree width for majority threshold. So I'll talk about these two positive results only. Okay, so before I go to design an FPT algorithm for this problem, so I'll just talk about what is parameterized complexity. It's instead of expressing the running time in terms of input size here, the running time is expressed in terms of n and k, where n is the input size and k is some parameter that could be the solution size, and that could be some that could be maximum degree or some structural parameter like neighborhood diversity or tree width or click width. So just an example, we know that vertex cover problem, which is the classical complexity, is the NP complete problem, but we have a parameterized algorithm for vertex cover problem, or time complexity, say order 2 to the power of k n square. And so you can see that this is polynomial or quadratic in input size n, but into a function of k. This could be any computable function. So if we have a time complexity of this form, then this is the algorithm is said to be in the it's a fixed parameter tractable. Whereas for the maximum click problem, we don't have an FPT algorithm for this one. So, and this problem, the maximum click problem, is W1 hard, and probably it's not APT problem. So for max click problem, we have complexity of the form n to the power of k. Okay, so now we move on to our designing APT algorithm for harmless set problem on planar graph. So first what we do is that we do reduction. What we do is that we color the vertices of G with two colors, red and green. So a vertex is assigned color red if it has a neighbor with threshold value 1. Okay, so why this is so? Because if suppose a vertex it has a neighbor, this has a neighbor which is of threshold value 1. So if this goes to the solution, then this will become active, right? So that's we don't want any propagation. So what we do is that if a vertex has a neighbor with threshold value 1, then we put color red, and that means the red vertex is not going to be in the solution. So this is the first reduction. And then what we do is that, if there is a vertex, red vertex, whose all the neighbors are red, we can easily delete that vertex from the graph. So that is what the first reduction is, that if a vertex V and all its neighbors are color red, then delete V from G. And the new instance is G minus V, the same parameter, solution size K. And that means if I have this graph, then I'll delete this vertex from the graph. So this is reduction 1, and then reduction 2 is important to design an APT algorithm for our problem. So it says that if the diameter of G is more than or equal to 6K, where K is the solution size, then we conclude that we are dealing with the ES instance. That means we have a harmless set of size K. Okay, so why this is true? That means if the diameter is greater than or equal to 6K, we are done. And if it is strictly less than 6K, then we know that the tree width of the graph, since it's a planar graph, the tree width of this graph will be bounded by 3 times 6K, that's in 18K. And that is what we use to design our APT algorithm. So here I'll just explain why this is true, why this reduction rule 2 is safe. Let me consider K equal to 2. So that means suppose the diameter of the graph is 12, and that means there is a path of length 12 in my graph. And suppose this is the path between V0 and V12. And then what we do is that we just pick the vertices of say V0, and then we look at V6 and then V12. So if V0 is green, then we pick that vertex in our solution. And if this vertex is red, then what we know is that every red vertex has at least one green neighbor. So that is from the reduction rule 1. So we pick one of its green neighbor. And similarly for this one also, if it is green, then we'll pick that, or if it is not green, then I know that it has a green neighbor. So we'll pick these vertices in our solution, like the vertices which are in the circle. And now we can sort of see that why they will form a harmless set. Clearly, threshold, this construction will satisfy, I mean, if a vertex has threshold value 1, so that will satisfy the threshold condition because of the first reduction. Now, suppose a vertex has threshold larger than or equal to 2, then what we are saying that this vertex can't have 2 neighbors in the solution, because if it has 2 neighbors in the solution, then you can see that we have a smaller length path, and that will contradict the distance property for the definition of diameter. So the diameter will be less than 6K, right? So so that's why if the diameter of the graph is more than or equal to 6K, then we know that we are dealing with the S instance. And so we can assume that the diameter of the graph is less than 6K.
2 minutes left.
Okay, so the tree width of a graph is how the tree-like the graph is, and then we can represent this graph by a tree-like structure. And what we know about this for the planar graph, that if G is a planar graph with diameter at most 6K, then the tree width is at most 18K. And once we know that tree width is bounded by 18K, then we can use dynamic programming technique to get an algorithm of this time complexity. So this is FPT algorithm with respect for the planar graph, and then we have one FPT algorithm.
No time to show the rest.
Okay, yeah, so I'll just skip this one, right? With respect to the neighborhood diversity, that is using we reduce this problem to ILP, and we sort of maximize some problem. So we know that, and what we do is that the number of variables in the ILP is the neighborhood diversity of the graph, and we know that any ILP can be solved in FPT time, FPT in the number of variables, and here the number of variables is the neighborhood diversity. So from there we conclude that for this problem there is a FPT algorithm with respect to the neighborhood diversity of the graph. And that's all. And then we have this proof in the paper that the problem is W1 hard parameterized by tree width for the majority threshold, and we have recently some other results also. And what we did is that
thank you so much, but your time is up.
Okay.
Thank you.
Thank
you for the talk.
Thank you.
Unfortunately, no time for questions. I encourage the participants that have some questions to contact you personally.
Okay, sure. Thank you so much.
Thank you. Please stop sharing your screen. And the next talk is given by Dennis Agaoglu, and it's about isomorphism testing for T-graphs in FPT, co-authored by Petr Hliněný. Dennis, are you ready?
Yes, just let me share my screen. Can you hear me, by the way?
I can hear you, but I don't see your screen.
Okay, I think it's fine now.
Now I can see it. I hope other participants as well.
But you see the screen I shared?
Yes, now I see it.
Okay, so hi everyone. My name is Deniz and I'm a PhD student from Maastricht University, and I will present you our paper called Isomorphism Testing for T-Graphs in FPT, which is a joint work with my supervisor, Petr Hliněný. So let me start by introducing the graph isomorphism problem. An isomorphism between two graphs is a bijection between their vertex sets such that a pair of vertices are adjacent in one of the graphs, if and only if the corresponding vertices are adjacent in the other graph. And whenever there exists an isomorphism between two graphs, we call them isomorphic, and this is shown by this symbol. And the graph isomorphism problem asks whether given two graphs are isomorphic or not. And in this example, we see three clear-white isomorphic graphs. And pardon?
Jembatan seperti
I can hear you.
Yep, I think that was by mistake. Please continue.
Okay. And this coloring here corresponds to one of the isomorphisms between them. And even though for the previous example, it was somehow easy to get the isomorphism, this problem is somehow special because it's still unknown whether it can be solved in polynomial time or if it is NP complete. And therefore we have this complexity class GI, which consists of problems which can be reduced to that problem in polynomial time. On the other hand, it can be solved in polynomial time for many graph classes such as trees, planar graphs, and so on. And it's linear time for interval graphs, which are the intersection graphs of a set of intervals on the real line. And we will also be using this result in our approach. And this problem is GI complete for split graphs, which are the intersection graphs of substars of a subdivision of a star with a suitable number of rays, as in here. And what does that mean? It means that solving this problem for split graphs is polynomial time reducible to this problem in general case. Now I move on to chordal and T-graphs, which are the subject of this research. A graph is chordal if it doesn't contain an induced cycle of length more than 3. And equivalently, they can be defined as the intersection graphs of subtrees of some non-fixed tree T. And when we consider some fixed tree, a T-graph is defined as the intersection graph of connected subtrees of a subdivision of that tree. And these kind of graphs are also chordal. Split graphs from the previous slides are a subclass of both chordal and T-graphs. Therefore, this problem is also GI complete for chordal and T-graphs, and T is a part of the input. And here we see a T-graph and one of its T representation. And in a T representation, on the branching nodes, we have some maximal cliques of our graph. And any path defines an interval graph. Now I list some of the related work just to emphasize it once more time. Interval graph isomorphism takes linear time. And like 2 years ago, we showed that ST graph isomorphism can be solved in FPT time, where ST is a star with T rays. And we can think of an ST graph as a T graph where T has only one branching point. So they're chordal as T graphs. And how did we get this result? We first listed all their maximal cliques, and then we tried to place each of them in the center. Then we needed to solve isomorphism problem for posets of bounded width together with cardinality Venn diagrams when we have a bounded anti-chain signs by inclusion. And this also extends to an isomorphism algorithm for T-graphs as follows. We can again list all their maximal cliques, and then we can try all possible assignments of these maximal cliques to the branching nodes, but we would have something like this. Therefore, it will only be an XP algorithm. What we did here is that we showed that T-graph isomorphism can also be solved in FPT time parameterized by the size of our tree. And independently and nearly at the same time, Arvind et al. Showed that isomorphism problem for chordal graphs of bounded leafage can be solved in FPT time. And now I will shortly explain why we also have this reference here. So the leafage of a chordal graph is the minimum number of leaves in a clique tree of our graph, and equivalently, it is the minimum number of leaves of a tree T, such that the given graph is a T graph. And how they are related? So if we can solve T graph isomorphism in FPT time, then given a chordal graph of leafage L, we can go over all possible trees which have L leaves and without degree 2 vertices. And since their number will be bounded, we can try for each of them the T-graph isomorphism at the end, getting an FPT time algorithm also for this problem. And from the other side, every T-graph has a leaflet bounded by its size. Therefore, for this side, it's also true. And this means that we can also state the problem we are solving as isomorphism testing for chordal graphs of bounded leaflets, and also their algorithm works for our graphs. Now I will explain our approach, but first I should mention that we don't need a T representation to be given, and also we won't be computing a one. And this is because the current best algorithm for T graph recognition, which gives a T representation, works in XP time. And it is also because for the same T graph there can be different T representations. But since we are testing for isomorphism, our approach shouldn't depend on a particular representation. And instead of this, we find the unique decomposition of our graphs into levels consisting of a bounded number of disjoint interval graphs. And then we will compute the automorphism group of the disjoint union of their canonical decompositions, which will correspond to actual decomposition of the actual automorphisms of the disjoint union of our graphs. And then we will return that our graphs are isomorphic if there exists an automorphism exchanging them. So the disjoint union of the canonical decompositions will look something like this. On the levels, we have disjoint interval graphs, and at each level, their number will be bounded. And between levels, we will have our attachment sets. Now I will first show how we compute the outermost level of a decomposition, and the rest will be computed recursively. So given a T graph which has D leaves, we first compute its leaf clicks. These are the maximal clicks of our graph, which can be placed on the leaves in some T representations, but they don't have to appear on the leaves in every T representation. And among those, we identify the leaf clicks, which are separated from the rest by minimum click cut sets. So in some sense, they will always be closer to the leaves in every T representation. Then we identify the ones which are separated from the rest using these minimum click cut sets, which doesn't separate any other leaf click from the rest. And what we showed here is that the number of such leaf clicks will be bounded. So if this set is not empty, then we return their simplicial vertices as the most outermost level of our canonical decomposition. And otherwise, any of these minimum click cut sets separates at least 2 leaf clicks from the rest. What we do is that we identify these joint minimum click cut sets, we remove them from our graph, and if we get some interval components, then we first join the ones which are separated using the same joint minimum click cut set into one component, and then we return these interval graphs. And what we showed here is that even though we can have arbitrarily many interval connected components here, after we join them into one, we will have a bounded number of them. And there's another case where we don't get any interval connected components, which means that we get some T dash components where this T dash is a sub G of our tree. And in that case, we run this procedure recursively and return the union of their outermost level. And whenever we call this procedure recursively, we always work on disjoint subgraphs of our graph. Therefore, all these procedure takes polynomial time without being dependent on these D. And here we have an example. Any of these maximal clicks can be placed on the leaves in any T representation, and they're separated using this joint minimum click cut set, which is the blue subtree. Therefore, instead of returning them separately, we join them into one, and this will be one interval component. And now we will be getting this canonical decomposition recursively. We first compute the outermost level, getting a bounded number of disjoint interval components. Then we remove them from our graph, and we mark their attachment sets as their terminals. Then, while we don't end up with an interval graph, we repeat this step. And in this example, for instance, we will first be getting level consisting of these magenta interval graphs, and in the second level, the green ones, on the third level, the blue ones. And even though it may not seem like this orange subgraph is indeed an interval graph, so we will stop there, getting the full decomposition. And now I'll explain how we compute the automorphism group of our canonical decomposition. So we first start with a symmetric group, which permutes the isomorphic components and the terminals from the same level. And here our only restriction is that we preserve the cardinalities of these terminals. And then we will be computing stepwise an automorphism subgroup of this starting group, which will correspond to the actual automorphism group of the disjoint union of our graphs. And how do we do that? We use Babai-Sarov groups approach. We loop over all pairs of levels and all cardinalities of terminals. And at each step, we add the restriction that the computed subgroup will consist of automorphisms which are consistent with the current components and the current cardinality of terminals. And as I mentioned before, at each level we have a bounded number of components. So for a pair of levels, we will have a bounded number of components to be considered. And what we also have is that among all terminals, we have a bounded anti-chain size. And when we consider a specific cardinality, it means that we will have a bounded number of terminals to be considered at each step. And that's why we can finish this step in FPT time using Babai-Stavrov groups approach. So after this step, we will be exchanging the connected components from the same level, but it will also be consistent with the terminals. And in the meantime, we also needed to show that given an interval graph and a set of its terminal sets, we can compute the automorphism group of these terminal sets, which will also be consistent with the automorphism group of this interval graph in FPT time when we have a bounded anti-chain size by inclusion for these terminals. So we show that T-graph isomorphism can be solved in FPT time, and as I mentioned before, the current best algorithm to recognize them works in XP time. Therefore, we would like to find out whether they can be recognized in FPT time, and also we would like to investigate whether our decomposition can be modified so that it can recognize T-graphs. And also we would like to consider H-graphs for unicyclic H, and we would like to investigate whether they can be recognized and tested for isomorphism in FPT time. And I should also mention that there is no XP time algorithms for that, so this will also be a good result, I guess. And for this kind of graphs, the problem seems that because there will be a circular graph on this unique cycle of H, they can have exponentially many maximal cliques. So we will potentially need to identify some cliques to be placed on the branching nodes of our H graph. So thank you for your attention. And if you have any questions.
Thank you, Dennis, for your talk.
Thank you.
And now we have ample time for questions. So are there any questions, please? I saw Ana Silva uploaded, but that doesn't mean a question. I just, what is your feeling? Will the answer for this unicyclic graph be affirmative, or do you expect that it may turn out hard?
For the proper case, like when we have a proper H graph for a unicyclic H, I'm nearly sure that we can solve their recognition and also test their isomorphism in FPT time. And I guess some of the lemmas and so on used for them can be used for this general H graph for unicyclic H. I think that we will be able to solve it in FPT time. But as I said, we also don't have an XP algorithm yet, so I hope so.
Last call for questions. Well, if there are no more questions, then thank you again.
Thank you.
And
Hello?
we have a four-minute break.
Sorry.
Who's talking? Chelina.
Celina. Hello. Good morning, everyone.
Yeah.
I'm sorry, I was not fast enough. I wrote in the chat that I had a question, but I'm sorry that I was late. I don't want to.
Then we still have time for questions. Please, Chelina, ask the question.
Thank you very much. It was very nice, and we are very happy because it's closely related to our talk, which is the following one. And I just want to understand. So this class, this subclass of codographs, is not the same as having bounded leafage. Could you please just stress this relation, please?
Okay, so these C graphs, they have bounded leafage when we consider this parameter to be the size of our tree. And
yes.
Because when we define T graphs, we are talking about the subdivision of our tree, fixed tree T. So we
yes.
actually just consider the case that we have T graphs which doesn't have any subdivision nodes because we can anyway subdivide them. And when we think about it that way, then if we know that a graph has bounded leafage, then we have a bounded number of T graphs which will have this many leaves. but
Yes.
bounded number of T-graphs which doesn't have any degree 2 vertices.
Yes, okay, okay.
Yeah.
Yes, yes.
Okay, so then we can actually also solve their isomorphism in FBT time.
Yes, okay. Thank you,
Thank
thank
you.
you. Very nice talk. Thank you.
Thanks a lot.
So we have 2 minutes till the beginning of the next talk. Adele, Anna, talking. Do you have a question? If not, please mute your microphone. May I use this time to ask the participants who are not giving a talk or not asking a question to mute their microphones, please. And also I'm using this time to explain that I am not able to watch the chat and follow the screen at the same time. So when you have a question, please raise your hand or just start asking the question when I ask for questions, like Chelina did. Yeah? And in the meantime, we have 1 minute to go. So Chelina, please, can you start sharing your screen so that in 1 minute you can start your talk?
Oh, it's actually me. Hi.
Oh,
I'm
Raul
yeah,
is giving the
yeah,
talk.
yes.
Okay,
Exactly.
okay. Sorry for
don't worry.
this misunderstanding. So the talk,
I will share.
Parameterized algorithms for Steiner tree and dominating set bounding the leafage by the vertex leafage by Chelina Figueiredo, Raul Lopez, and Alexander Melo and Ana Silva. The talk will be given by Raul in a few seconds.
So can you see my screen?
I can see your screen, and on my clock it's 7:10, which means that it's time for your talk to begin. Please, Raul.
Okay, thank you. So in this talk, I'm going to, as mentioned, I'm going to talk about how we can use some ideas to bound the leafage of a chordograph by the vertex leafage and use this to design parameterized algorithm for chordographs. So this is a joint work with Celina Figueiredo, Alexander Melo, Ana Silva. They are all here. And I am currently a postdoc at the University de Paris Dauphine. But this work was done by the end of my PhD when in Universidade Federal do Ceará. And so I mentioned in both institutions here. So first, chordographs. Chordograph is just a graph that has no induced cycle of size at least 4. So for example, let's take this guy. This guy clearly is not chordal. And as an exercise, let's just make it chordal. To do this, we may need to add an edge inside the cycle. But now we may still have a C4, like this red one. So we add another edge to break it. Then they have a C4 on the other side. We add another edge to break it. And now this guy is chordal. Okay. And chordographs, they are algorithmically meaningful, which means that we can solve some problems that are classically hard efficiently in chordograph. We can solve click. We can solve vertex coloring. I think we can solve, as mentioned by the previous speaker, I think we can solve graph isomorphism in FBT time. And also, but then it's not like the best thing ever, because some problem remain hard, like dominating set, K dominating set is W2 complete. Oh, W2 hard, sorry, it should be hard. And because I don't know if it's W2, okay. And then Steiner tree is also W2 hard in chordographs. And what we're going to do is that we're going to show that we can do K dominating set and K Steiner tree in FBT time in some subclasses of chordographs. Okay, so a dominating set, most of you should know it already. The problem is defined like this. I'm given as input a graph G and an integer K, and I want to search for a subset of vertices D of size at most K, such that every vertex of the graph either is in D or has a neighbor inside of D. And so if I find some guy like this guy is known as dominating set of my graph G. And the connected dominating set problem is basically the same thing, but I'm also asking that G of D, the graph induced by D, is connected. And the natural parameter for those guys is K, which is the size of the solution. And it's also worth mentioning that connected dominating set and the Steiner tree have the same complexity in subclasses of causal graphs, and here the same complexity in the classical sense. Okay. So now intersection graphs. To talk about subclasses of causal graphs, I'm going to talk about intersection graphs a lot. So if I'm given a graph G and a family of sets where I have one set associated to each vertex of G, I say that G is the intersection graph of this family if and only if I have an edge of G, U, V, and G, whenever the sets associated with U and the set associated with V, they do intersect. For example, I can have an interval graphs, which are the intersection graph of subpaths of a path. I can have this big path blue here. All the black paths are subpaths of it. And you can see that they intersect in a very obvious manner. And I can extract the interval, the intersection graph of this collection is this guy. Okay. And we can make more complicated things with this idea. We can go for interval graphs to rooted directed path graphs, which are the intersection of directed paths in an out tree. And here an out tree is when I take a tree with a root, a unique root, which is a source vertex, and I direct every arc. I orient every edge away from the root. And contained in this class, I have the class of directed path graphs, which are the intersection of directed paths in an oriented tree. And now the difference here is because an oriented tree is just I take a tree and I orient the edges any way that I want. So there is a distinction between those classes. And it's important to mention this here because many times I see that this is not very, there is no, I don't see a distinction between those classes very often. People usually call this as this. And from directed path graphs, I can go for undirected path graph, which is just intersection graph of paths of a tree. And then from these guys, I can go for the causal graph, which is intersection of subtrees of a tree. Okay, now let's look at some hardness. So dominating set and Steiner tree, they are both polynomial time solvable in rooted directed path graphs. And they are both NP complete in undirected path graphs. They are both too hard with parameter K, which is the size of the solution in causal graphs. And for this guy, for directed path graphs, the thing between rooted directed path graphs and the undirected path graphs, both questions are open. I'm going to talk a little bit about this later. So, okay, so what's between? We can ask what is between undirected path graphs and causal graphs. And we can make the distinction between, we can go from one to the other by talking about two graph parameters, which are known as leafage and vertex leafage of causal graphs. Okay, so since I'm going to be talking about two graphs, I'm going to, when I have a tree model, I'm going to mention that mention the vertex of the tree as nodes and the vertex of the graphs as vertices. Okay, so a tree model of a graph G is just a tree is formed by a pair, which is a T, 3T, and a collection of subtrees where I have one subtree associated with each vertex of G, and G is just the intersection graph of this collection. Right? It means that I have an edge in G whenever two of the subtrees they intersect. So, for example, I can have this tree right here, and here I'm drawing a square node to say that there is a vertex V. This is a tree model, and I'm using a square node to denote that there is a vertex V that the associated tree, if the tree associated with the vertex V is only that guy. So for instance, this tree model draws this graph on the right, and I have that the tree associated with the vertex U is only B, the tree associated with the vertex V is only C, and the tree associated with the vertex W is only D. And also I have this blue tree right here containing everyone. So I add this blue vertex here, and then add an edge from it to everyone. And I can make some more complicated things. I can also actually have now the same UVW, but now I also have a blue vertex, a red vertex, and a cyan vertex connected like this. I can also make choose it to be now an out tree. The root here would be B, and then I would have this graph. I cannot have the cyan vertex on the previous slide anymore because I cannot have a directed path from C to D. But then I can actually now make it an oriented tree by adding some other E guy and placing the edge to A and an edge to D, and then I have this cyan guy like this. And this is the graph that I'm constructing with this tree model. Okay. And now, what is the leafage and the vertex leafage? Given a tree model C, I will say that the leafage of the tree model is the number of leaves of the tree. And the leafage of a graph G is the minimum K such that G has a tree model with leafage K. And the vertex leafage of a tree model is the maximum number of leaves of one of its subtrees. And the vertex leafage of the graph G is the minimum K such that G has a tree model with vertex leafage K. So of course you can only have a vertex leafage has to be at most the leafage, right? So the leafage of the graph is the stronger parameter between the two. And for example, if you have what are interval graphs, right? Interval graphs are just the caudal graphs that have leafage at most two, because you need to have the intersection of paths. And undirected path graphs are the caudal graph with vertex leafage at most two, because now you can have a tree, but then what you want to consider inside of tree is only paths. Okay, now. Okay, so now if I want to find a tree model with optimal number of leaves, optimal leafage, I can do this in polynomial time. However, if I want to, I cannot do this for the vertex leafage. In fact, I cannot even decide efficiently if the vertex leafage is at most 3. This is NP complete. So this is much harder. And also dominating set, K dominating set, the K is missing here. Oh, actually, not the K is not missing here. Dominating set is FPT being parameterized by the leafage. This is important. I'll leave that. Okay, so what we want to do is to bound the leafage by the vertex leafage, and then use these ideas to produce algorithms. So for this, we use something that we call a minimal tree model of a minimal tree model, right? And then it has some interesting properties that we use all the time. But the most important thing that I need to mention now is that when I have it, I mean that for every leaf of the tree, the host tree, I'm going to have a vertex, right? It's associated with that leaf. So, and I'm going to call those vertices the leafy vertices. So U, V, W are leafy vertices of this guy, this graph, because U is associated with P, W is associated with T, and V is associated with C. Okay, and now, very simple idea actually. Okay, if you want to have a dominating set, of course, for your graph, you have to dominate all leafy vertices because you have to dominate everyone. And then by dominating it, what we are actually saying is that for each leafy vertex T, what we want to find is a subtree of the model that contains that leaf. Okay, but then each subtree that I have in my model can only cover at most this number of leaves, right? Because this is the vertex leafage of the graph, which implies that if I have too many leaves on my model, I mean more leaves than k times the vertex cleavage plus 1, the instance of k dominating set is negative because I do not have enough guys to actually cover all the leaves of your tree. Okay, so what you conclude from this is that every positive instance of k dominating set has to have this bound. And then what we say here, more precisely, what we're trying to do is that we are choosing paths. For instance, when you have vertex leafage equal 2, you are choosing paths to cover your leaves. You can actually this blue guy, and then this red guy, and then this cyan guy, and then this green guy to actually cover everyone from in this example, your undirected path graph. Okay, so what is the idea that we want to do with this is that, again, square nodes are leafy vertices. What we want to do is that for the algorithm, that okay, we're going to guess, start from a red vertex, from a red leafy vertex. And from this guy, we're going to look at each of the other leafy vertex. Each of the other leafy guys, they are actually specifying directions that we can choose to pick a guy to cover this red guy. We just pick one, we call it a target. And then, okay, since we're going to say that we want to cover the red guy with a path that is from the red guy to the blue guy, I'm going to just pick the best one that I can. I mean, the one that starts here and goes the furthest that I can in the blue direction. It may actually stop right here. When I do this, I'm going to mark every guy that was intersected by that red path as dominated because they are contained in the neighborhood of this guy. And then we can do some tricks and reduce the instance to a smaller one. And then we repeat this for a new pair of origin and target pair of non-dominated leafy vertices. Okay. Following this, what we get is a bounded search tree because from the start we have this many choices of origin and target pairs. And so each choice that we make, we generate a new instance that has at most k minus 1 leaves. From each one from this instance, we generate at most this number of new instances. And since we have a budget k to construct a solution, the size of this the height of this bounded search tree is at most k. And if we do some math with those numbers, we obtain that we can an algorithm for undirected k dominating set and undirected path graphs in this time. So we get this, doing this trick, we get this for dominating set and undirected path graphs. And also with the same ideas, with some small difference, we can get this time for Steiner tree and connected dominating set. And also the time that we get for undirected path graphs beats the alternative that was to actually use the bound the leafage by the vertex leafage and apply the algorithm by Foreman et al. To get this time. And now repeating the table, what we got new is that we covered this with FPT and this with FPT. Before it was just NP complete. And then in short, we showed this that dominating Steiner and connector are FPT when parameterized by the size of the evolution plus the vertex leafage when we are given a model with optimum vertex leafage. But all these are applicable. All these are applicable to undirected path graphs because we can always get, we can recognize undirected path graphs in polynomial time. Okay, so in short, we show that we can get an FPT algorithm whenever we have an FPT algorithm by the leafage. We can also get an FPT algorithm by the size of the solution plus the vertex leafage, provided that a tree model with optimal vertex leafage is given. This works for this largest class of graphs of problems, this mean LCVSP problems, these including independent set and dominating and click. And regarding the open questions, we actually believe that dominating set is FPT when parameterized by the number C of sources on a tree model, on a directed path graph with C sources. And there is NP complete otherwise. And this would be very interesting if it's correct, because it would mean that it's actually a separation problem between the classes of directed path graphs and rooted direct path graphs. And oops, okay, this is it. Thanks for your time.
Once more. Thank you, Raul. Any questions, please?
I have a comment.
Comment, please.
Please, could you say anything about Steiner tree, since you mentioned dominating set, please? You said that you believe the dominating set is NP complete for GV. What could you say about Steiner tree, please?
I think that we have a reduction from connected dominating set to dominating set, right, in this class DV. So if we have this, if we have the algorithm for the FPT algorithm for dominating set, then we also get an FPT algorithm for connected dominating set and for Steiner tree. But then if we get the hardness, I don't think that the hardness will be immediately applicable for Steiner tree also.
Thank you. Thank you.
Any other question? If not, then I would like to thank Raul and all the speakers of this session once more. And we ended 1 minute early for the invited talk to be introduced and started. Thank you for coming to this talk. Bye-bye, everybody.
Bye-bye. Thank you.
Thank you.
Bye. Thank you.
Okay. Good afternoon, ladies and gentlemen. Thank you for Mr. Tio Darmawan and also all of the chair and of course the presenter too in the session before. And also we would like to thank you for your participation in WALCOM 2022 until the second day. And now we are going to move to the next session. But let me remind you to fill the link of attendance. And for the next agenda is invited talk 2, which will be led by Miss Petra Mazel as the chair. For Miss Petra Mazel, time is yours.
Okay, thank you very much. So welcome to the invited talk session. My name is Petra Mutzel. I'm from Germany. And so I'm very happy to welcome also the invited speaker here, Hans Bodländer. He's a head of the Algorithms and Complexity Group at the Department of Computer Science at Utrecht University. He's a leading researcher on graph algorithms and parameterized complexity. He has published more than 300 scientific papers, and which is a tremendous number. And also his H index is quite very, very high, 67, which is for the field of graph algorithms. I think it belongs to one of the highest number there. His excellent work was awarded in 2014 by the IPEC Narod Prize of the European Association for Theoretical Computer Science. And this work this prize was for outstanding papers, or is for outstanding papers in the area of multivariate algorithmics. So Hans, I see you're ready to start your talk, and we are looking forward to your talk titled From the W Hierarchy to XNLP, Classes of Fixed Parameter Interactability.
Thank you very much, and I'm very happy to be here. I actually have two screens, so if you put something in the chat, I can actually see that. So what I'll want to do is I'll start with some introduction that many of you will know. What is FPT? What is XP? Tell about some But I really want to look at what's going on there in this world of XP and what kind of classes are there. And as you know, the W hierarchy, and if in several of the talks before already, W1 hardness was mentioned, and so I'll tell a little bit about that, and then I want to go to a new development, which is basically starting with a story it's an old story about a paper about the problem of bandwidth, and it leads to a class which we called XNLP, and then I'll talk a little bit about that. And then in the end of the talk, I'll talk about some other classes of problems. And I hope that, I mean, for those who are unfamiliar with parameterized complexity in the beginning, there will be new stuff. And I think for many of you, something new will be at the end. And actually, I will give some homework at the end of the talk to many you. So why parameterized algorithms? So suppose you are the mayor of a city, and you have to find a number, you have to decide where you put some fire stations, and you want that everybody lives at most 15-minute drive away from a fire station. Now, you may realize that this is actually an NP-hard problem. It hides a dominating set inside it. But then there comes the financial man of the town, and he tells you, we have money for 3 fire stations. Now, suddenly this problem becomes much easier. You can just look at all possible locations for these 3 fire stations. You have a cubic algorithm just to find this. So what you have here is this property that you have an NP-hard problem, but it becomes easy because some parameter is small. And there are many examples in the theory of algorithms. So with dominating set, you can solve an n to the k time by just trying basically all different situations. There is a nice branching algorithm for vertex cover, which solves the problem basically in 2 to the k times linear time. You may know that many problems which are hard become easy and have a running time, which is a function of the tree width times the number of vertices if you have graphs where the tree width is small. And there's a classic result in integer linear programming that tells that if the number of variables is small, then you can solve this problem in a time which is a function of the number of variables times the number of bits to denote this integer linear program. So we have this property, problems may become easy if some parameter is small. And in early 1990s, Downey and Fellows, they started to building a theory about that. And I'll start with some notions there. So they looked at problems which we call parameterized, and a parameterized problem has 2 parts of the input. The first part is just some string in an alphabet, and the second part is an integer, and that we call the parameter. And that's what we usually assume that it's small. And what we want to know is now how much time does it cost to solve some problem, some parameterized problem, as a function both of the input size and as a function of the parameter. Now there, basically you can see 3 different types of behavior. This problem can be fixed perimeter tractable, which means you have an algorithm which solves it in time, a function of the parameter times something polynomial in n. For instance, vertex cover is an example. You can have that the problem is an XP, or what we call slice-wise polynomial time. And then you have an algorithm whose running time is the input size to the power a function of your parameter. So for every fixed value of the parameter, you have a polynomial time algorithm, but the polynomial is growing when your parameter is increasing. And so it's a dominating set has this property, you have an n to the k algorithm there. But it can also be bad in the sense that the problem is para-NP hard. For instance, graph coloring is already NP complete if you have 3 colors. So NP hard problems are NP complete even for some fixed value of the parameter. And then you're more or less out of luck here as looking at the parameterized algorithms. Now for this, to distinguish these first 2 classes, that's basically where a lot of this this fixed parameter tractability complexity is around, because XP really is much worse and the complexity is much higher than FPT. Also, one of the nice things about being fixed parameter tractable is that this problem actually has a kernel. And if you're not in FPT, you don't have a kernel. And what the kernel is, it's a wonderful field, but I won't talk about that today. Yeah, so central in this theory about distinguishing XP and FPT is the W hierarchy, which I'll tell about next. And I would also like to mention that using a diagonalization argument, you can actually show that FPT is a proper subset of XP. So there are problems in XP which are not fixed parameter tractable. So I'll review some early important results, and then I try to tell things about what I think is a very interesting structure within XP, and I'll also try at some points to give some of my intuition why things are where. So, but first, to really talk about hardness and completeness, you need the notion of reduction. And for parameterized problems, you have parameterized reductions, which have the same property as usual, that it maps an input where the answer is yes to an input with the answer yes and a no to no. But there is another property, namely that if you have an input, then the new input, the value of the parameter should be bounded by a function of the alt parameter. So basically small parameters go to small parameters. That's the second property. And the third property is that you can basically use FPT time to compute your reduction. And for more involved classes, you need reductions with extra properties. For instance, for XNLP, you need actually that you can compute this reduction in logarithmic space. And there are some details which are technical, but not very difficult, but I'll skip about all these details. So you have to believe that things go right here, but yeah, there's some technicalities for the larger classes. So Downey and Fellows introduced this W hierarchy, and then we have classes W1 and W2 and W3, and for every integer there is a W class, and then you have WSAT and WP, and the original definitions is in terms of circuits. And I'll skip that here because I think there is an easier to understand definition using some versions of satisfiability. And there is a whole hierarchy, so all these classes are contained in the next one. And we believe actually that W1 hardness already tells that the problem is not fixed parameter tractable, because if W1 would be the same as the FPT, then the exponential time hypothesis would not hold, and people in general believe that the ETH is actually true. So W1 hardness is really an indication, okay, this problem is not fixed parameter tractable. So first, the first animal in our zoo is W1, and you can define it as follows. You can say, okay, a problem is in W1 if and only if there is a parameterized reduction to a problem called weighted 3 satisfiability. And what's that? I have a Boolean formula in conjunctive normal form with 3 literals per clause, so just like 3sat. But I also have an integer k. And now the question is, I want to make this formula true, but I have to set precisely k variables to true and all others to false. So this is a parameterized version of 3 satisfiability. And that problem is W1 complete. And you can just see if you can formulate your question in this type of logic, then it's also in W1. And many problems are known to be W1 hard, and already today and yesterday we see in this also at WALCOM problems which are W1 hard, but also some problems are W1 complete. The independent set is a nice example of a well-known W1 complete problem. So W2 has a similar characterization. The only difference is now that I allow my classes to be arbitrarily large. So I can have classes with any number of literals I want to have. And then so this weighted CNF satisfiability is basically the same thing, but now I have just large clauses. And again, the problem is in W2 if it has a parameterized reduction to this weighted CNF SAT. And again, many problems are known to be W2 hard, some are known to be W2 complete, and a nice example of a W2 complete problem is dominating set. Now, after that, we have for this classes W3, W4, W, and so on. For every integer t, there is a WT class. And the basic idea is that we want to, that is the complexity of deciding if a Boolean formula can be made to true by setting exactly k variables to true. But this formula has t times an alternation of ands and ors. So that's an and of some things, or which each of these is an or of some things, and that's an and. So if you would write it down as the tree of your formula, then the depth of this tree would be t. And WSAT is just the same thing, but now I just will have any Boolean formula. And WP is defined in terms of circuits, which I'll skip here. Now, for this higher classes in the W hierarchy, there are very few problems known to be complete for these. But to be in this hierarchy, basically all these problems which are member of the W hierarchy, they have this sense that I want to choose k things out of n things, such that some property holds. So if that's typically if you are member of this hierarchy, then it's always a question of choose k out of n with some property. So that's, let me now go and start with the story of bandwidth. And it's a story which goes back like more than a quarter of a century ago, but let's first define bandwidth. So I am given an undirected graph and an integer k, and I want to number the vertices from 1 to n in my graph such that for every edge, the difference between the endpoints, the numbers of the endpoints is at most k. So here in this example, you see a graph with bandwidth 2, because for every edge, the difference between these numbers is at most 2. And it's well studied. It's really a very old and classic problem. One of the reasons is that it has a strong connection with Gauss elimination. It's basically the question, I have a symmetric matrix, I permute rows and columns such that all the non-zero elements are at a band of width k along the main diagonal. And for that reason, it's also the name bandwidth comes from it. And already in 1983, Monin showed that this problem is NP complete even for a very simple type of trees, which are caterpillars. I have a picture of a caterpillar next to this. But there's also a paper 1 year later, which shows that bandwidth is actually in the class XP. You can solve it in n to the k plus 1 time by Gurai and Sibero. And I'll talk a little bit about that algorithm as well. Now, in 1994, Mike Fellows, Mike Hallett, and I wrote a paper, and we gave proofs of many results in this paper, but we also claimed without a proof that bandwidth was WT hard for all integers t for trees. And that was the time in 1994, you still could get away with that. You just published a paper at the conference without a written down proof. I mean, it's a long time ago. And we never wrote this down. Actually, I promised Mike Fellows that I would write it down, and I was for many years too lazy or too busy with other things, I should say. Also, in the same year, Mike Hallett conjectured that bandwidth is not in the class WP. It's not in this hierarchy at all. And the argument is interesting because if you are in WP, it's choosing k elements out of n. So your solution, you have a certificate, you can write down a solution with k log n bits. But for bandwidth, you have to order all the vertices of your graph. And it seems that you need at least something like n bits to write down any solution to the bandwidth problem. So it seems that you need for bandwidth more bits to write down solutions than for problems in WP. So that's an indication, it's not a formal proof, that bandwidth is not in this W hierarchy. So we had really this question, where is this bandwidth problem actually? What is the complexity of it? And it was open for a long time. But let's first, before telling the rest of the story, show you the caterpillar, which is just a tree with the property that I have one path, and then to this path, I attach a number of other paths. And that's a very simple type of tree here. Yeah. Okay. So in 2014, there was a written down proof that bandwidth is W1 hard for trees by Dregi and Lokstanov. And they also showed, with help of the ETH, a lower bound for how hard it is, how much time it costs to solve bandwidth on trees. And finally, in the same attic, as you can see on my second screen, me sitting here, I was locked up, and then I finally came down to writing down the proof of after almost 30 years, to write down this proof of the and showed that bandwidth actually indeed WT hard for all T, and even for caterpillars. But then we start to think again about it, and finally gave a class which I call XNLP, and I'll tell you about that. And that shows that actually bandwidth is complete for this class XNLP. So that pinpoints precisely the complexity of bandwidth. And let's go now to XNLP. But first, some intuition. So here is a non-deterministic algorithm for bandwidth, a very simple one. What I do is I guess every time I guess the next vertex. Now you need to check if you guess a vertex, and then you give this the next number. You check when you guess a vertex whether it was not already taken, and you check if it has a neighbor which has a number which is smaller than the current number minus k. If one of these checks fails, you reject, and otherwise you guess the next vertex. Now, to do these checks, the only thing you need to know are the last 2k vertices. So you keep only 2k vertices in memory. And then with depth first search, you can actually do this verification. So what we now have is we have a non-deterministic algorithm for bandwidth, which basically has something like 2k vertices in memory. So it has order k log n bits in memory. So we have a non-deterministic algorithm using k log n additional memory, except for that it has the input. It's interesting to see there is actually, you can, from a non-deterministic algorithm, you can build a deterministic algorithm. This is a classic technique. You basically just make a table of all the states you can reach by the non-deterministic algorithm, which is called, if I remember well in class to me, was called the power set construction. So if you take this algorithm and you turn it into a deterministic algorithm, you get to the n to the basically 2k algorithm. And that's basically almost the same as the 1984 algorithm, except that these authors were more careful with the details, and then you'll get an n to the k+1 algorithm. But also it goes in the other direction. And this is actually the way we noticed that there's this non-deterministic algorithm. If you know that there is a DP, a dynamic programming algorithm, instead of building the entire table, you just guess an element in the table, and then you get a non-deterministic algorithm. Somebody has to mute himself because Mr. Hassan is, I think, somebody, I hear some noises. Anyhow, so this is a way of finding actually and seeing, okay, there is a non-deterministic algorithm for a problem by just inspecting existing existing dynamic programming algorithms. It goes in two ways in this way. So that's an intuition that, and so let's then look at what we know about logarithmic space. So for classic decision problems, there is a theory of L and NL, which are well-known classes. L are all the problems which you can solve with additional logarithmic space, and NL if you have a non-deterministic algorithm using logarithmic space. And because the time is at most 2 to the power of the space of an algorithm, you know that L and NL are subsets of P, they imply polynomial time. But you can also look at parameterized variants of these, and then you can get actually three classes. There is XXL, which is a deterministic algorithm using a function of K times log n space. There is XNL, which is non-deterministic function of K log n space, but also, and this appears that we need, it's actually XNLP, where you have a function of K log n space and a function of K a polynomial in n time. So you use FPT time, because 2 to the power Fk log n could use XP space, XP time. And 2 to the power Fk log n is n to the power Fk. So you can distinguish whether you use exponential XP time or FPT time in an algorithm which uses Fk log n space. And XNLP, basically you do n guesses, so it uses indeed this Fk n time. And so bandwidth is in XNLP. That's basically what the non-deterministic algorithm shows us. So this class with a different name was introduced in 2015 by Elberfeld et al. And they showed for three problems, for a number of problems, they showed that they are XNLP complete. There is a version of Turing machine acceptance. There is a problem on cellular automaton, which we used as starting points for the reductions. And there is, what is nice is a well-known problem on strings, which is called longest common subsequence. And now, so last year, Carla Groenland, Jesper Nederlof, Celine Svenhaus, and we showed for a large collection of problems that they are actually complete for this class XNLP. I'll tell you about what we call weighted, chained weighted satisfiability. There's a chained version of multicolored click. There are some problems where you take path width as parameter or path width divided by log n as parameter. There is a nice scheduling problem, which I talk about as well. And there are reconfiguration problems, but there's also bandwidth. And I just have here our arrow of how the reductions are going. And you can see here at the top down, there is this bandwidth problem indeed as one of the hard problems. Okay, but let's just give a few examples of how these reductions are going. And let's first start a problem which is very useful to use is a problem which we call chained weighted satisfiability. What I now have is I have a number of sets of Boolean variables, and then for every set and the next set I have a formula. And now from each of these sets I have to choose k variables such that all these formulas are true. So that's what we call chained weighted sat. And so here more are in the picture. So you have all these boxes are formulas, and you have to make the conjunction of all these formulas true by choosing from each of the sets xi precisely k variables. It's a very useful thing to start your reductions from, and in many cases, if you could just modify or update a reduction from if you have a W1 or W2 hardness proof, then in several cases you can just look at how that goes, and if then getting XNLP hardness in this way. And actually, not only there are much more regular variants, for instance, one where all the formulas are true or where all the clauses are monotone, and there are several of these variants which are also complete for this class XNLP. But one other problem we show to be XNLP complete is a little bit strange, but it appears to be very useful. And it takes a very strange machine model, which we call the non-deterministic, non-decreasing counting checking machine, so the NNCCM. But actually, when I think about it, I always think that one of these C's actually doesn't mean what it actually means, but crazy. But but okay, but it appears to be really a very nice tool to get actually relatively simple proofs in several cases. So we have K counters, and these counters, they start at 0. They can never be larger than some value n. And at each step in time, we can do the following things. We can non-deterministically decide to increase counters. We never decrease counters. We can keep them at the same value or make them larger, but not more than n. And then if we are done with increasing counters, we do a check. We have a series of checks and we do them in order. And if we do a check, we have a for tuple consisting of a counter, a value, another counter, and another value. And if this first counter has this first value and the second counter has this second value, then we halt and reject. And otherwise we continue. That's all. So, and if none of these checks reject, then we accept. That's the whole way the machine goes. And so the question is giving this integer, these integers and this series of checks. The question is there an accepting run? Is it possible to, with non-deterministic steps, to do this in such a way that we never halt? And the parameter is the number of counters. So this is this first problem, and it's XNLP complete. And I'm going to use this and show you the proof for a hardness proof for a very classic problem from scheduling. And this is the following. I have a number of tasks. Every task uses one step in time. I have M machines, where actually the number of machines is my parameter. And I have a partial order on tasks, some precedence constraints, which means that if a task is before another task, then I first have to complete this first task and then can do the other task. Yeah, this tells when you only can do some tasks after some others. And there's a deadline, and then the question is, can you schedule all the tasks? So on these M machines before the deadline. So this is really a very well-studied problem, and it's one long-standing open problem already since the 1970s, whether this problem is NP complete or polynomial time solvable if we have 3 machines. This is one of the classic open problems from scheduling theory. So in 1995, we showed that this problem, if the number of machines is a parameter, it's hard for W2 together with Mike Fellows. And if you look at this proof, it also shows that as a second parameter, you can take something called the width of the partial order. And the proof I use, you have to believe me, but the width actually indeed is also bounded by the function of number of machines. So, okay. So what we actually show is that this problem with number of machines and the width of the partial order is XNLP complete. If you look to algorithms existing for this question, there's a dynamic programming algorithm, and it really directly translates back to a membership proof in XNLP. So, so for the hardness proof, which is something I'll go and check, I'll sketch to you, and it goes from this accepting NNCCM. So I have K counters between 0 and N and R checks. I take some large number L. I take my number of machines 2 times this large number plus K plus 1. I properly choose a deadline. And now I have, which I call D. And now in my input consists of one gadget, which I call the floor, which is a chain with D jobs. And then at some moments in time, namely at n+1 and 2n+2 and 3n+3 and so on, I take L additional jobs in parallel. So what we have here is the only way to schedule this, because I have D jobs in a sequence and D time, that the first job goes to time 1 and the second to time 2 and the third to time 3. And then at these different times, there are suddenly lots of extra jobs there. So sometimes slots have less machines available than others. That's what the floor is doing. And now for every counter, I take a gadget, which is a chain of D minus N jobs. And then for some checks, I do some parallel jobs. So to be precisely, if I have at the ith check, I check for value B, I take L jobs in parallel to the n+1 times I minus beta job of the chain. Yeah, so that's what we're going to do. So we have this is my whole input, and now you can show actually that there is a solution to your scheduling problem if and only if there is an accepting run of the NNCCM. The idea is the following. So we have this job, this chain with we have a chain for a counter. We have a chain with D minus N jobs. So I can basically N times I cannot schedule a job. I can skip this time. So what I do is if I don't schedule a job of the chain at a certain time step, that corresponds to increasing the counter by 1. So the counter is basically precisely the number of steps that at each point in time, the counter is the number of steps that I didn't schedule a job of the chain before that. Yeah, so that's the plan. And because you have D time steps in a chain of length D minus N, the value of the counter is then always between 0 and N. And now if check I includes whether a counter Cj equals beta, then the chain of Cj has L parallel jobs at time n+1 times I minus beta. And so it just have n+1 times N. At that time, it has L parallel jobs if and only if this counter equals beta at that check time. So what you now have, if you do a check, if both counters have the value which is checked, then there are L parallel jobs of this floor gadget, and each of these counter chains has, because of that, L parallel jobs as well. So then we have 3 L jobs at this time, but we cannot have more than basically that's too many. So then so if both, and if there, so this shows that if there is a schedule, then actually indeed the NNCM accepts. And in the other direction, if you have an accepting run, then at every time, at most 2 of these large amounts of parallel jobs is somewhere. So you have at most 2 L plus 1 job per chain extra, and then you have enough machines and you have a valued schedule. So I did a few of the hand waving things here, but I hope you can see that it's actually, I mean, if the details are, I mean, there are hardly any details left. So it's a really, and if you look at this proof, it's much simpler actually than the proof in the original 1995 paper. So you get a stronger result by using this NNCM with a much simpler proof. Okay, so this is what I wanted to tell, what I wanted to tell about XNLP, except that there is a very interesting conjecture. There is was a paper by Allender, and then Michael Filipchuk and Rockna used things from that paper, and they formulated a conjecture about the space use of a number of problems. One of them is longest common subsequence. And we can reformulate this conjecture in the following way, that if you have an XNLP hard problem, then there does not exist an algorithm which solves this problem in XP time and n to the function of parameter time, and uses at most FPT space, a function of the parameter times a fixed polynomial space. So it tells you that an XP algorithm for an XP and XNLP hard problem cannot use small space. It must use a lot of space. I would actually want to strengthen it. I think it's also, I believe that actually the space is also of the form of XP. And this is both theoretical and practical of interest. I mean, in practice, if you run a dynamic programming algorithm, and I had students doing projects implementing XP algorithms. And what you typically happens is that at some point, your computation runs out of main memory. Your dynamic programming tables do not fit in the main memory of your computer. And then all the time is being spent of going from swapping information, data from main memory to hard disk and back. So, and hardly any time is spent on computation, and your program, you basically just stop. Because so for practical reasons this is interesting, and for theory it's also interesting. So XNLP hardness really tells us more than being W1 hard, because it tells you, okay, we probably need much memory. Okay, so that's what I wanted to tell you about XNLP, and I want to do a little bit part on reconfiguration. And there, again, one of the recurring themes of WALCOM, and we look forward to the invited lecture later today. And there were lots of other papers, again, with reconfiguration. But what I want to look at is one special case, which is a reconfiguration of independent sets. So what I have is I have a graph and I have two independent sets. And I want to change the first independent set into the second with a sequence of moves. And every move takes out the vertex from the set and adds another vertex back. But you have to keep that the set is independent. So at each point in time, your set has to be independent. And the parameter is the size of these sets. Now the unparameterized problem is p-space complete. And it was shown that if you take the sizes of sets as parameter, the problem is actually W1 hard. But you can strengthen that. And what also is nice to look at is to look at variants where you specify how many moves you can make. And then you get really a kind of interesting behavior, because depending on how you write down the number of moves, how you view that, the complexity changes. So you could take the number of moves as a second parameter of your problem, and then the problem is W1 complete. If you write down the number of moves in unary, so if you have 1 million, you are allowed to make 1 million moves, then your input size is at least 1 million. Then the problem is XNLP complete, which is a reduction from chain satisfiability. But if you write down the number of moves as a binary number, it's actually complete for this class X and L. So it's complete for another class. And there's the proof you can do by basically a proof in a similar type of flavor as Cook's proof, which shows that satisfiability is NP hard. You simulate a Turing machine inside the reconfiguration problem. But actually the most interesting of the four, I think, is the case where you don't specify the number of moves, because then the problem is complete for XL. And here's the intuition. If I am allowed to make arbitrary many moves when reconfiguring, then what I can do is I can take a position. If I can move from a certain position, I can also move back. So if I simulate a Turing machine, this Turing machine is actually able to do a step back in time. So you can not only move forward in time with your Turing machine, but you can also move back in time with the Turing machine. And that goes to a notion of Turing machines, which are called symmetric Turing machines, where a symmetric Turing machine has for any way of going from a certain state to another next state, there's also the possibility of going from that next state back to the previous state. This is called the symmetric Turing machine. And it's actually known for a long time that symmetric Turing machines have the same computational power as normal Turing machines. If the space is logarithmic, so basically SL equals L, that's symmetric Turing. If you have logarithmic space, then it doesn't help to be symmetric. And that's what we use. Actually, we simulate a symmetric Turing machine, and in this way show that this problem is XL complete. And you have similar types of results for dominating set. So this was a little bit what I wanted to tell about new results, and what I want to go now. Oh yeah, no, I still want to mention one thing about very new results. I mean, in our work, we proved for several problems that are XLP complete if you take path width as the parameter, or path width divided by log n as the parameter, or linear click width as the parameter. And you see in my slide a number of examples here. But then the question is, yeah, what happens if you take instead of path width tree width, or if you take click width instead of linear click width? Well, you know, of course, that because these include those of small path width or linear click width, we have XNLP hardness. But for which class are these problems complete? And we believe they're not complete for XNLP, but for some other class, which is, and the idea is based on work by Allender and Machin, Filipchuk, and Rokna, where it's Michal, sorry, it's Michal Filipchuk. We can, we define a class which we call XALP. And XALP is the class of, it's basically a parameterized variant of a class also called NLP AUX, or yeah, you can see SAC with some things there. But it's the class of parameterized problems which you can accept with an alternating Turing machine. Again, it uses function of k log n memory. It uses FPT time, but also each computation uses at most order log n co-non-deterministic steps. Now, if you don't know what is a alternating Turing machine, we take a Turing machine and it can make non-deterministic steps, which is a guess, and you say yes if at least one of the guesses says yes. But you can also use a co-non-deterministic step, and that means that you take again a guess, but you say yes only if all the guesses lead to a yes. So you have this, you can have this alternation between co-non-deterministic and non-deterministic steps, which is basically, if you would write down in a formula, an alternation of the for all and there exists. And this is what we believe is actually the class which captures the complexity of problems on 3D, many problems on 3D compositions or click width. There are equivalent definitions, either with other forms of ATMs or with circuits, but you can also say, okay, take the model of XNLP, but also give your Turing machine access to an additional type of memory, which is what people call the push-down automata, just functions like the stack. So you could just only put things on top of the stack and get the element from the top of the stack back, but not. And that's what the additional memory you have, and that you can actually show that these things are equivalent. And Well, we're still, this is work in progress. So we believe that most problems which are complete for XLP for linear structures, you have a corresponding ALP completeness result for corresponding tree-like structures. So things like list coloring or all or nothing flow with tree visits per meter, or the max cut with parameters like the click width or the rank width. And we believe that these are, but we still have to write these things down, that these are complete for XLP. So what I want to do in the last few moments is just to review a few of the other classes in this which live within XP. And I'll skip some definitions, but I would just want to give some intuition there. And there's the M hierarchy, which was introduced by Flum and Grohe. And this basically captures problems with small input size. And there, interestingly, this M hierarchy is interleaved with the W hierarchy. So in the sense that the M1 is a subset of W1, is a subset of M2, is a subset of W2, and so on. But it captures problem where you can express your input in a small way. And yeah, so one of the examples is of a M1 complete problem is the mini independent set problem, where you are given a graph where you can describe the graph, and I'll skip the details what kind of descriptions we allow, but you can describe it in k log n bits. So the parameter is the length of your input divided by log n, basically here. And then you want to know whether there's an independent set of size at least r. So the independent set, they're different from normal independent set. Your independent set can be larger, but the size of your graph is small. Basically, the description size of your graph is small, and that's M1 complete. So there are two classes which are of hierarchies introduced by Abelson and al. Introduced what they call the AW hierarchy, and Flum and Grohe later refined that to the A hierarchy, and they both captures alternation between for all and existence in the definitions. And I'll skip the precise definitions, but what I'll instead want to do is just give you two example problems, just to give a little bit of the feeling of what happens. So here is an example of an A2 complete problem, where I'm given a graph and two integers, and this parameter are these two integers. And now I want to know, is there a set of k vertices S such that for every click of size L, this first set dominates this click. So basically, for every click of L vertices, either it has a vertex in this set or it has a vertex with a neighbor in the first set. So you see this alternation over for all and there exists here. And this problem, it's believed not to be in the W hierarchy, because you really need, I mean, if you want to think about it, you really need large certificates to write down solutions. And this is actually complete for the class A2. For the AW hierarchy, typical problems which fall there are what I would call short games. So games with few moves. So here's an example. I take a game, it's called Geography, and I play it on a graph. I have a start vertex and I have two players, and they alternatingly choose a vertex. And the rules are you have to choose a neighbor of the vertex which was chosen last, but you are not allowed to choose a vertex which has already been chosen. So you basically alternatingly build a simple path in the graph every time choosing the next vertex. And if you cannot choose a vertex, you lose the game. And you win, and then the other guy wins. So now the problem is there a winning strategy for the first player? And Now the question is, decide whether there's a winning strategy for the first player that uses at most k moves. And that is actually complete for the class AW1, which happens to be the same as all the AW2 and all the other AWs with an integer. So these are typical examples of problems complete for. There are some others with logic formulations, but this is a typical example of problems complete for this AW hierarchy. And finally, which is also interesting, there are actually problems complete for the class XP. And some of these examples are games with few pieces. And it basically, the idea builds upon an old proof from complexity theory that actually if you have an alternating Turing machine and the time of this Turing machine is logarithmic, the space, sorry, you have an alternating Turing machine which uses logarithmic space, then this has precisely the same computational power as just normal standard polynomial time. So P equals AL, you would say. And building on that, you can actually show that the following problem is complete for the class XP. It's what's called the pebble game. So I have a graph, and on some vertices of my graph, there is a chip. And I'm giving the chart starting set, so where some vertices have a chip or pebble. It's of course, because they have a pebble. And there's one vertex T, which is what we call the winning vertex. And now the players alternatingly move, and there's a set of rules. And every rule has 3 vertices. And if you have a rule X, Y, Z, then it means that if there is a pebble on X and a pebble on Y, but not a pebble on Z, I can move the pebble from X to Z. That's the game. And you win if you move a pebble to this winning vertex T, and you win if your opponent cannot move. So if you cannot move, you lose the game, and otherwise you win. Yeah. So this is the game. And now the question is there a winning strategy for the first player in this game? So you see here we have a very long alternation of for all exists. Is there a move for the first player? So it said for all moves of the second player, is there a move of the third player, and so on. And it can be very long because you can have lots of different locations. Because the number, the number of chips is a parameter, you can actually use a result which I think dates back to 1930, that you can just build a graph of all the different positions and then determine for all the positions whether they're winning or losing. This is really I think almost a century old technique to, and then in this case it's n to the k different positions in the game because I have k pebbles. So you see that the problem is an XP, but actually this problem is complete for XP, and means that so you really know for this question that you cannot solve this in polynomial time. Okay, so this is the last example I want to give, and I'll finish my talk now with my conclusions. So I believe I hope I showed you that that within XP there is actually a rich structure living with lots of different classes which capture different types of problems with different behavior. I hope I convinced you a little bit that this notion of XNLP completeness is interesting. And one of the reasons is that this XNLP hardness really implies that algorithms, XP algorithms for problems there, if you assume this slice-wise polynomial space conjecture, then they need much space. So it's XNLP hardness also tells you something about the space use of problems. But it's also, I think it's really interesting if you have a problem, not to show only hardness, but really to see for which class is this problem actually complete. Because it really, I mean, it's really much more clear pinpoints where the complexity of the question is. So this was I promised you some homework. But if you want, it might be nice to look at some of your results, and where you have W1 hardness or W2 hardness in your paper, think about whether you can actually lift that to hardness or completeness for a class higher up, for instance, like XNLP or one of these other things in these hierarchies. I think it's interesting to think about that and see if you can strengthen results in that way, and because it really improves the insight in how these problems are related and where they are. So I hope that I think that might be a nice thing to look at. So at the end, just a brief overview of classes. This is FPT has this time bound. W1 is basically you look at making k variables true, and then making a 3-set formula true. W2 is the same thing, but then you have just a formula in CNF, conjunctive normal form in the W hierarchy. So you have most of this classes W hierarchy, you have still Boolean formulas which are more general, but they all have this notion of k elements. You choose k elements from n. So XNLP has this definition, but it basically boils down that you have this dynamic programming algorithm with a linear structure where you basically have something like n vertices of your graph or k vertices of your graph. You have some function of k things in memory. Each of these things would probably cost log n space. So then you have this k log n memory, and that's basically XNLP. And it always, the structure of your dynamic programming is linear, but you also have this dynamic programming algorithms which have more a tree-like structure. And then you go to XALP. We have seen the M hierarchy where you have small inputs, the A and the AW hierarchy where there are alternations between for all exists. For instance, you have this for short games, and the XP has this running time bound, and XP complete problems are typically games with few pieces. There are not many examples there, but it's very nice if you really can show that something is XP complete. And then in the worst case, you have something which is para NP complete, which is then still like coloring, which is already complete for 3 colors. Then you're more or less out of luck. So that was still a little overview of all I told, and thanks a lot for your attention.
Thanks a lot for this beautiful talk. It really was a great survey on these complexity issues. So complexity is not my favorite topic, but I really got a lot of insight now. Thank you very much. And concerning the homework, so if we discover such W1 or W2 hard problems, so would it be also possible just to ask you, because it seems that you have a quick look on it and you've solved the problem already, while we must start thinking.
I would really be happy if you at some point, I mean, at some point, if you work with, I mean, they're always with a problem like this, there are 2 phases. The first is the intuition, and if you at some point worked with it, then I mean, I would be able to take a bet in many cases. So that's the first part. And then after that, there's the hard work. Yeah, which really, I mean, you need to really write. I mean, for bandwidth, for instance, it was like I mean, at some point, okay, yeah. I mean, I think it was 2 months before at some point I knew bandwidth is XNLP complete. It still took 2 months of hard work after to get all these reductions on a row, but yeah. But that's so that's for I would really be happy to work with. I mean, this is my current hobby. So if you want to discuss this with me, please contact me.
Thank you, wonderful. So at least guide our PhD students or postdocs. So there, Peter has a question.
Hello, Hans. So I am among the researchers who just know the first two and the last two lines of your overview of classes. But can you please recapitulate where the XNLP lies with respect to WP and with respect to the AW? Is it above or?
No, it's actually. It's I think besides it, because you can build something where you need more than logarithmic memory. In actually in WP, and I mean all the okay, very precisely for all the W1, 2, 3, X for all the integers.
Yes.
They are contained in XNLP.
Okay.
So XNLP hardness implies also W17 hardness for all the for WP and WSAT. I mean, you can formulate problems. I mean, you could, for instance, do a P-complete problem, which is where you believe that you need more than logarithmic memory, and then it doesn't fit in. So it's actually for the highest two of the hierarchy, it's separate.
Okay, so it's somehow aside or not known exactly.
Yeah, of course. I mean, there are things we believe for half a century to be true, but we still don't know, like whether logarithmic memory is actually where, for instance, L equals P. This is one of the questions. If you have logarithmic memory, can you actually do less than just, we believe you can do less than polynomial time, but I think it's not known whether these are different. And so, yeah, so based on well-known conjectures, they are different.
Yeah. Well, and how is it with AW? Well, I'm particularly interested in FO model checking, which is AW star complete. That's its class. So that's something harder than XNLP.
Yeah, that's a good question. I would believe so. I mean, we didn't work on that. I mean, still work to do.
Okay. Thank you.
Yeah.
And Hans, there is also one more question in the chat by Deba Jodi Mondal. I think we can go a bit over time because now there is the tea break. So people who want to go to the break, they can just do it, and the other ones can just.
Yeah. Okay. So actually, so the question, let me read it loud. Does the 2020 paper on W2 hardness on bandwidth is also for some simple class of trees, and does the parameter hair length play a role? Well, actually, we show that bandwidth is the XNLP complete, so also hard for all the classes WT for caterpillars with hair length at most 3. Yeah, and well, I should tell that actually the proof uses. I mean, there's this 1983 proof by Monin, and one of the I basically I took that proof and played with it, made something. But one of the gadgets is precise. I mean, I just basically precisely took one of the gadgets of Monin's proof. And you need this hair length 3 because you at some point you need to turn something around, and so yeah. So it's indeed hair length 3, and hair length 2 actually becomes polynomial. That's already known also for 40 years or so, but yeah.
Okay, thank you very much. So if there are no other questions, and because we are over time, then thanks again. It was really, I learned a lot, and I think many of us also. Thank you, Hans.
Okay, thank you for listening, and see you.
Okay, thank you for Professor Dr. Petra Mazel as chair and Professor Dr. Hans L. Botlander as the presenter. It's really very nice presentation. And then for around 15 minutes later, we will continue our agenda with the next session. So for this time, we will have a break. Thank you.
So Hans, maybe I can ask another question, or was there somebody else?
Well, I just spoke up. Sorry, Petra.
No, you can just start.
Yeah, there was one technical question I had to Garota actually. Are all speakers of the next session already there or something like that? Is this monitored, or because I'm chairing the next session?
Yes, I'm here.
But we can also continue a technical discussion on with Hans. So hi Hans, first of all, and maybe Petra should continue. Thanks, and I will maybe also continue then a bit.
I have the impression that everything is very good organized. The moderators, they do a very good job, and I think it will work.
Okay, good.
It's very good prepared, everything. Yeah. No, just a question to Hans again. What was the trigger that you started to write down the proof, or decided to go back and to write it down now finally after 30 years? There must be a trigger for that.
Yeah. Do you hear me?
Yeah.
Yeah, okay, because I went to my other screen now. Yeah, I think, I mean, it was I think the lockdown played here a role, because yeah, we at that point. So the other trigger was actually my birthday book. So I turned 60, and a number of people made the volume of the lecture notes on computer science dedicated to that, with a number of surveys. And there was the survey of Mike Fellows, and he wrote again about this bandwidth problem. And I know that, I mean, every time I see Mike, he asks me, Hans, when are you going to write down that proof? So at that point, and then there was this summer, and I was at home and basically had time, and couldn't. So yeah, and then I said, okay, now let's try it again. And then it worked, and finally I got some details slightly different, and I found this old paper by Monine again, and then there was this trick, and then, oh yeah, that's really nice and cute to use. And yeah, and so it was actually, it was a way of dealing with the lockdown as well. Yeah, and the trigger, the other trigger was the survey in the birthday book.
It's interesting that you seem to have more time during the lockdown, because in the very beginning it was also like this for me, but then there were lots of meetings starting, and now my week is full of Zoom meetings.
Yeah, that was the summer of 2020.
Yeah.
So I didn't have teaching in the fourth quarter of the of that year.
Mm-hmm.
And yeah, so that was, I mean, it was very quiet, and I didn't see anybody. So I thought, okay, let's write down.
Wonderful.
Yes, Hans, and if I got it right, the class that you call XNL is the same as Guillemot's class.
Sorry,
the class XNL you were describing,
yeah,
is the same as Guillemot's class WNL, right?
WNL is, No, it's actually the closure over of. Yeah. So actually, WNL. Yeah, I didn't mention that one. I mean it's actually forgot to put it in my survey paper as well, but it's the closure of XNL with parameterized reductions. So it means that actually you can cheat a little bit and put a problem where you use more than logarithmic space as well there. So they are slightly different. There's this, I mean, you have this, for instance, a strange example is take a problem which is XNLP complete, and then take the following. Now I have an input which consists just of two things. One is a P-complete question, and the other is your XNLP hard question. And do you say yes if both in both cases you say yes?
Okay.
That's of course a little bit cheating, but that one is actually in WNL complete, but not in XNLP because you need more than logarithmic space.
Yeah. Okay.
Yeah. So they're different. But in practice, it doesn't make a difference actually, because
I also think that Guillemot considered, for instance, this common superstring problems or whatever, which are, I think, both complete for XNL and WNL, something like that.
Yeah, I think many things are complete for both, but except when you have things where there's some incomplete question hidden in something where you need logarithmic. So if you the advantage of WNL is actually that you are allowed to use more space in your reduction, so you don't have to work so hard to, and you could do shortest path on a directed graph or things like that. You can use as a part in your reduction, which I mean, things which are you can't do, things you can't do in logarithmic space. So that's so there might be practical things. There might be practical some cases where there is a difference, but I don't have concrete examples yet.
Okay.
Yeah, I mean, this is all also quite new still. So still, I mean, I'm not finished yet researching this, and I'm really happy to work with people on questions here.
Yeah. I mean, I also have to look at this this new class that you proposed, because well, also because I noticed that these things are not really fitting within the W hierarchy. At some point, I introduced the class which I call WThink, because it's sort of the typical question is synchronization of finite automata, which you might not be knowing of. It's just a classical language problem.
Yeah, you take. Yeah, I think I saw that. Is that the, what was it? I don't know. I've looked at that. I actually, in an earlier version of a paper, I wrote a wrong statement about it. But
but then I also sort of wrote down some things where there's a couple of formal language problems which are FBT equivalent to this question, and so that might be that they also, because it's below WNL, that it might be also sitting somehow in your class that you introduced. I have to check.
Yeah, it might be an X. I think XNL or XNLP might be the right things there.
Yeah, maybe it's XNLP then. Yeah.
I don't know. It depends on how many steps you make.
Yeah.
In the automaton. But if you, maybe we can just share email about it at some point.
Yeah, would be nice.
And that would give me at least a few moments to think about it. I have looked at intersection of automaton at some point. But so it might be good to just send an email.
Yeah. Thank you.
Okay, so we have 4 more minutes until the next session starts. So
Okay, so thanks for sharing. And I'm actually now stepping on my bike and going to work.
Yeah, it's really early in the morning. Yeah.
Yeah.
Yeah, the
Now
opening-
it's only 8:45, so that's not so bad anymore. But
That's
we're also
true.
in Germany.
Yeah. The opening was at 3 a.m. yesterday morning, so I needed to get up very early.
Okay. Well,
Okay.
nice to see you. Bye.
Nice to see you. Bye.
Nice seeing you, Hans.
Yeah. Bye.
Bye-bye.
Bye, Jan.
So once again, a technical question. Is anybody giving me a signal when people are back, so to speak, to start?
Okay, we will continue our agenda today. And the next session is contributed talk session 7. There are 3 topics that will be presented in this session. So please be prepared for the next presenter. And for this session, will be led by Mr. Henning Fernau as the chair. For Mr. Henning Fernau, time is yours.
Yeah, thank you very much for the sort of opening of this session. And yes, I'm happy to announce, I think it will be Stephanie Maas who will give a talk on reconfiguration of atoms and their parameterized complexity. And this talk is joint work with Alexandre Cooper and Amer Mawad and Naomi Nishimura. And I just got a message in the chat of a hi from Amer and hi back. So, and now the floor is Stephanie's.
Thank you. Okay, so I start by giving a motivation for the problem. So the problem is motivated by one of the challenges that you are presented with when building quantum simulators. And to abstract away the physics behind it, imagine you are given a positioning of a set of traps. And then you are given a process that load atoms into those traps. But this process is flawed, so it results in a random and a non-desired arrangement of the atoms. What you are allowed to do to fix this arrangement is to move an atom along a connected series of traps as long as those traps are empty. The problem that lies here is that there is a survival probability that is associated with the atom. So the probability, the survival probability decreases as whenever you move the atom. So a reasonable goal would be to minimize the total number of moves of atoms. It's easy to see that this problem can be abstracted to become a problem on graphs. So you can think of the traps as vertices of the graph. We can think of atoms inside the traps as tokens that are placed on the vertices. And also the concept of adjacent traps can be easily ported using edges of the graph. In fact, this problem falls under the reconfiguration framework. So already Professor Hans Bodlander gave a very nice introduction about parameterized complexity, and he also mentioned reconfiguration problems. I'm going to give some definitions that are under reconfiguration that are exactly adapted to our problem. We call a configuration a set of vertices that represent the placement of the tokens in a graph at a given time. And we define a move to be a displacement of a single token along a path of 3 vertices, which are vertices without token. Then what we are interested in doing now is to find a sequence of move so that we can form the target configuration from a given source configuration of a graph G. And throughout this presentation, we assume that the sets S and T are always equal size, not equivalent. So now we define the token moving problem. What we are looking for is the question, can we find a transforming sequence that has size length at most L? We look at 4 variants of this problem, mainly when the underlying graph is either directed or undirected. We also look at the case where we call it labeled versus unlabeled case. And this is when the tokens are distinguishable or indistinguishable. All 4 variants of this problem are NP-hard. Therefore, we look for parameterized algorithms for these problems. And so to summarize what are parameterized algorithms and what's parameterized complexity, so whenever you think of a parameter that whenever you have a problem and you think of a parameter or a set of parameters that are relevant to this problem, and you try to design an algorithm that solves the problem in some function of the parameter or the parameters times polynomial size in the times some polynomial function in the input size, then this becomes a parameterized problem. And the intuition behind it is that you are trying to design an algorithm that puts all the blame or all the load on the parameters. So whenever your parameter is small, you get some reasonable running time. And if you are able to find an algorithm that has such a runtime, the problem becomes fixed parameter tractable, and it belongs to the class FPT. And similar to the notion of P and NP hardness, we can show that we think it's highly unlikely that a problem has an algorithm with this running time by showing it's W1 hard or W2 hard. Now, instead of always thinking as the representation of the source configuration and the representation of the target configuration as 2 separate graphs, we can combine those 2 into one color-coded graph that represents all the information we need and all the sets that we care about. So besides the sets S and T, we define the set O, which is, we call it the set of obstacle vertices. And those are the vertices that are simultaneously in the source and the target configuration. We also will look at the set T minus S and S minus T. Finally, we define the set F of free vertices, which are the vertices that are neither in the source nor in the target configuration. Now, below are the results that we show in the paper, mainly under the unlabeled variant of the problem. For most of the parameter, the problem is in FPT. This is not the case for the labeled variant. Also, if we look at the parameter where, if we try to parameterize by the number of obstacles that will participate in moves, then the problem is W2 hard under all 4 variants. I will give an overview of the algorithm for the unlabeled, undirected token moving problem when the parameter is L. And for that, I will need a lemma that will also easily show that the unlabeled variant is an FPT when parameterized by K. So we will start by thinking only about the parameter K at first. And we have a very famous technique in designing parameterized algorithms, that is kernelization. And we start from there. We ask ourselves, can we build, given an instance, given an unlabeled instance, build a smaller size instance, such that those 2 instances have the same length of their shortest transforming sequences, and we call these instances equivalent instances. And the intuition here is that if we can, from a given instance of an arbitrary size, build a smaller instance, then we can afford to run any slow exact algorithm on the smaller instance. So, and the first thing we think of removing from the graph is the free vertices in the graph. And note that if we remove the free vertices from the graph has size, will have size at most 2K, where K is the number of tokens. So we proved that we can actually remove those free vertices by proving the following lemma. We showed that under the unlabeled variant, in a minimum length transforming sequence, no token has to move more than once. And we proved the result by contradiction. So we assume that this is not the case. We have an instance where all shortest transforming sequences move some token, at least 1 token more than once. And we pick one shortest transforming sequence that minimizes the distance between the first and the second move of the same atom. And what we do is we try to build a new sequence. We look at this specific subsequence and we build a new subsequence that has 1 less move. But applying our original subsequence or this subsequence will result in the same configuration. Therefore, we have showed that what we started with is not a shortest transforming sequence, thus a contradiction. What this lemma implies is that inside our shortest transforming sequence, we will never have a token move into a free vertex, sit on it for a while, and then move again into another vertex. So, so this means that the only role a free vertex can play in the graph is to connect its neighbors. Thus, I can, under the unlabeled variant, I can remove those free vertices and connect their neighborhood in an appropriate manner, depending on if it's directed or undirected. And I get a small instance, basically something that has size at most 2K, and we call this instance a contracted instance. Now from here, we can directly show that the unlabeled variant is fixed parameter tractable, because we already know that free vertices will not participate in moves. So we only have to choose from 2 up to 2L vertices from the source or target configurations, pair them as sources and targets of moves, order the moves, and test in polynomial sign whether the form sequence is actually a valid transforming sequence. Basically, we can brute force. So now we are ready for the parameter L. And before that, I will need to define a graph called G of alpha for a transforming sequence alpha. And the idea is, if you have a representation of the source configuration on the graph G, then if you remove the parts from this representation that are not used by the sequence of moves in alpha, you get the graph G of alpha. And note that in this graph, every token that appears participates in at least one move. Otherwise, we would have removed it from the graph. So now we show that given a contracted, if we start from a contracted instance, then any transforming sequence of minimum length, at least one transforming sequence of minimum length will have G of that sequence be a forest. And the way we show that is we will assume that this is not the case, that for some instance, all shortest transforming sequences alpha will have G of alpha containing a cycle. And we pick any such sequence. And what we do is we look at the subsequence, we call it beta, between the first move in alpha and the move that forms the first cycle. Oops, sorry. Yeah, and the move that forms the first cycle in G of alpha. So in this graph below, this move is the move from S to T, and it is the parts that are added by this move are the dotted lines. So now we look at the graph G of beta. And we already said that in G of alpha or G of any sequence, every token moves at least once. But also we know that beta is part of the shortest transforming sequence. So we know that, and we know that from a previous lemma that in the shortest transforming sequence, every token moves at most once. So we know that in G of beta, every token moves exactly once. So looking at G of beta, we can directly conclude the number of moves that are the number of moves in beta by just counting the tokens that appear in G of beta. What we do is we build from G of beta a forest of trees that have equal numbers of vertices in the source and the target configuration each. So we show that we can ignore some parts of the graph that were introduced by the last move, mainly the parts that are here highlighted in red. And now we have a forest of trees where in each tree the number of source and target vertices are the same. And we have a result that states that on trees we can find for any instance of the unlabeled undirected token moving in linear time the minimum length sequence. So if we only run this algorithm on the trees that we have, we will get a minimum length sequence in which each token will move at most once. Thus, we will get another subsequence, beta prime, that will only use edges of a forest, but will result in the same configuration. And this way, we remove the first cycle from alpha. So now we repeat for the next cycle, in alpha until we build a sequence alpha prime that doesn't where G of alpha prime doesn't contain any cycles. Finally, we showed that also that this forest for the minimum length sequence, this forest is a forest of minimum Steiner trees where the terminals are in the symmetric difference between the sets S and T. And given this lemma, we can now prove that the problem is fixed parameter tractable. So we showed before that we can remove free vertices and form a contracted instance, and we do this. We also showed that alpha for the minimum length sequence alpha, G of alpha is a first of minimum Steiner trees. So we will attempt to build the G of alpha. And we do this by trying all possible partitions of vertices in the symmetric difference of S and T into 1 up to L Steiner trees that have equal number of vertices in T minus S and S minus T. And we can only try up to L Steiner trees because each tree will contribute at least one move. And finally, we showed that in G of alpha, every token moves at least once. We have this algorithm that finds the minimum length sequence on trees. Thus, we can conclude that the number of moves that will be associated with each forest will be equal to the number of tokens that appear inside the trees. And we basically, for each possibility, we count the number of tokens that appear, and we check if it's less than L or not. If we find one that is less than L, then this is AS instance, otherwise it's a no instance. So we have also other challenges that are present in this process, in the process of building quantum simulators. And those include that under certain conditions, we can move the atoms simultaneously. Also, the survival probability of the atom decreases due to also because of the distance the atom travels, not just the number of moves. So other reasonable open questions that we have is, can we find efficient approximation algorithm for this problem? And can one incorporate the movement of atoms in batches subject to a given set of physical constraints? Thank you.
Thank you very much for your nice presentation. And yeah, are there any questions to repeat or to read out from the last slide? Maybe can you sketch once more in 1 minute or something like that? You motivated your whole thing with quantum computing. And so these FPT results, what do they mean in this context?
Okay, so like some parameters are we got them while looking at the parameter K. We got the result while looking at the parameter L, and what the parameter L means is that this the survival probability of the atom is also depends on the passage of time. So sometimes they are looking for like a very small sequence of moves. So that's why we think that L would be some small parameter. And this is why we started by thinking about the parameter L. Mm-hmm. Also, like L plus F, we got it also like because of the parameter L. So mainly what we looked at is the parameter L and the parameter that is the number of optional moves. Those that are we are not sure they will participate in the sequence of moves.
Okay, thank you. Yes, and thanks again for your nice contribution. And I think we should move forward to the next talk. And the next talk is probably presented by Adele. Is this correct?
Yes, I'm here.
Yeah. Okay, fine. So Adele Reginho will give a talk co-authored by Gennaro Carrasco and Luisa Gargano, and it's about parameterized complexity of immunization in the threshold model. Looking forward to it. The floor is yours.
Okay. Can you see the slide?
Yes, everything's fine. Everything's fine.
Okay, thanks. So in this paper, we studied the parameterized complexity of immunizing a network. In particular, we consider the problem of controlling the spread of harmful items in networks, such as the contagion proliferation of diseases or the diffusion of fake news. Here, the goal is to try to limit as much as possible the spreading process by adopting immunization measures. One of such a measure consists in intervening on the network topology by either blocking some links so that they cannot contribute to the diffusion process, or by immunizing some nodes. In this paper, we focus on this second strategy. So we studied the problem of limiting the spread to a small region of the network by immunizing a bounded number of nodes in the network. We studied the problem in the linear threshold model introduced by Kemp in 2003. And in this model, each node has a threshold measuring the node resistance to the diffusion. And a node gets contaminated if it receives the item from a number of neighbors that is at least equal to its threshold. In this model, the diffusion proceeds in rounds. So initially, only a subset S of nodes has the item and is contaminated. And at each round, the set of contaminated nodes is augmented with each node that has a number of already contaminated neighbors that is at least equal to its threshold. Since we want to select nodes to be immunized, we represent the network through a graph consisting of the nodes that can be immunized. So we select only the nodes in the network, all the nodes in the network, except for those in the spreader set S. Here, the threshold, the T of U of a node is equal to the original threshold of the node, decreased by the number of its neighbors in the spreader set S. Furthermore, given a set Y of nodes that we want to immunize, the diffusion process in presence of this set Y of immunized nodes is the sequence of the node subset DGY1, DGY2, and so on, where DGY1 is the set of the nodes initially contaminated by the spreader set S. That is the nodes in V minus Y having threshold 0, and so the nodes that initially are contaminated by the spreader set S. And where DGY tau, that is the set of nodes contaminated at round tau, is the set of nodes contaminated at round tau minus 1, added with all the nodes in V minus Y, having a number of neighbors among the nodes contaminated at around tau minus 1 that is at least equal to its threshold. Well, the process here ends when no more nodes can be contaminated. And we denote by DGY the set of nodes that at the end of the diffusion process are contaminated in G when the nodes in Y are immunized. As an example, consider this graph where the red node, where the red numbers are the threshold of the nodes. If no node is immunized, then initially and then at around 1, only V1 and V5 are contaminated since they have a threshold 0. Then at around 2, node V3 is the only node that is contaminated, having threshold 1 and 2 neighbors contaminated. Then at around 3, nodes V2, V4, and V6 are contaminated. And finally, at round 4, the whole network is contaminated. But if we choose to immunize node V3, then only V5 and V1 can be contaminated in G. So the influence immunization bounding problem that we have studied in this paper asks, given a graph G representing the nodes that we want to immunize, that can be immunized, and a threshold assigned to each node, and to integer k and l, the problem asks if it is possible to limit the diffusion to at most k nodes of the network by immunizing at most l nodes. This means to find a set Y of nodes that we want to immunize, whose size is at most L, and such that the size of the sets of contaminated nodes in presence of Y is at most K. Well, we have studied this problem. We have studied the parameterized complexity of this problem, or influence immunization bounding problem. And we have considered several parameters. Some of them are associated to the input. For instance, the bounds K and L, the number zeta related to the initially contaminated nodes, so the nodes that have threshold 0 at the beginning. And also we have considered some other parameters that are related to the underlying network, such as the maximum degree, the tree width, and the neighborhood diversity of the graph. And we have proved that the influence immunization bounding is W1R with respect to any of the parameters, K, tree width, or neighborhood diversity. And it is also W2R with respect to the pairs L and delta and L and zeta. On the positive side, we also have presented FPT algorithms with respect to any of the pairs K and L, K and zeta, K and tree width, delta and tree width, K and neighborhood diversity, and finally L and neighborhood diversity. We now present the idea that is behind two of these results. In particular, we now consider an hard result and a positive result. Okay, the first result that we present regards the W2 hardness of the influence immunization bounding problem with respect to the parameter L, even when the maximum degree of the graph is at most 3. Recall that L is the bound on the sides of the immunizing set. Well, we give a reduction from the eating set problem, which is W2 complete in the size of the eating set. And in the eating set problem, we have a collection S1, Sm of subset of a ground set A with elements A1, A2, An, and a positive integer H. And the problem is to find a subset H of the ground set that intersect each set in the collection and whose size is at most H. So starting from a eating set instance, we construct an influence immunization bounding instance. Well, traditionally, given a eating set instance, a bipartite graph is constructed that has on one side a node for each element in the ground set, and and on the other side, a node for each set in the collection. And then an edge is put between an element and a set if the element is in the set. Since we want to limit the maximum degree of a node to 3, we add the two auxiliary sets of nodes, W and U, and they will be used to keep the degree bounded. In particular, we introduce an expansion gadget that connects each AI node with the W nodes, and in particular, node AI is connected through a path to the W nodes representing AI in each of the sets who AI belongs. So the size of W is at most n times m. We also introduce another gadget, namely the reduction gadget, that connects the W nodes to the U nodes and finally to the S nodes, so that a node Sj is connected to the W nodes representing the A elements, that is the elements in the ground set belonging to it. And this is done through the U nodes. So also in this case, the size of U is at most n times m. Finally, we add a path of length n plus 2n times m to each node Sj. To complete the reduction, we assign the threshold. And we assign threshold 0 to the nodes in the ground set, to the nodes corresponding to the elements in the ground set. Then we assign threshold 2 to the U nodes and threshold 1 to all the other nodes in the networks. That is the nodes in W, the S nodes, and all the nodes in the paths attached to the S node. Well, by this construction, it's easy to see that each node has a degree at most 3. Furthermore, we can note that there is a path from AI to each of the sets who AI belongs. And considering that, considering the threshold we have assigned to the nodes, we have that if we immunize node AI, then all the nodes in the path starting from AI cannot be contaminated. And this has to prove that the eating set instance has an eating set of size at most h, if and only if the influence bounding, the immunization influence bounding instance has immunizing set Y of size at most H, and such that the number of nodes that can be contaminated in presence of the nodes immunized in Y is at most n plus 2n times m. Well, we now present an FPT algorithm for the influence immunization bounding problem with the parameter L and the neighborhood diversity of the graph. Recall that L is the bound on the sides of the immunizing set. Well, we first of all, we given a graph G, we compute the neighborhood diversity and the OG, and so we have the type partition V1, V2, V, and D OG. Recall that in a type partition, each set in the type partition can be either a clique or an independent set. Furthermore, the nodes in a type set, that is one of these sets, share the neighborhood. And also two type sets are connected, where are connected when there is a complete bipartite graph between the nodes in these two sets. Then our algorithm proceeds as follows. For each tuple, H1, H2, H, and D, such that the sum of these components is at most L, we construct the candidate set Y. This is done by selecting from each type set VI HI nodes, and in particular we consider the HI nodes in VI with the smallest threshold. Then the set Y is just the union of these selected nodes. After that, we consider the diffusion process in G when the nodes in Y are immunized. That is, the nodes in Y are removed from G and the diffusion process starts. And so if we obtain at the end of this diffusion process a set of nodes contaminated that are at most, then we return Y. Otherwise, a new tuple H1, HND is chosen, and the algorithm goes in this way. Well, by using the properties of the type partition V1, V, and D, we are able to prove that if the answer is no, that is, no set is returned, then no immunizing set of sites at most L exists, able to limit the diffusion to at most K nodes in G. Finally, consider the running time of this algorithm. First of all, consider that the number of tuples H1, H, and D that we have, that are, the algorithm considers, who's characterized by the fact that the sum of its components, of the components, are at most L. Well, this number is upper bounded by 2 to L plus ND minus 1. And also consider that in each iteration of in each of these iterations, we construct the set Y, and this requires time of H. And also we construct the set DGY, that is the set of the nodes that can be contaminated, and this can be done in time of n squared. So overall, the full time of this algorithm is O of n squared times 2 to L plus ND minus 1. And this completes the talk. Thanks a lot.
Yeah, thank you again for this nice presentation. And yes, are there any questions from the audience? And please just speak up. I don't know if I see everybody at once. Maybe one silly question. Do you have any examples where the relation between L and ND is kind of arbitrary?
LN?
Why I'm between, you have this double parameter, L and ND, this combined parameter of L.
Okay. ND, do you mean the neighborhood diversity, right?
The neighborhood diversity. And
yes.
Because at the very end, you have this sort of, you say, proof how you derive the running time of the FPTR algorithm, right?
Yeah.
And there, of course, if you knew anything about the relation between L and ND in some sense, you might get better bounds or from the summation formula you had on this next slide, I think, or wherever it was.
This one.
Yeah, this one. Yeah, because I mean, you sum up only to L, and if you know that ND is much bigger than L or something like that, then this is just
which
small.
relation there is ND depends on the graph. So on the structure of the graph.
And L not.
So L, you can choose L as you want. Try you choose L small such that you can find eventually a time that is small. I mean, in the way that 2 to L plus ND minus 1 is small, but you can choose L as you want. There is no there is no a clear relation between them.
Yes, but if you know, for instance, that ND is very small, you might be able to do something different, and then maybe so just a win-win approach. And if ND is big, then you might gain from the fact that you don't sum to something dependent on ND, but just dependent on L. So you might, I see a little bit the possibility to have a win-win approach there to get better running times.
Yeah, you're right. Yeah, yes.
But anyways, maybe we are a little bit over time anyways. So is there any remark or question from the audience? If not, then thank you again for your presentation. And we'd like to switch over to the last talk, which is on parameterized complexity of minimum membership dominating set. And I'm not 100% sure who's the presenter, but maybe the person
myself,
can
Nisha,
just.
sir.
Yeah, it's
And
you.
I'll be presenting that.
Okay, very nice. So Anisha, I see. This is joint work with NS money. Oh, sorry. Maybe you should introduce.
Yeah, sure. Yeah.
Because maybe it's easier. But yeah, please go ahead. Thank you.
So hello everyone. Myself Nisha, and the topic is parameterized complexity of minimum membership dominating set, and it's a joint work with Akanksha Agrawal, Pratibha Chaudhary, NS Narayanaswamy, and Vijay Raghunathan Ramamurthy. So we all know that a dominating set problem, given a graph G and a positive integer K, we have to find a subset of at most K vertices such that for every vertex in the graph, it is either in that subset or it has a neighbor in that subset. And we like dominating set, and many of its variants have been deeply studied in the literature. And we are now focusing on some variants which are the solution is constrained by the neighborhood size as well. For example, we have this perfect code where if you are given a graph and an integer K, we have to find a subset of at most K vertices such that S is an independent set, and for every vertex outside the set, it has a unique neighbor in this subset. And similarly, we have a sigma row dominating set where sigma and rho are subsets of natural numbers, and you have to find again a subset of at most K vertices such that for every vertex in this subset, the number of neighbors it has in this subset is from sigma, and for every vertex outside the set, the number of neighbors it has is from rho. And there is this ij dominating set where I and j are integers, and we have to find a k-sized subset of vertices such that for every vertex outside this subset, the number of neighbors it has in this set is at least I and at most j. And we can see that in all these variants, they are trying to optimize the solution size along with this additional constraints. And then like in our problem, we are trying to optimize the membership where membership of a vertex in a set, membership of a vertex related to a set is the number of number of neighbors in the closed neighborhood it has on this set S. And we adapt the notion of membership from the minimum membership set cover problem. And then we formally define our problem. We call it minimum membership dominating set, or MMDS in short, where you're given a graph and a positive integer K. We have to find a dominating set S such that for every vertex, the membership of V is at most K. That means for every vertex in the graph, the number of neighbors it has in the dominating set is at most k. And we have to emphasize that there is no, we are not considering the size constraint. We are only trying to optimize the membership of every vertices. And we study this problem, and our results are, we prove that it is NP hard on even on bipartite planar graphs for k equal to 1. And W1 hardness for the problem is proved for the parameter path width. And it is for the parameter k, it is W1 hard on split graphs. But then on the positive side, it is FPT for the parameter vertex number. And vertex scar number parameterization, we also give a lower bound for the same. Okay. We'll move on to the NP hardness part. It's a simple reduction from planar positive 1 in 3 set to MMDS, where we are given the instance of planar positive 1 in 3 set. We have n literals here and m closes. So each of these clauses, the condition is that you have to find a satisfying assignment such that each clause is satisfied exactly with one literal. So if you are given the incident graph, it will have a planar embedding. So we construct our graph for the MMDS problem, where we replace the clauses using some vertices. All the CIs represent the corresponding clauses, and we do have the vertices corresponding to the given literals, and we give n more vertices. We call it xi caps and attach the xi's with corresponding xi caps using an edge. Now we go for the reduction. Suppose we have a solution for the planar positive 1 in 3 set problem, where x2 and x5, they basically satisfy all the clauses exactly once. And here we construct a solution for MMDS in our graph by selecting the same like the corresponding corresponding literal vertices, and for the other, like, you know, so we can see that they dominate the closed vertices exactly once, and for the pendant vertices we just take the remaining pendant vertices into the solution. And for the reverse direction, we can just observe that we cannot take any of the closed vertices into the solution, because we take them in order to dominate the pendant vertices, we may have to pick any of the xi's and xi caps, which will violate the membership property for the literal vertices. Therefore, the solution will be a subset of the literals, that means xi's and xi caps, and we select the solution accordingly so that all the closed vertices and other vertices are dominated exactly once. And we can map the solution onto the original problem so that the literal variables or the literals corresponding to the vertices can be assigned one for a satisfying assignment. And we can move for the W1 hardness for path width. And here we do this using a reduction from the problem multicolored click, where we are given an instance of multicolored click problem, and we construct an MMDS. So the multicolored click instance has got a graph G and K, which is the click size, and we have we'll be constructing graph H for the MMDS problem with parameter K prime, or membership parameter K prime. We'll see what it is. Suppose this is the multicolored click instance which is given. The graph has k vertex partitions, where each of the vertex partition has are independent sets, and we need to find a k-sized click such that a vertex, exactly one vertex, is selected from each of these vertex partitions. And we, without loss of generality, we assume here that each of the vertex partition has n many vertices. And we now construct our graph. This is a higher level overview of the graph H which is constructed. Here, for every vertices, we give a block, and for every edge sets between these vertex partition, we give another block. Okay, so the green ones represent the vertex partition block, and the blue ones represent the edge sets between the vertex partitions. So we can just see that H1 stands for V1 here, and H12 stands for the vertex partitions, or sorry, the set of edges between V1 and V2. Okay, once the blocks are given, we connect them using some connector vertices. And here we are trying to see, that if there is a solution for the multicolored click instance, then we have a we have an MMDS problem for K prime equal to n plus 1. Now we move into the details of the construction of block. So for construction of block, we use gadgets. The picture which is shown is our basic gadget. We call it a D gadget, where the blue colored vertices are termed the heads of the gadget. U and V are connected to each other, and also they are connected to some n plus 2 independent vertices. And we claim that for any solution of MMDS in this graph, either U or V must be there in the solution, and the path width of this gadget is 2. And using this D gadget, now we construct our primary gadget I. We call this I gadget. So as we can see, there are 2 different sets of vertices A and D, and 2 other vertices H1 and H2, where each of this A and D has got n many vertices. Now each AI and DI, they are connected using a D gadget, and we represent that using a red line for the sake of simplicity. And now here comes our complete construction of the I gadget, where all those vertices in the set A are connected to H1 using an I gadget, and all the vertices in D are connected to H2 using an I gadget, and the black lines, they indicate direct edges. So this is our primary gadget. So we use this gadget for every vertex and every edge in the original instance for multicolored click. Now once we claim that either the complete set A along with H2 or the complete set D along with H1 must be in the solution for MMDS with membership equal to n plus 1. And path width of this gadget is proved to be 4. Now we come to the construction of block, where as we've already seen that there is blocks for the vertex partitions and edge partitions separately. Like we are going to look at the vertex partition block currently. So as we can see, there are n many I gadgets representing the n many vertices in each of the vertex partitions, and we have highlighted the A set of vertices in each gadget. They are connected to a vertex F, where F is again connected to another vertex F prime. F prime getting connected to n plus 1 C vertices, where each of the CAs are again connected to n plus 2. So this is pendant vertices which are n plus 2 in number. Now we can see that for any solution, the complete set C1 to Cn plus 1 must be then in the solution, because otherwise we need to include those pendant vertices which will violate the membership property. And by the same argument, we can also say that F prime and F cannot be present in any of the solution, because selecting any of them will violate the membership property for F prime. Therefore, F prime is getting dominated with C1 to Cn plus 1, but F is not getting dominated. So in order to dominate them, we have to select exactly one A set from a unique gadget. So there will be a unique gadget here such that there will be the complete set A will be there in the solution, because if we take more than one A set from different gadgets, then it will again violate the membership property for F. So here, this is for the vertex partition block, and for edge partition block, it's the same, with only difference in the number of eye gadgets, because the number of eye gadgets will be the same as that of the number of vertices from any vertex partition Vi to Vj. The rest of the construction are the same, and now we'll see how do we connect these blocks. So we introduce 4 vertices each for every pair of vertex partition, namely Siij, Riij, Sjij, and Rjij, and we connect, like for suppose there is an edge from X to Y, there's an edge XY from say Vi to Aj in the original graph. Then in Hi, we'll have a gadget which represents the vertex X, we call it Ix. So in the A set of vertices, we connect the A1 to AX to Siij and the remaining vertices to Riij. And we do the same thing for the other partitions as well. Okay, so now this completes our construction of graph H. And the path width of this graph will be based on the number of connectors, which is a polynomial in K. And when there is a, and we prove that if there is a solution for the multicolored click problem, if there is a click there, then we can construct a solution for the MMDS problem with K equal to n plus 1, the member shape equal to n plus 1, and vice versa. Like if there is a MMDS solution with n plus 1 membership n plus 1 here, then we prove that for the multicolored click problem, we have a solution, like the selected vertices form a click. And for the next set of results, I'll be just giving an overview. MMDS is proved to be W1 hard on split graphs for the parameter K, and we are doing the reduction from multicolored independent set to MMDS, where given a graph and K, the instance of multicolored independent set, we construct a split graph H with K prime. K prime is same as that of K exactly. And we construct a graph like this. The dotted portion gives the click side of the split graph, and the other vertices gives the independent vertices. And we prove the reduction. And when we call it as FPT, when parameterized by the vertex car number, we give a reduction from the minimum membership dominating set to the integer linear programming, and we such that the number of constraints in this ALP instance is at most twice the number of minimum vertex car. And as it is FPT when parameterized by the number of constraints, we say that like MMDS is FPT by vertex car number as well. And vertex car lower bound, we prove that there is no sub-exponential time parameterized algorithm for MMDS when the parameter is a vertex car number, unless the exponential time hypothesis fails. And for this, we give a reduction from the 3-SAT problem to MMDS. And if there is a solution for MMDS in sub-exponential time, then we prove that there is a sub-exponential time algorithm for finding 3-SAT. And unless it fails, this is not possible. And on concluding remarks, we have seen that we have proved many results on the hardness, W1 hard for the parameter path width. It is for the parameter K, it is W1 hard on split graphs, and it admits an FPT algorithm for the parameter vertex car, and also we give a running time lower bound. Now on the open problems, can we on other graph classes we can analyze the parameterized complexity of MMDS problem, And also we can do for other parameters like FVS number as a candidate. And also we can go for designing an exact exponential time algorithm. Yeah. Thank you.
Yeah, thank you, Nisha, for this nice presentation. And of course, are there any questions or remarks to Nisha's talk? And again, please just speak up. I think it's easier before I try to find somebody raising his or her hand. You might have to unmute yourself first. Well, if there are no other comments, then maybe one little remark connecting again to Hans's invited talk. Do you know anything about membership in any of the W classes, for instance? We use through, for instance, this W1 hardness with respect to path width, but is there also a membership result for W1? I would doubt, at least in this context.
Actually, we haven't found the membership results on the actually in W1 ring, and basically we have two problems which deals with membership, which are minimum membership set cur and hitting set problems, but they are not studied in terms of parameterized complexity. It's for the best of our belief, it's like that.
Okay. Well, any further remarks or questions? Okay, so then there's one small remark in the chat. So then let's thank the speaker of this session again, all of them. And we will now switch to the invited talk. And I think Petra is now taking over. Is this the case?
Okay. I think I'm ready to take over the session. Thanks, Professor Henning for now. Yeah, and welcome to the third or last invited talk session. This invited talk will be delivered by Professor Takehiro Ito. I hope Professor Ito is here. Yeah, and the title of his talk is Invitation to Combinatorial Reconfiguration. And before Prof. Ito present the talk, please allow me to introduce him. And Professor Takehiro Ito is a distinguished researcher of Tohoku University. He is head of investigator of the project Fusion of Computer Science, Engineering and Mathematics approach for expanding combinatorial reconfiguration. And Professor Ito got a PhD in information science from Tohoku University in 2006 under the supervision of Professor Takao Nishiseki. Yeah. And from the same year, he is working for Tohoku University as an assistant professor, an associate professor, and currently a full professor since 2020. He is working on graph algorithm and received 17 awards, which is huge awards, yeah, and fellowship, including the Young Scientist Prize, the 2018 commendation for science and technology by the Minister of Education, Culture, Sport, Science and Technology, Japan, and the Best Paper Award of ISAAC 2008. And he has been named in 2020, 2022 Distinguished Researcher of Tohoku University. He is currently leading 3 years project on combinatorial reconfiguration in Japan, which is the topic of today's talk. Okay, please join me to welcome Professor Takehiro Ito. Professor, the time is yours now.
Yeah, thank you. Thank you for your kind introduction. And it is my great honor to give this invite talk in WALCOM. So I'm Takehiro Ito from Tohoku University, Japan. So today, I'd like to talk about my favorite topic, computer reconfiguration. So and this is a talk outline today. And let me start with a definition of computer reconfiguration together with motivation. So the most familiar example of computer reconfiguration appears in sliding block puzzle. So such as 15 puzzles and Sokoban and rush hour and so on. Like this, yeah. And for example, in the 15 puzzle, we are given an initial board state where tiles with numbers from 1 to 15 are given on a board. And we are asked to find a procedure of sliding tiles from the initial board state to the target board state. So in each step, we can slide a single tile to an empty spot. So here is an empty spot, and we can slide only a single tile to the empty spot. Then, so here is an empty spot. And so by repeating this procedure, so we want to reconfigure the initial board state to the target board state. So there are 15 tiles and 1 empty spot, and hence the number of possible board state is factorial of 16, which is approximately 10 to the 13th power. Among such a large number of possible board states, we need to find a procedure of sliding tiles from the initial board state to the target board states. So this is a typical example of computer reconfiguration. Another example of computer reconfiguration appears in 24 hours, 7 days service systems, such as power distribution system, mobile network system, and so on. For example, consider a power distribution system. Power distribution network have many feasible configurations so as to deliver electricity even when some trouble happens. If we find a better network configuration, we want to change the current configuration to the optimal one. However, due to the electricity conditions, we cannot change directly from the current configuration to the optimal one, but need to change the switch configuration in some sense one by one. Of course, we cannot cause any blackout even during the transformation, and all the electricity conditions must be satisfied even during the transformation. And I'll explain later, but there is a benchmark data for standard model of Japanese power distribution networks, and it is known that the benchmark network has, we want to try to reconfigure to the optimal configuration. And there is a benchmark data for the Japanese standard distribution network. And there is a huge number of possible configurations. So 10 to the 53rd power. So many. Among such a huge number of possible network configurations, we need to find a switching procedure from the current configuration to the optimal one. So in both situations, we wish to find a procedure for transformation over the state space. So computer reconfiguration is an algorithmic study on procedures for transformation. So more theoretically, computer reconfiguration asks the reachability or connectivity of the state space. A typical search problem asks the existence of at least one feasible solution in the state space, while reconfiguration problem asks the reachability between feasible solutions. So for example, consider the most fundamental problem, namely the satisfiability. In the standard SAT problem, we are asked to check if there exists at least one feasible solution, namely a satisfying truth assignment of a given SAT formula from 2 to the n candidate of solutions for n variables. So for in this example, for example, 001 is a satisfying truth assignment for this SAT formula. And hence, the answer is yes for this typical SAT problem. On the other hand, in a reconfiguration problem for SAT, we first introduce the adjacency relation defined on feasible solutions. For example, as an adjacency relation for SAT, we may choose Hamming distance 1 that is a flip of a single variable. So there are several variants of reconfiguration problem I'll explain later, but here, suppose that we are given two satisfying truth assignment. So initial and target one, like this example. And then we are asked the existence of a sequence of adjacent feasible solutions among 2 to the n candidate of solutions. So please note that although we have initial and target solutions as input, we do not know the feasibility of the other 2 to the n-2 candidate. So we only know these two solutions, and we don't know the feasibility of the other solutions. So in this example, there is a path from initial to the target like this. As another example, consider graph coloring. In the typical search program, we are given a graph and an integer k, and asked to check if there is at least one proper coloring for the graph using k colors like this. On the other hand, in a reconfiguration problem for graph coloring, we first introduce an adjacency relation on graph coloring. There are several ways to define, but so for example, regarding a single vertex at a time. Then we are asked the existence of a sequence of adjacent proper graph coloring between two given colorings. So state space can be seen as a graph called a solution graph. The node set of the feasible solution, the node set of the solution graph is a set of all feasible solutions for base search problem. Such as satisfying truth assignment or proper graph colorings. The edge set of the solution graph can be defined by introducing adjacency relation on feasible solutions, such as Hamming distance 1 or regarding a single vertex at a time. The adjacency relation may be defined by application, or if there is no clear application, then we may choose the most elementary change to solutions. Anyway, there is no clearly stated rule for the choice of the adjacency relation. So for example, more than one adjacency relation have been studied for the independent set reconfiguration. So recall that an independent set of a graph is a vertex subset such that no two vertices are adjacent. In this talk, we regard a token coin is placed on each vertex in the independent set. So in this example, we have 3 coins, 3 tokens, and placed on these yellow vertices. As a feasible solution, we take all independent set of size exactly k, and as an adjacency relation, we choose moving a single token at a time. Then, for this initial target independent set, we have a reconfiguration sequence like this. So we first move this token to above and obtain another independent set, and then move this token to the left side and obtain another independent set. And finally, we move this token to this vertex, and obtain a target independent set. So this program is called the token jumping because we can move a token to any vertex as long as it results in an independent set. On the other hand, token sliding takes another adjacency relation such that we have to slide a single token to its neighbor along an edge. Then this sequence, so this sequence is not the desired one for token sliding because last step here. So we move this token to this side, but there's no edge joining two vertices. So this movement is okay for token jumping, but it's not okay for token sliding. Yeah, actually, in this, this is no instance for token sliding. In this way, the reachability depends on the choice of the adjacency relation, that is the structure of the solution space. As an observation, the solution graph for token sliding forms a spanning subgraph of the solution graph for token jumping. As another example, I would like to introduce the K-coloring reconfiguration problem, which is one of the most well-studied reconfiguration problems. So recall that K-coloring of a graph is to color all vertices of the graph so that any two adjacent vertices receive different colors by using at most K colors. We take all K colorings as a set of feasible solutions and choose recoloring a single vertex at a time as a adjacency relation. Then this is a yes instance like this. So we first recolor this vertex from blue to red, and then recolor this vertex from green to blue, and finally obtain a target coloring by recoloring this vertex from yellow to green. Yeah, of course, there is no instance for coloring reconfiguration. For example, this is no instance if k equals 2. But this is a ESC instance and another adjacency relation called the Kemp change, although I omit this detail. So in this way, the reachability depends on the choice of the adjacency relation. So in order to define a reconfiguration problem, we first define a solution graph to be considered, namely the set of feasible solutions and adjacency relations defined on the feasible solutions. And once we define a solution graph, we can ask natural reachability or connectivity questions. So the most well-studied variant of reconfiguration is a reachability question. That is, we are given two nodes in the solution graph and ask the existence of a path in the solution graph joining the two nodes. As a generalization of the reachability question, we may consider the shortest variant. Shortest question computes the shortest length of a path in the solution graph, namely the minimum number of reconfiguration steps required for transformation between given two nodes. We may also ask the connectedness of the solution graph itself, namely a connectivity question asks whether the solution graph consists of a single connected component or not. Diameter question computes the diameter of the solution graph. That is the maximum shortest length of our path between any two nodes in the solution graph. So note that reconfiguration is basically a decision problem. We simply output yes or no, or an integer for the shortest question. And so actual reconfiguration sequence is not required. Indeed, there are examples such that a shortest reconfiguration, indeed there are some examples such that the shortest reconfiguration sequence requires super polynomial length. Therefore, it would be impossible to output an actual sequence in polynomial time. Of course, the solution graph itself can be exponential size with respect to the input size. as a previous SAT example. But the difficult point is we evaluate the difficult point is we evaluate the learning time of algorithms with respect to the input size. So this means that we need to output the answer without constructing the solution graph explicitly. Yeah, my original motivation to start reconfiguration was algorithmic analysis of power distribution system. At that time, there are some non-algorithmic research that can be seen as reconfiguration. So in Isaac 2008, we proposed a framework for algorithmic study of reconfiguration. After about 15 years, currently, as far as I know, more than 150 papers were published from all over the world. And I think this topic has grown to become a new trend in algorithm theory. And in 2015, I started an international workshop on combinatorial reconfiguration together with several colleagues. We hold the workshop series every 2 years, 2015 in Japan, the first one, and 2017 in Canada, and 2019 in France. So these workshops are really working workshops. So we share the current development and try to solve the open questions. Because of the COVID-19, we could not hold the workshop last year, but now planning to hold that in Banff, Canada again in this coming May. This workshop will be a hybrid mode, and online participants are welcomed very much. So if you are interested, please let us know. So from now on, let me explain some technical part of reconfiguration. Similar as several paddles, as you may know, many reconfiguration problems are known to be p-space complete. So first, I briefly explain p-space completeness. The complexity class p-space is a set of decision problems that can be solved in polynomial space. We only care the space, we only care the space and don't care the running time. Note that the class P space includes a class NP. So, and hence we can solve a P space complete. So if we can solve a P space complete problem in polynomial time, then we can solve all NP complete problems in polynomial time too. Therefore, from the viewpoint of algorithmic designer, if we can show that a reconfiguration problem is p-space complete, then it implies that there is no polynomial time algorithm for the problem under the assumption p equal not np. In addition, we can say that there exists a yes instance whose shortest reconfiguration sequence requires superpolynomial length under the assumption of NP not equal P space. So this is because if your shortest reconfiguration sequence is always polynomial length for P space complete problem, then we can use it as a weakness for NP. And many reconfiguration problems belong to the class P space. So how about the P space hardness? As you know, there is a well-known flow of NP hardness reductions. So this is a flow for NP hardness, not P-space completeness. Then for many NP complete such problem, we can show that their reconfigurations are P-space hard by following this flow of reductions. So the important result is, so Gopalan et al. Shows that P-space shows that the 3-sat reconfiguration is P-space complete. And so we can use this 3-sat reconfiguration as a source problem for reductions. However, we have to note that these reductions must preserve the reachability of the solution graph. For example, consider an NP hardness reduction from 3-sat to independent set. So this is the NP hardness reduction for the NP hardness. So in one of the well-known reduction, we first make a click for each clause over a given formula. So for example, for this clause, we make this click of side 2. For this clause, we make this click of side 3 and so on. And then join the batches corresponding to the opposite literals to preserve the consistency of variables. Of course, this reduction is correct for NP hardness, which asks only the existence of a feasible solution. But we need to be careful when we talk about the connectivity or reachability of the solution graphs. So consider these two independent sets, which are adjacent in the solution graph. Because these two independent sets are adjacent because just sliding this single token from here to here, we have this independent set. So they are adjacent in the solution graph for independent set. Then the independent set above correspond to two satisfying truth assignment, 000 and 001, because the variable z is don't care. On the other hand, the independent set below also correspond to two satisfying truth assignment, 101 and 001, because the variable x is don't care. Then these 000 and 101 are not adjacent in the solution graph for SAT, although these two original independent sets are adjacent. So consider another well-known NP hardness reduction from 3SAT to independent set, where we prepare variable gadget for each variable, so this part, and that clearly indicate all the variable assignment. And hence there is no don't care variable in this independent set for this graph. Then every independent set corresponds to exactly one satisfying truth assignment, and we can prove the p-space completeness. In this way, although we need to be a little bit careful about the reachability, we can show that many reconfiguration programs are p-space complete. And let me introduce another important p-space complete reconfiguration program for computational hardness. So let me first back to the 15 puzzle. For the 15 puzzle, the reachability question is easy to solve. We can determine whether a given initial configuration is reachable to the target one without constructing an actual transformation. To do this, we align the integers according to the configurations. So like this, so 11, 2, 4, 5, and we align the integer 11, 2, 4, 5, and so on. And draw an arrow between the corresponding integers like this. Then we count the number of crossings of the arrows. If the number of crossing is even number, then the initial configuration is reachable to the target one. But if it is an odd number, then it is not reachable. And this 15 puzzle instance is a very famous one, where only 15 and 14 appears in different order. As you notice, there is no such transformation because the configuration has only one crossing, an odd number. For more general sliding block puzzle, Martin Gardner posed an open question if there is such an easy characterization of reachability for more generalized sliding block puzzle. So he said, these puzzles are very much in want of a theory, and no one knows how to determine if a given state is obtainable from another given state. So this is an exact reachability problem. And if it is obtainable, no one knows how to find the minimum chain of moves of yeah, for archiving the state. So this is exactly the shortest question. So about 40 years later, so it was 1964, and about 14 years later, this question was solved in some sense negatively. So Hahn Demine proved that many sliding block puzzles are piece-space complete. So to prove the piece-space completeness, they introduced the very important problem, a reconfiguration problem of graph orientation, which they call a non-deterministic constraint logic. So we are given an undirected graph such that each edge has weight 1 or 2. And then, so an orientation of the graph, namely assigning a direction to each edge. So the orientation of the graph is feasible if the sum of incoming arc weight at every vertex is at least 2. So as a adjacency relation, so as a one step, we can reverse a single edge direction. Sorry, although I omit the details, so this is a very powerful tool for piece-space hardness reduction. And several puzzles and games are shown to be piece-space complete using this NCL program. In particular, by analyzing the NCL problem deeply, these well-known program for reconfiguration variant for this well-known program shown to be remain piece-space complete even for bounded maximum degree and bounded bandwidth and the planar graphs. So this is a very difficult, very restricted case, but remains piece-space complete. And because tree width and path width of a graph can be bounded by bandwidth from above. So surprisingly, these problems are difficult to solve even when bounding graph width parameters. Yeah, but the constant big for many problems. So they may be solvable in polynomial time for small constant width. Yeah, and then so I'll try to explain the intuition why reconfiguration problems are difficult even when bounding the graph with parameters. So it is probably a natural idea to try the DP method, dynamic programming method, for reconfiguration problem too. However, so far, only a few positive results are known based on DP method. So because that the design concept of dynamic programming algorithm is to store information required to solve the problem only, and delete the other information so as to bound the DP table with the polynomial size. So we want to reduce the information. For example, if we wish to solve the k-coloring search problem for trees by DP, so of course tree can be colored with only 2 colors, so it's an easy problem. But so let me try to solve the problem by dynamic programming approach. Then it suffices to store only k types of colorings of the subtree. So we take one vertex as a root and regard the tree as a rooted tree. And for each subtree, we only compute the minimum number of colors under the assumption that the root of the subtree is colored by, for example, green, for example, blue and red, and so on. And in addition, when we solve a reconfiguration problem, it is important how to store the information about the reachability with the polynomial size. So this information is enough for solve the search problem. But because when we want to solve the reconfiguration problem, we need to consider how to store the information about the reachability, in particular in polynomial size. So consider the list coloring reconfiguration. For example, this is a tree, actually caterpillar, and so each vertex has a list, can be colored to assigned to each vertex. Then this is a solution graph for this subtree. So this subtree has 8 list coloring. And like the previous example for such problem, we focus on the color assigned to the vertex W here, which is adjacent to outside the subtree, and forget the color assignment to the other vertices. So like this. Then these four colorings assign blue to the W, to the vertex to outside, but they belong to the different component in the solution graph. So we need to store reachability information with a polynomial size. So this kind of information we need, but in polynomial size. So this is a difficult point to construct efficient algorithm for reconfiguration problem. Indeed, we showed that the size of DB tables can be bounded by polynomial size for caterpillars. And the DP method was first applied to the shortest path reconfiguration on unweighted graph by Bonsman. He also gave a polynomial time algorithm for the K-kernel reconfiguration for K-2 connected graphs based on the dynamic duality. And let me remark that the dichotomy result is known for graph coloring reconfiguration with respect to the number of colors, where feasible solutions are proper vertex coloring using K colors, and we can recolor single vertex at a time. For such a solution graph, reachability question is p-space complete when the number of colors is at least 4, while it can be solved in polynomial time for any graph when K is at most 3. And this dichotomy result has been generalized to reconfiguration of circular colorings. And I then talk about the shortest reconfiguration. Yeah, because that the shortest variant asks for the length of a shortest reconfiguration sequence. So this solution graph for that illustrates the difficult point for the shortest variant. That is, so even though the variable z is assigned 0 in the initial and target, in both initial and target, we need to flip it once for keeping the feasibility. So in the initial and target, z is assigned as 0, but there's only one path like this. And during the path, we need to change the assignment of z from 0 to 1 and back from 1 to 0. So actually, almost previously known algorithm for shortest variant touch only the symmetric difference. And hence, there is no such a we call unhappy moves. But recently, there are some examples such that algorithm developed for shortest variant, which capturing the such unhappy moves. For example, Moore et al. For sub-shortest reconfiguration, and Yamada and Uehara for sliding token. Namely, independent set reconfiguration, we can slide only along an edge. And I'd like to introduce another example for the shortest variant. So recall the 15 puzzle. The 15 puzzle is solvable in polynomial time, as I said before. But interestingly, it is NP hard to compute the shortest length of a desired transformation. Yeah, of course, so we generalize the problem to not 15 puzzle, but to the n by n puzzle, n by n boards. So we have the, another example of the same behavior for perfect matching reconfiguration by alternating cycles. So where each solutions are perfect matching in the graph, and as one step, we can exchange edges along an alternating cycle. So these are the perfect matching of the graph, and we take an alternating cycle like here, and then so flip the exchange the edges along the alternating cycle. Then we obtain another perfect matching, And then we choose this alternating cycle, and exchange all the edges matching or not matching, and exchange status and obtain another perfect matching, and so on. And we want to find we are given two initial and we are given two perfect matchings of the same graph as the initial and the target perfect matchings, and we want to find the reconfiguration from the initial to the target by alternating cycles. So if we take the symmetric difference of two given perfect matchings, then it consists of alternating cycles because they are perfect matchings. So this means that the reachability question is always yes. So we just exchange the edges along the symmetric difference. We exchange the edges in the alternating cycle in the symmetric difference. In addition, this suggests us there always exists a transformation of polynomial length. On the other hand, so we prove that a shortest reconfiguration is NP hard if we wish to minimize the number of steps for transformation. So even for bipartite graph or planar graphs. And so there's a paper, another paper, not ours, but there's a paper. This problem remains NP hard for planar graphs and NP hard for bipartite and planar graphs. And we also gave up as a positive result. We also gave the problem is solvable in polynomial time for outer planar graphs. So we believe that this solution graph, this perfect matching graph, solution graph for perfect matching is interesting and important because it is equivalent to the perfect matching polytope, and hence the shortest reconfiguration equivalent to the combination shortest path problem. So more precisely, in the perfect matching polytope, each node in the polytope corresponds to the perfect matching in a graph. And so for example, for this graph, there are three perfect matching. And then the polytope is a convex hull of these nodes. So this forms a perfect matching polytope. Kubota proved in 1975 that two nodes in the polytope form an edge, so from the boundary of the convex hull, if and only if the symmetric difference of their corresponding perfect matchings is a single cycle. So this means that exactly correspond to our solution graph for perfect matchings. Then the shortest, then combination shortest path problem for perfect matching polytope is equivalent to our problem, our shortest reconfiguration problem for perfect matching. And as a background in the polyhedral combinatorics, there is a famous open question, not for perfect matching, but in general. That is, can simplex method for linear optimization always run in polynomial time or not? The running time of simplex method is at least the combinatorial diameter of convex polytope, which is maximum combinatorial shortest path. And there is a famous, sorry, I cannot pronounce, but a Hollis conjecture on the combinatorial diameter of linear length. So this one from 1957. So this conjecture was disproved by Santos in 2012, but remains open to probe the combinatorial diameter of polynomial length. And current best upper bound is like this, given by Segawa. So I think we believe that studying the shortest reconfiguration for the solution graph for perfect matching is very important because it relates to such a interesting questions. However, actually, it is difficult even to check the adjacency of two given vertices in the convex point of in general. So for example, checking just the adjacency of two vertices, sorry, it should be two nodes, is co-NP complete for these polytopes. While checking the adjacency easy for our case, like a perfect matching polytope and material-based polytope. Yeah, and because even the adjacency, checking the adjacency is difficult, combinatorial shortest path of two vertices is NP hard for these polytopes. So we prove that combinatorial shortest path because combinatorial shortest path problem for perfect matching is equivalent to our problem. So we prove that combinatorial shortest path problem is NP hard for matching polytope, for perfect matching polytope. So this means that we give an interesting example such that the checking the adjacency is easy, but finding the combinatorial shortest path or computing the length of the shortest path is difficult. And as the last of the technical part, let me explain some applications of reconfiguration. Combinatorial reconfiguration is useful to understand the state space, and studying the reachability or connectivity of the solutions graph may give you feedback to the original search problem. So, for example, this theorem is not for reconfiguration, and saying that if a graph contains no cycle of length if a graph contains no cycle of length dividable by 3, then the graph is 3-curve. So this problem was proved, this theorem was proved in 1994. And 20 years later, Martin Brofner gave another simple proof of this theorem using the idea of reconfiguration. The proof takes only 8 lines. Of course, it's based on the several definitions of the reconfiguration, but essentially it uses only 8 lines. And this proof appears in this paper, although his name doesn't appear in the author list. Brofner wanted to not to be listed, but of course, these authors listed his name on the proof. Another example is from our paper in Soda this year. In 1960, Nash-Williams proved that a graph is 2-edge connected if and only if the graph has 2k-edge connected, if and only if the graph has k-edge connected orientation. So the theorem was known for k equal 1. The case for k equal 1 is known in 1939. And we gave a new proof for this theorem based on reconfiguration. And finally, I'll explain the application to power distribution system, which was my original motivation to start studying reconfiguration. As I said before, power distribution network have many, actually so many feasible configurations so as to deliver electricity even when some trouble happens. Then distribution loss depends on the choice of network configurations. So if we want to reduce the distribution loss, there are actually 2 issues. One is how to find an optimal configuration, And another is how to reconfigure the current configuration to the optimal one. Of course, we cannot cause any blackout even during the transformation. Indeed, the issue one is NP hard problem. It is NP hard to find an optimal configuration that minimizes distribution loss. And we propose an algorithm which resolves both issues 1 and 2 at the same time. Of course, it is not a polynomial time algorithm, but runs efficiently for several distribution networks. I mean, experimentally. So, for example, there is a benchmark data as a standard model of Japanese power distribution network. So this network has 72 substations and 1,008 sections and 468 switch gears. And we can control these switch gears turning on or turning off and obtain the feasible configuration. So basically the possibility is 2 to the this number because so we can we have a choice of turning on or turning off of the switch gears. But even if we restrict the number to the feasible one, there is a 10 to the 53rd number of feasible network configurations. So these are quite huge choices. Our algorithm runs efficiently and find an optimal network configuration together with the switching procedure for transformation in a few seconds using a standard desktop computer. And we estimate the energy efficient improvements for 1 year in Japan. So it's rough estimation, but it corresponds our result efficiency. Our improvement corresponds to reduce CO2 emissions by about 6,800 tons. So which is roughly amount about absorbed by this number of trees. Finally, let me conclude my talk with some advertisement. So I'm now leading a 3-year project for computer reconfiguration in Japan. So where 20 young researchers in Japan work together for reconfiguration. So in this project, we work not only for theory, but also for practice. And we have developed some solver for computer reconfiguration. And we plan to publish a solver in Python in the coming months. So we hope it would be helpful also for theoretical study, such as finding a small counterexample and so on. So if you are interested in, please check our project website. And but please note that so the solver has not been published yet. So we plan to publish it maybe the coming months. And as a part of the project, we will organize one-day workshop in ICAP 2022, which is different from the workshop in May in Banff, Canada. It will be held on July 4th in Paris with the option to participate online. We now calling for contribute talks. So if you are interested, please visit our website. So that's all. Thank you for your attention.
Thanks, Professor Ito. What a wonderful thoughts. Please give virtual applause for Professor Ito. Okay, we still have 5 minutes for discussion. Is there any questions or remarks for Professor Ito? Or comments? if not, then please join me again to give applause to Professor Ito. Thank you very much, Professor Ito. And I think this is the end of the invited talks session. And we still have 15 minutes for break, yeah, before the next agenda. The next agenda will be a business meeting, and it is led by Professor Shaidur Rahman. Okay, thank you very much, and I will give back to the committee. Yeah, is there any question?
No, there are some questions. I think Professor Uehara raised hand. Professor Petra Mutzel also raised hand. So I think.
Sorry, I didn't see in my iPad. So okay. I'm so sorry, Professor Ito. Please, please ask a question for Professor Ito. Sorry, I have to put all participants.
Sorry, I did not raise my hand, and it was just a clapping. But,
Okay.
but on the other,
okay,
so it was. Thank you for. It was just a really great talk. And whenever I hear this reconfiguration, and so I'm working a lot on graph algorithms. So I'm wondering about the connection to the graph edit distance. Because for the graph edit distance, you're also given two graphs, and you're asking for to transfer one graph to the other one. But there's a special case that the property must be kept. But otherwise, it's the same.
Yeah. So it depends on how to define the solution graph. So if we take that as a base graph, like a complete graph of any parts, with a sufficiently large, and so any graph can be obtainable from by the edit, then we can obtain a solution graph that contains all the graph, and so we can ask the reachability. So so it's really depends on how to define the solution graph, yes, and so in that sense, so we can graph editing can be seen as a reconfiguration program. Yeah. I think.
Right. Okay.
Thank you.
Is there any comment or question? No? Okay, then let's thank again to Professor Ito.
Yeah, thank you so much.
Thank you. Okay, I will give back to the committee. Mbak Yuyun, please handle it. Okay.
Okay, thank you very much for all of the chair and all of the presenters today. And then we have around 10 minutes later to go to the next session. The next session is a business meeting that will be led by Mr. Shaidur Rahman. And for this session, we will have a big thank you.
Hello, Zaido. Can you hear me? Zaido, can you hear me?
Yes, I can hear you. Tokima Sensei, konnichiwa.
Konnichiwa. Okay.
How's I doing?
Hello.
Oh,
Yeah. Welcome to the business meeting.
Thank you. So yesterday I finally got the test and was negative. I had been home for a few days because I had been tested positive to COVID. And so I'm very happy that I'm out. I'm now in my office.
Okay. At the end of January, I also suffered, and I was also COVID positive. And it was around, say, 28 days. It was positive.
28. Oh, gosh.
After 28 days, it became negative.
Yeah. It's such a strange thing, right? That you then. Yeah. In my case, it was just a cold, nothing serious. I don't know how was it for you?
Okay, the time has come. Like I said before, that the next session is the last one of this day. That is a business meeting session. And for this session will be led by Professor Saidur Rahman. For Professor Saidur Rahman, time is yours.
Thank you. Honorable advisory board members of WALCOM, steering committee members, program committee members, authors, participants, invited guests, welcome you all to this business meeting. In this business meeting, actually, we have three parts. First, one is remembrance of Professor Takao Nishizaki and Professor Etsuji Tomita. Then declaration of next WALCOM, that is WALCOM 2023. And finally, we will do open discussion or get comments from the audience for improvement of WALCOM. So first is remembrance of Professor Takao Nishizaki and Professor Tomita. Here, okay, and with great sorrow, we are sharing the news that we have lost great advisor and mentor of WALCOM, Professor Takao Nishizaki, on January 30, 2022. And before that, we also lost our mentor of WALCOM, Professor Etsuji Tomita, on September 2, 2021. And so for this session is for remembrance of these two mentors of WALCOM. First, in this session, actually, I first show a few slides on the roles there, that is relation with WALCOM, and then Professor Tokuyama will talk on Professor Nishizaki, and Professor Nishino will talk on Professor Etsuji Tomita. So I am just sharing a few slides on the remembrance of Professor Takao Nishizaki and Etsuji Tomita. I think many of you know that actually Professor Takao Nishizaki is the central person of that is establishing WALCOM. And in fact, into WALCOM 2007, it was the first WALCOM, and it was held to celebrate the 60th birthday of Professor Takao Nishizaki. Actually, that time, Bangladesh Academy of Sciences was recognizing Professor Nishizaki as his contribution of computer science education in Bangladesh. And so they invited them, and that time, February 12, it was birthday of Professor Takao Nishizaki, and we organized the first one WALCOM. At that time, actually, Professor Nishizaki and his team, that means all of his former students, went to Bangladesh and they gave talk in the workshop. Professor Nakano, Professor Jo, Professor Ito, Professor Kusakari, all of them went to Bangladesh and gave the talk that time. So this was the first event, WALCOM 2007. And then from 2000, we continued this event from 2008, and currently you know about WALCOM and its status. And so in 2007, Professor Nishizaki attended and it was started. Professor Nishizaki lastly attended, that is WALCOM 2015, and it was also held in Bangladesh. And in this figure, in this photo, you can see that Professor Nishizaki is receiving a crest of recognition from the Minister of Science and Technology, Bangladesh. And actually, Professor Nishizaki first visited Bangladesh in 1998. And that time he met the President of Bangladesh, Justice Shahabuddin, and who recently passed away. So that time, Professor Nishizaki met the President of Bangladesh. And lastly, 2015, he was, that is given a crest by the Minister of Science and Technology of Bangladesh. And here in the right side photo, you see that the famous researcher, Professor Monindra Agoral, and he was the invited speaker of WALCOM 2015. And Professor Nishizaki was the session chair, and he was giving his talk, giving a crest to Professor Monindra Agarwal. And actually, 2015, Professor Nishizaki attended as a author of a contributed paper, and he himself presented this paper in WALCOM 2015. And there is also a history behind it, because in 2014, I went to attend FAW for 2014 in China. There I met Professor Nishizaki. He has also a paper there, and he also presented a paper there. And I requested him to give an invited talk in 2015, WALCOM 2015, which was then supposed to be held in Bangladesh. But he did not agree, and he told that it might be the last conference for his life, and he did not want to give an invited talk as the last talk in the conference. He told me that if he will submit a paper, and if the paper is accepted, and then he will go and then give an invited talk. Give an contributed talk. So he wanted to attend his last conference in his life by presenting a contributed talk, not an invited talk. So, and later his paper got accepted and he came to Dhaka and he presented this paper, is coloring of weighted graphs. He actually was the founding steering committee member of WALCOM and also advisory board member of WALCOM since 2020. So WALCOM community gratefully remember the contribution of Professor Takao Nishizaki. Now I will just show you only a few slides of which indicates his relationship and his helping attitude towards students. So this is a picture that is with Nishizaki and me, and this is he was correcting one of my paper, and this is not only with me, with all of his students. Here I think Professor Nakano is present here, Professor Ito is present here, Dr. Suzuki is present here. They know that Professor Nishizaki spent hours after hours in correcting students' papers. And every time, whenever he changed something, he always explained why he is changing this one. So in this way, he taught his students. This was a picture with his former students in his retirement ceremony. And this is a very sweet memory of mine when he was in Kansei Gakuin University, and I went to visit him, and he took me to a restaurant. Now I could not remember the name of the restaurant, but I think Professor Tokuema can recognize maybe. So it is a very famous restaurant in Kansai area, I think. So now I will show some of the activities of Professor Tomita connected with WALCOM. Professor Tomita first attended WALCOM 2010, and he that is as a contributed author, and he presented his paper, a simple and faster branch and bound algorithm for finding a maximum click. The conference was held in Dhaka, and this paper actually currently the most cited paper of WALCOM. Professor Tomita was program chair of WALCOM 2015, and where Professor Nishizaki received the crest from the minister, where at that occasion he was the program chair, and he was giving a talk here and presenting the statistics of WALCOM 2015 here. And here is the Vice Chancellor of BOET, then Vice Chancellor of BOET, and here is the minister, and Professor Naim Chaudhary, the secretary, is then Secretary of Bangladesh Academy of Sciences here. In the right side, this picture, this photo is very, I think, very important photo, because you can see that three steering committee members. That is, here is sitting Professor Nishizaki, Professor Kaikobad is here, and Professor Subhash Nandi and Professor Tomita. So, and Professor Tomita was also invited speaker of WALCOM 2017. I could not find a picture of him, but this paper he presented in 2017. So now, so this is I think this illustrates the relationship of Professor Nishizaki and Professor Tomita with WALCOM, and we gratefully remember them, the contribution of Professor Nishizaki and Professor Tomita. I now request Professor Takeshi Tokuyama to talk about Professor Nishizaki.
Okay, thank you. And let me share some slides. So can you see my slide? Okay.
Yes.
Okay, so it's a great sorrow, the loss of Professor Takao Nishizaki. And so Professor Takao Nishizaki was born in Fukushima, Japan in 1947 and got PhD in engineering in Tohoku University in 1974. And so immediately he became an assistant professor there and promoted to full professor from 1988. And he was Dean of Graduate School of Information Sciences of Tohoku University from 2008. And after retired from Tohoku University, so he became a professor of Kwansei Gakuin University. And suddenly passed away on January 31st, 2022, fighting against cancer for 3.5 years after 1 year life expectancy declaration by doctor. So there is a tribute in the WALCOM conference brochure. So you can see his contributions. So let me tell about Professor Nishizaki. And in Buddhism, we get a Dharma name. So in Japanese, we call it kaimyo. And Takao, usually we ask a priest to prepare a kaimyo, this Dharma name. But Takao prepared his own Dharma name himself. And this Dharma name tells his story. So it is in Japanese, but it is pronounced Sanzuin Kenkyo Ryu Kei Koji. And as you know, Chinese character has a meaning. It comes from pictures. So in the right column, there are ancient way of Chinese characters. So you can see some pictures. So implicating the meaning of these characters. And the first character, san, means computation and algorithms. And the second character, zu, so this indicates graph. And the third character, in, is a fixed character to show high contribution. And and the next character, ken, is this means research. And the next one means teaching, hyou. And the ryu, the next one is inherited from his name. His name is Nishizaki Takao, and the third character is given here. And the next character is kei. It means continuation. And the last two characters is a suffix to show the level of faith in Buddhism. So those 5 characters, san, zu, ken, kyo, kei. So this shows his life. The first character, san, means algorithms and computation. So algorithms is written as 2 characters like sanjutsu, and computation is keisan, but both means both contain this character. So he was pioneer and leader of theoretical computer science in Asia and Pacific. And in particular, he initiated and promoted Isaac conferences from 1990. So in the right, you can see the first, the group photo of first Isaac, and some list of Isaac proceedings. And he was advisory committee chair for 17 years. And interestingly, he said that a conference should be fun for participants. And he introduced karaoke session, and you can see some pictures. So here, Takao is dancing with a lady. And there are several people singing songs like Chazelle, Kirkpatrick, Mike Crowley, and Andy Yao, and Xie Liu, and so on. And of course, so this is a picture of WALCOM. So as I showed in the last talk. And in the left picture, so you see quarter century celebration of Isaac, and we celebrated main contributors to Isaac. And from left, so you can see the faces of Hiroshi Imai, Peter East, Francis Chin, and myself, and Kunyun Chua, and D.T. Lee, and Nishizeki, Takao, and Kunsu Park. And Nishizeki was always our leader. And the next character is Zu. So Zu means graph. And he was a pioneer. He is a pioneer of graph algorithms and drawing, and foundation member of graph drawing conference. And here, so there is a handbook he wrote as one of the editors. And this is the graph drawing conference he organized. And in the center, there is a picture with other foundation members of graph drawing, like Toris and Tamashia. And he wrote 2 books. So one book is planar graph drawing, co-authored with Zaidu. And the other is planar graph co-authored with Chiba. Those are very popular books, textbooks in this field. And the next character is Ken. This means Kenkyu, research. So I'd like to tell about one of his pioneering works, that is algorithms on structured graphs. Many graph problems are necessary to solve in practice. However, unfortunately, most of them are intractable. That means NP hard. So what we should do? So Takao's solution is like this. They are not intractable for practical instances, since graphs in real world are well structured. And in his seminal paper in JACM in 1982 with Takamiza and Saito, so the title is Linear Time Computability of Combinatorial Problems on Series Parallel Graph. And he showed that most problems can be solved if the graph is made by using series and parallel operations. And he extended this theory to partial K trees. And this is this contains K as a parameter. If K is huge, then it can represent any graphs. And typical time complexities are order Fkn or order Fk times polynomial of n. So we can see a beautiful down of FPT, fixed parameter tractability, in his work. And today, Professor Bodrender talked about its state of art, mainly on hardness 3 hours ago. So it's a kind of sun, shining sun in these days, right? And here, I'd like to show people with whom Takao discussed and worked. So on the top, Claude Berger, Jin Akiyama, Paul Seymour, Paul Elzesh, and in the below, his friends, D.T. Lee, Tetsuo Asano, Yoshihide Igarashi, and Shinichi Nakano, and Hiroshi Imai, and myself are given. You can find them, right? So he has very wide range of friends in theory of computation. And the next character is Kyo. Kyo means the teacher or teaching. As Zaido said, Takao was a kind, patient, but stout teacher. And his motto was practice makes perfect. And practice and practice and practice. So he has many academic descendants, including Shinichi Nakano, Xiaozhou, Abdul Kashem, and Daizuru. and Takehiro Ito, who just gave an excellent invited talk today. And you can see them in these pictures. And then the final character is K. That means continuation. So Takao's motto given in speeches in graduation celebration is as follows: time is evenly given to everyone, and continuation is power. So we should continue his will to promote our community on algorithms and computation in Asia Pacific and worldwide. So many thanks to Takao, now Sanzuin Kenkyo Ryu Keikoji, and thank you for your attention. Okay, thank you very much.
Okay, now if someone want to speak or tell something on Professor Nishideki, can tell us. I think if someone wish to talk, okay, and then I request Professor Tetsuro Nishino to talk about the Professor Etsuji Tomita.
Okay, thank you very much. So I'd like to share my slides. So can you see my slides?
Yes.
Okay. So today I'd like to give a speech in memory of Dr. Etsuji Tomita. I'm Tetsuro Nishino of the University of Electrocommunications. And Dr. Etsuji Tomita is a fellow of Information Processing Society of Japan and a recipient of the Distinguished Achievement Award in IPSJ and emeritus professor of the University of Electrocommunications. Unfortunately passed away on September 1st of 2021, and his funeral service was held on September 3rd. Dr. Tomita completed his doctorate in electric engineering at the Graduate School of Science and Engineering, Tokyo Institute of Technology in March 1971. Then he immediately began working as research associate at the Tokyo Institute of Technology, the Faculty of Engineering. And in October 1976, he was hired as an associate assistant professor at the University of the Electrocommunications and became a professor in April 1986. And Dr. Tomita has long been involved in research and teaching in the fields of automata, language theory, learning theory, and combinatorial optimization, and has made pioneering and outstanding achievements. So first, he devised the unified and completely new algorithm for the equivalence problem of deterministic context-free languages and proposed a new method of computational learning theory, as you know. And on the other hand, in the area of combinatorial optimization problems, he focused on the graph structures called cliques, which play an important role in the analysis of large-scale network from a very early stage, and he long been a pioneer in research on clique extraction. Among them, the optimal algorithm he devised for enumerating all maximal cliques has been cited, not only in the field of algorithms, but also in a wide range of other fields. including biotech or many things. So he has also developed several fast algorithms for maximum click extraction problem, which are widely cited and have become one of the international centers of development of this problem. So these algorithms have been skillfully utilized in many applications and as collaborative research, as you know. So also he has served as chairperson of executive committee, program committee chairperson, conference committee chairperson, and invited keynote speaker at several international conferences. Meanwhile, the famous textbook Automata and Learning Theory from Morikita Publishing has gone through a total of 30 reprints from the first to the second revised edition and had made a significant contribution to education in this field. So for the above mentioned outstanding research achievement, he has received the Funai Prize of Promoting Information Science in 2003, a Fellow of Institute of Electronics Information and Community Engineering 2003, and Fellow of the Information Processing Society of Japan in 2003. And in addition, as you know, the paper enumerating all of the extreme clicks, maximal clicks received the 2005 to 2010 Most Cited Paper Award from Theoretical Computer Science. And on the 40th anniversary of the journal publication, it also received the 2006 Most Cited Paper Award in 2010. Also, in the Information Processing Society of Japan, he served as the chief editor of the journal editorial committee, or chief editor of the mathematical modeling and problem solving study groups, and the chairman on the computer science area committee, and several directors. So in the following, I'd like to specifically mention Dr. Tomita's contributions. So first, I'd like to look on the learning theory and the inference algorithms. So Dr. Tomita was the first in the world to focus on the importance of learning theory, of course, which is fundamental to artificial intelligence, and published his findings in international conference and journals in the 1970s. So these were pioneering achievements, including the key concept of learning algorithm for well-known regular languages, which are published in 1980s. Equivalence problem is a fundamentally important issue in the learning process, but this has been a largely unsolved and difficult problem in modern regular languages. So Dr. Tomita has established a new equivalence decision method that is simple and efficient and can be applied to a certain wide class of deterministic pushdown automata, as you know. And inductive learning languages is an important research topic, and well-known learning algorithm for regular language is the MAT, minimally adequate teacher learning model proposed by Dana Ang-Ruin. The core idea of this learning algorithm to find a finite set of representative positive examples that captures the essence of the target finite automaton by allowing questions and counterexamples. But 10 years before Ang-Ruin, Dr. Tomita and his colleagues had already proposed the important concept of representative symbolic sequence sets, leading to results for efficient learning algorithm for finite automata. Furthermore, Dr. Tomita and his colleagues have extended this notion of representative example set to simple deterministic grammars and succeeded in proposing an efficient learning algorithm for simple deterministic language families and truly encompass regular language families. And next, I'd like to talk on maximum click extraction problem. So Dr. Tomita had made many contributions to combinatorial optimization problems, including maximum click extraction problem, which involves extracting the largest interrelated subset of the set of objects. And in 2001, he presented a new algorithm for maximum click extraction that has been used in several DIMAX international benchmark tests. It was several 100,000 times faster than the standard algorithm of that time. It was proven to be significantly faster than existing algorithms at the time. So this achievement of high speed enabled the proposed algorithm to be applied to solve various real-world problems. And research results in new application fields have been produced, as you know. And in fact, these combinatory optimization algorithms were introduced in newspaper report in 2002, which is titled New Method Solving Explosive Computations. Dr. Tomita responded to various inquiries from many companies and gave them a lot of advice, which had a strong impact on biotech researchers as well as on the industrial world. So in this way, Dr. Tomita has contributed to a society not only as a researcher, but also as a person in charge of technologically evaluation for companies through the promotion of basic technology research and technology evaluation. And next, I'd like to talk on the activities and contributions in academia. So Dr. Tomita was awarded the 2005 to 2010 Most Cited Paper Award by Theoretical Computer Science, as I said before. And the number of the citation of this paper on Google Scholar is more than 700, which is a very high number in the field of theoretical computer science in the first decade after publication. And it continues to increase. And Dr. Tomita has held the following position or derived the following speeches. So in the case of algorithmic learning theory, ALT, he served as local chair in 2003, PC chair in 2005. In the case of International Colloquium of Grammatical Inference, ICGI, he served as conference chair in 2006, a steering committee member from 2004 to 2012. In the case of international, WALCOM, he served as a PC member in 2003 and PC co-chair in 2005. And also, Dr. Tomita delivered the keynote speech in WALCOM 2017, and which is titled Efficient Algorithm for Finding Maximum and Maximal Clicks and Their Applications. So finally, I'd like to talk on the famous textbook, Automata and Language Theory. So Dr. Tomita is well known for his enthusiasm for education, and his textbook, Automata and Language Theory, this was written by Etsuji Tomita and Takashi Yokomori, and has been widely used as a textbook at universities and graduate schools since its publication, and it's revised almost every year. So although many textbooks on automata and formal language theory have been published, one day in 1990, Professor Tomita decided to write a textbook that could be conveniently used in his lectures. Dr. Tomita decided to use a vast amount of lecture materials prepared over the years to make the book as easy to understand as possible. And the basic policy to kept in his mind is writing the book was as follows. So starting with concrete, easy to understand examples, The author the author means that Dr. Tomita gives more general explanations and definitions, then presents the theorem and keeps the proofs as rigorous as possible. So throughout the writing process, the subtle attention for details for students new to the field was evident, and the depth of thought and care given to the explanation, presentation, and proofs of each selected topics was excellent. So that's the first edition of Automata and Language Theory was published in May 1992 by Morikita Publishing, and subsequently revised and expanded second edition was published in 2008. And since its publication, this book has been widely used as a textbook and reference book in universities and graduate schools, and has made a significant contribution to basic information processing education in Japan. In fact, since the first edition of the first printing in 1992, the book has gone into the 24th printing, and the second edition, published in December 2013, has already completed its 7th printing and is now in its 8th printing. So it has become an exceptionally long seller as an information technology textbook. So I myself sometimes see new students who say, I like Dr. Tomita's textbook even now. So finally, I would like to offer my heartfelt prayer for the repose of Dr. Tomita's soul. So thank you very much for your attention.
Thank you, Professor Tetsuro Nishino. Now I invite from the audience and the colleagues and who knows Professor Nishizaki and Professor Tomita, if you memorize some of your memory, you can briefly memorize it. Professor Ito, would you please say something?
So sorry. Yeah. So I haven't met Nishiki Sensei for a long time. So yeah, of course I heard about his cancer and fighting cancer, but it was even though I know that he's fighting, but it was really sad news, of course, for me. And unfortunately, so because of the COVID-19, we couldn't visit his how can I say ceremony. Yeah, it was also also sad. Yeah. That's all. Thank you. Yeah.
Okay, thank you. So then we pray for the departed soul of Professor Nishizaki and Tomita. May the Almighty give them peace in their eternal life. So next, we are moving to the next part of business meeting. This is a declaration of WALCOM 2003. I request Professor Lin is here I think he will tell us about the next WALCOM 2023.
Okay, thank you. I will share my slides first. Can you see it? Can you hear me?
Yes.
Okay, sorry. Okay, so hello everyone. I'm Chen Lin from National Yangming Zhao Tong University, and I'm going to present an announcement of the conference of the next year. In fact, it's really hard for me to announce this event right after the remembrance of the two esteemed professors, but I will try my best to make this announcement. Because of the COVID-19 epidemic, this conference will be held on two channels. The physical conference will be held in my university, NYCU, and it is in Hsinchu, Taiwan. And the other virtual conference will also be held online at the same time. The most important thing is the important days. So the conference will be held in March 22 to 24. And from the following calendar, you can see the dates are in the last second week of March. And it is the same of the conference of this year. And the other dates, the other important days are also similar to the days of this year. And I hope all of you are available to submit papers on time and join this event next year. The other important thing is about the impact of COVID-19 epidemic. And so far, Taiwan has kept a strict quarantine policy for COVID-19 epidemic. In the policy, any visitor to Taiwan needs to be quarantined in an isolated hotel for 10 days, and then to be self-health managed for another 4 days. So I think it's very hard for the participants to decide to visit Taiwan during the date if the policy is not changed. But fortunately, there's a trend in Asia. In this trend, we gradually alleviate quarantine restriction. For example, Japan already allowed Taiwanese visitors with 3 doses of vaccine to enter Japan. So in the future, maybe Taiwan will follow the same rule of Japan to allow visitors with 3 doses of the vaccine to come. But if the policy is not changed, the conference of the next year will be held physically and virtually. Here's the conference organization. And I'm Chun Lin from NYCU, and I will serve as both chairs, program chair, and organizing chair. And I'm also very happy to co-chair this conference with the other 2 esteemed professors. And the first professor is Professor Bertrand Lin. He is also from the same university of mine. And he is an expert on developing algorithms for operations research and the scheduling problems. And the other professor is Professor Giuseppe Leotta. He is from University of Perugia. And I think most of you are familiar with Professor Leotta, so I skip his introduction. Here's the conference scope. This page was copied from the webpage of the website. So I think I don't mention too much about the scope, okay? So because the conference will be physically held in my university, so I introduce my university in the following. And my university, NYCU, has a new brand name. It is a merged name of the 2 top universities in Taiwan, and it is a new name since last year. Okay, the first university is National Jiao Tong University. Sorry, this one, and it is notable for engineering fields. And the other university is National University, and it is notable for medical fields. And because the government in Taiwan would like to develop the research, the research field for ICT, biological ICT field. So the government would like the two universities to become a new universities. So we merged the two university and has a new brand name. It is called National Yangming Jiao Tong University since the last year. And here's the ranking of my university. And about the engineering, EE, and the CS subject, and engineering and technology subject, the ranking of the three subjects are between 100 and 150. And about the nursing and the medicine ranking, the ranking of the two subjects is between 100 to 200. So from these statistics, you can see that we would like to develop the bio-ICT field. And here's the locations of our university campuses. And our university, my university has 10 campuses spread all over the whole island, the whole Taiwan island. As you can see, we have campuses in Taipei, Taoyuan, Hsinchu, Tainan, and Yilan. And about the conference venue, it will be located in Hsinchu major campus here. And here's a photo for the conference location. About the map of the location, as you can see the figure, this is Taiwan Island, and the Taipei capital city is here. And we have we have the major international airport here. And it is the idea of the international airport is TPE. And my university is in Hsinchu City. As you can see, it is a triangle. So for each node of the triangle to the other node, it takes only 1 hour driving distance. Okay, so this is a big, if this is the airport and this is my university, so it takes only 1 hour. And from the information, you can see if you can visit, you can attend a conference of the next year. You can also visit Taipei city. It's very easy to visit Taipei. And Hsinchu City is also known as Silicon Valley of Taiwan. And there's a science park in this city, and this science park has more than 500 high-tech companies, including the TSMC, which is the global leading semiconductor foundry, and the headquarters of the SMC is located here. Okay, and in this city we have two top universities. One is my university. The other is the Tsinghua University. Maybe some of you know the top university in China is Tsinghua University, right? And in Taiwan, we also have other Tsinghua University. So in this city, we have two top universities. Okay, in the following, I will introduce the information for the tourism to Taiwan. And I show you some photos here. The first photo is the National Palace Museum. It collects a huge number of artifacts from the Forbidden City in Beijing. And this museum is ranked as one of the top 20 global most visited museums in the world. Okay, so this is very famous. The second one is the Taipei 101, and it was ever the highest building in the world. And if you buy a ticket, you can take elevator to the top of the building and take a look at the whole Taipei city. Okay. The next one is the Chiang Kai-shek Memorial Hall, and it is a large park in the center of the Taipei city. Okay. The next one is the Shilin Night Market, and in this night market, you can enjoy a special Taiwanese food and snacks, and you can also enjoy the Taiwanese culture and various cuisines. And the next one is the Longshan Temple. Longshan Temple is a Buddhist temple, and it is famous. The next one is Queen's Head, and this is a stone, and it's amazing that this head is sculptured by nature. So I suggest you to visit it. The next one is Jumin Museum. Jumin is a famous artist, and he has a series which is called Taiji. And so you can see this figure. It looks like a person playing Taiji, Chinese Kung Fu. Okay. The next one is Arishan. Arishan is the high mountain. So it provides a beautiful view of the sea of clouds as this figure. And in the morning, it also you can also enjoy the beautiful view of sunrise. Okay. The next one is the Sun Moon Lake. It is the largest lake in Taiwan. And we also show you some photos for the spatial Taiwan. And for example, the first one is the Xiaorongbao in Din Tai Fung. And I suggest that I think some of you may have Din Tai Fung in your country, but it is high price. But if you come to Taiwan, you can enjoy the Xiaorongbao in affordable price, at an affordable price. The next one is beef noodle and hard mango rice, bubble tea. The orange of bubble tea is Taiwan, and the chicken chop. And because the conference will be held in the flower season in Taiwan, so if you can come physically, you can enjoy the flower blossom during your stay in Taiwan. And I will, in the following, I will show you two videos. The first video is for introducing touring Taiwan by train. So I'm going to play this. Sorry, I cannot see my mouse. I may escape first. By train, Taipei 101. You can take elevator to the top. Longshan Temple is a Buddhist temple. Fortune telling. Taipei main station. Go to the east side of Taiwan. So this is the Pacific Ocean. And this is one of the oldest train in Taiwan. And you can go through the forest and go cycling. There's a garage for trains. This is Wurongti Mountain. This rice field. This Aboriginal culture. This is high-speed rail. Rice box. National Palace Museum in South Branch. It's a stone. Looks like a meat, but it cannot be. It's not eatable. You can also enjoy the tea and the food, high quality food. And this is solar field. Puppet. Joven Mountain Town. Tea, Chinese tea, Taiwanese tea. Night market. A variety of cuisines, bubble teas. It's a lantern frying. Okay, this is a video for touring Taiwan by train. Oh, sorry. I offer another video. Maybe I can go to the next slide. Oh, okay, this slide is for the food in Taiwan. Soya milk, Din Tai Fung, Xiaolong Bao. Mango shaped ice. Beef noodles. Teppanyaki. Pancake. Aboriginal cuisine. Rice pudding. Bubble tea. Hapa. Rice dumpling. Rice cake. Okay. I go to the next slide. Okay. This is the last slide of my presentation, and I hope you enjoy my presentation, and I hope you can submit the papers and attend this conference physically next year. And but if you do not have a plan to attend this conference, and you can also have a plan to visit me or visit Taiwan. And I'm always here to welcome you to visit Taiwan. Thank you.
Okay, thank you, Professor Lin, for showing us the next venue of WALCOM beautifully. Actually, we hope that next year the COVID situation will be improved and we will be able to visit physically there. We hope so. Okay.
Sorry, I don't know how to
okay.
finish the sharing. Sorry.
Okay, do anybody has any comments or do we have any question to Professor Lin?
I enjoyed your movies a lot and your presentation also a lot, and now I really feel hungry because it's lunchtime. I wish I were there already and eat all these wonderful things you suggested.
Okay.
Thank you. I hope I can see you then. I hope the isolation policy, the quarantine policy can be changed so that I welcome all of you can visit me. Thank you.
Actually, I visited in 2017, and at that time also Professor Lin was organizing chair of WALCOM 2017. So he has, and he organized very well that conference that time. Okay, now we will move to the next part of our business meeting, and it is open discussion. Actually, at the beginning of open discussion, I must thank Professor Slamin and his team for organizing WALCOM 2022 very well and very well organized it is, and everything is well prepared. So I thanks on behalf of steering committee and program committee. Now I open the floor to discuss. I think we have several steering committee members and advisory committee members here. And actually, this is the first time we are getting so many PC members, steering committee members, and advisory committee members in the business meeting, because it is held in, it is being held in virtually. So I will request you to give your comments, suggestions, whatever you think.
I wanted just to make an addition for 2023. Sorry if it's the previous point of the agenda. I wanted just to say that invited speakers we've been looking for, highest profiles, and at this point we got a yes, although conditional to all the pandemic, and so from Jan Kratochvil and from Michael Kaufman. It is still informal, so but we will work on it in the next few months. Hopefully, Jan and Michael will give invited talks.
Okay, that would be nice. They agree.
Yeah.
So, Professor Subhash Nandi is here. Would you please tell us something?
Yes, it is nicely organized. Actually, we are looking for the next year actually, so that we can physically be there to attend the conference. So that will be very, very nice actually. But the situation, how the situation will take place, right? We don't know. We are expecting for the best situation so that we can attend it. Attending virtually is very difficult actually. People cannot meet the other person, so that the idea exchange and all those things, the main objective of the conference is not satisfied. So we are looking for the physical conference in the next year.
We hope the situation will be improved.
Otherwise, it is only at the publication of the paper. The basic objective.
Professor Petra Mutzel, would you please say for the audience and for the participants of the conference this year?
This year, so I really like to thank the organizing. I am really very impressed by everything. Is very well moderated. Everything works out, and that's not always easy because online it's much more difficult, and hybrid it's even more difficult. And I'm really impressed how you did it, and yeah, at every point of time, there's somebody there who exactly knows what to do now, and it's very well prepared. So I really thank to the organizers, and of course, I think we need to give a big thank you to you, Saidur Rahman, because I think you're the driving force of WALCOM since 2007 on now.
Professor Slamin, as the organizing chair.
Yeah, okay. Yeah. Thanks. Sorry, I'm in the car now. Sorry, but it's okay. First of all, I would like to thank for all participants, all steering committee, especially Professor Saidur Rahman and Professor Mutzel, who really guiding us how to prepare the conference. Yeah. And I also apologize on behalf of the committee if there is something not good, something is not convenient, but we always do our best for this WALCOM 2022. And I hope we can join again the WALCOM 2023 in Taiwan, and we really like to go there. Yeah. And thank you very much. Thank you very much, and keep healthy. Thank you.
Thank you. Look forward to seeing you then.
From the participants of this year, do someone wants to tell or give some comments or suggestions for improving WALCOM? Professor Jan is here, I think. Actually, it was organizing virtually. It was very difficult because of time zone. So creating program, considering the time zone of the authors of the papers, it was very difficult. Even for some session chairs, they were. It was very early. For example, today, Professor Chan Kratosville, I think he joined very early in his time. Thank you all, everyone. Thank you for helping or for contributing to WALCOM. Professor Jan, would you please say something?
I thank you for letting me chair the session and asking me to say a few words. I really enjoyed. As you said, I mean, I had to set up an alarm clock this morning. It's an unusual time to get up, and I'm looking forward to WALCOM next year. I mean, I hope very much that the situation will improve regarding COVID and improve regarding the overall situation in the world, and it would be possible to come over and deliver the invited talk in person at WALCOM 2023. Yeah. And thank you for a wonderful organization. And if I may add a personal thing, I really enjoyed seeing Slamin again. We haven't seen each other for many years, so I really enjoyed
me
seeing
too.
him.
I miss you so much, Jan. Actually,
hello.
last month I visited Germany for 3 weeks, Petra. Yeah, but we just going around Germany and then go to Holland, to Netherlands, and also to Denmark and Australia. But unfortunately, I cannot go to Prague. Yeah, actually, I was in resident only for 2. Yeah, next time. I've been there twice. Yeah, I will come for the third one. Keep healthy, Jan. Nice to meet you. Yeah.
You too, and everybody.
Yeah. Everybody too.
Safe and healthy.
Too. Yes. Thank you so much. Actually, we expect all of you come to Indonesia, but unfortunately, the COVID is still not good. I was good in Germany, but when I came to Indonesia for just for a week after coming Indonesia, I got myself positive. So that's so I have to quarantine like for 10 days. Yeah, but now everything is okay. Yep.
Okay. Professor Uehara, would you please talk something?
Yeah, okay. Thank you very much for your nice organization. So far, it's very, very nice conference. And actually, I hope I could visit Indonesia. This time I'm missing you, but next time I hope we can get together at Taiwan. So thank you very much.
Okay, thank you so much. Professor Nakano, would you please say something?
Thank you for well organizing this conference. My hope is we may have another WALCOM in Indonesia in future.
Okay.
I like to have a physical WALCOM in Indonesia, Jamba.
I hope so.
I hope so.
Someday.
Okay, thank you. So, is there any other comments or suggestion from other participants? If not, then we can close this session. And we thank Professor Slamin and his team for organizing WALCOM 2022 beautifully. And we hope that in future, he will organize a physical WALCOM conference in Taiwan. And next year, I hope so. in Indonesia. And next year, Professor Lin is taking the responsibility of organizing WALCOM in Taiwan. I hope the COVID situation will be improved and we will be able to visit Taiwan physically. Okay. Thank you all. Thank you very much. So tomorrow, our session will start at 9 a.m. Okay. Yeah. So see you tomorrow. Everybody.
See you tomorrow.
See you tomorrow.
Keep healthy. Thank you.
Okay.
Bye.
Keep healthy. Thank you.
Okay, thank you very much for all of the participants of this event, all of the speaker, all of the presenter, and also all of the chair for today. This is the last session of the day 2, and hope we can see you again tomorrow in the last session of WALCOM 2022. Thanks for your attention and good evening.
Okay, good afternoon in Europe, right?
Okay.
Bye-bye. Bye-bye. Good evening and have a good lunch, Petra.
Yeah. Okay. You.
Thank you.
Petra. Yeah. Okay, bye-bye.
Thank you. Bye-bye.
Thank you.